by 10 o'clock, and we'll be in good shape and we'll be back on schedule. So I think we have an exciting plan here. Some very good discussions, economic, environmental, green road to space, engineering, background and knowledge. We've got a lot of stuff. And then we're going to end up with Vern Hall, who's going to put it in perspective. What are we really talking about? Everybody likes to talk about spacecraft or something like that. Vern's going to put it in perspective that it's just another element in the transportation infrastructure around the globe for humans. And if you think about that a little bit, you start saying that it's a natural step off planet. Okay, just putting this in perspective, where are we? Well, we have a lot of people with a lot of dreams. The National Space Society, and I understand the Foundation for the Future is now working with those guys. I love that organization. They're really good. They've been saying for 50 years that they want to have a thriving community off planet. Well, Mr. Bridenstine said, hey, let's take NASA, first woman, next man on the moon by 2024. Now, I would not be one to say NASA can't ever make schedules because they made 69. And so they can do that. Well, maybe 26. But anyway, the point is not when, but the fact they are going. Mr. Musk is already heavily on the way to Mars with his Starship. And Mr. Bezos has the idea of building the road to space for the next generation. So, we're there. The visions are there. So space elevators have stood up and said, we've got a green road to space. We're going to move massive tonnage, and we're going to do it safely. So we want to be the second lane in the space trip. Okay, so what do you get when you do a space access infrastructure? Okay, I just sit back and think of the San Francisco Golden Gate Bridge. That's an easy one. I love to take the ride over there. But anyway, the point is it's permanent. And how many jobs are there to build it? Well, wait a minute. There's also jobs to maintain it. They have a permanent crew painting the Golden Gate Bridge from one end to the other. And when they get there, they turn around and come back. So, when we think about permanent infrastructures, you have to think differently in the economic. And Kevin Barry's going to talk about that a little later. And we've got to think about what an infrastructure does for jobs and finances, economics, things like that. The thing that we offer that nobody else can offer is massive tonnage delivered to space because we scoot around the massive rocket equation. Okay, future strategy, dual space access. But the basic message is we take mass to geo and beyond in a green road to space. Okay, permanent. I just talked about this, but basically, space elevators have a capability of doing it every day, forever. And the rockets are there to really supply different orbits and move people rapidly through radiation belts. The strengths of rockets are really tremendous. We don't want to shortchange rockets. They're really, really good. And by the way, that's what we have today, so we got to support them. The advanced rockets, the New Glenn, the Starship, those are remarkable. The SLS is remarkable. And then, of course, you got to remember the Chinese have like 4 new rockets they're building, 2 huge ones. The Russians are building new rockets. Everybody's building new rockets, European Space Agency. Those are good. We support new advanced technology rockets. They have plenty of missions, low Earth orbit, things like that. But the space elevator strengths are really out there beyond what you can do with rockets. Now, here's what we see, and we published this in our document, Space Elevators of the Transportation Story of the 21st Century. We can put up space elevators, and there'll probably be competition between countries or corporations to end up with 6 space elevators, 2 in each galactic harbor. And if we have that, and we have the numbers right on our estimations, we'll be moving 30,000 tons a year. Now, to put that in perspective, and I got a chart later on, the human race has put 22,000 tons into orbit since 1957. 22,000. Now, we're going to do more than that in our first year of operations. And then when we ramp up to the fully capable space elevator, we'll be doing 79 metric tons a day from each space elevator times 6 is 173,000 metric tons per year. Now, those numbers are not even in anybody's comprehension, even Mr. Musk. There is no way rockets can move that amount of mass. Here's the numbers for the 22,000. You can check that out later. Here are the numbers of customer demand pull. We did this back in 2013 and 14. These are the estimates of needs mass to orbit. There's a lot of missions out there that are beyond what we're doing today. And the reason they're beyond what we're doing today is you can't do it today with rockets. We have 3 reference missions we always talk about. Space solar power. We're going to have 2 talks about that. And we recognize that space solar power is a big job. But Dr. Mankins, a friend of mine, says he can stop global warming. Think about that a little bit. Stopping global warming, even if he's halfway right and he just slows it down, you know, he really would contribute greatly to the environment. So he has a slight problem. 5 million tons. Now think of it at 20 metric tons to GEO for the big rockets. The New Glenn, Starship, SLS, they're around 20 metric tons to GEO. So that's 5 million divided by 20. Don't even go there. Okay, there's an example so that everybody understands what I'm talking about. There's a conundrum of rockets. The delivery of mass to the destination. Okay, if I want to deliver a package on FedEx, I expect it all to get there, and I expect them to use the airplanes again and the automobiles and the trucks again. If we use rockets, we can only get 1/2 of 1% of the mass to the surface of the moon. The rocket equation dominates. Now, we can use reusability all you want, but you're still only going to get 0.5% to the surface of the moon. 0.5%. And just think of this. The astronauts who came back and landed in the ocean, that was only 2/10 of the mass at the pad. 2/10. The rocket equation's a bear. And here's some other numbers just to talk about it. Atlas V, Falcon, the numbers are all draconian. It's 4% to LEO. 4% of the mass on the pad, you get to low Earth orbit. 2% to GEO, and 0.5% to the surface of the moon. Bummer. So what we need to do is ask the question, how much of the mass do you want to get to your destination? A space elevator takes off and 70% of it is payload, and all 70% gets to GEO or the apex anchor. 30% is tethered climber, and we reuse that. So it's 100% is either reused or supplied to your destination. So we have some approaches we have today that we're really talking about. And we really are ready to establish and start a space elevator development program. The strategy is dual access. And we're building the Green Road. So the promises to go to space by space elevator are so remarkable. We really cannot not take this step. Now, I'm not going to go over this list. If you think about bridges and train tracks, permanent, you don't have to play with them. They're just there. They're cheap, routine, daily. That's a characteristic of space elevators. Now, I'm going to real quickly, and I'm going to use these charts fast because I lost 15 minutes someplace. Anyway, we had a study at ASU, Arizona State University, right down the street here, and ISAC Research, and we looked at what we could do if we climbed up the space elevator and released at the apex anchor. The answer is we're going 7.76 kilometers per second. So we can get to Mars in 61 days. Now, the ones that just reached Mars just this last month were going for 7.5 months. Normally it's 8 to 8.5 to 9, but they had the fast track in their slow way. We can also deliver or release daily. Oops, wait a minute, rockets have to wait 26 months for the two planets to line up. Why can we launch every day? Because we have velocity. Now, it might take 400 days to get there, but I don't care how long it takes a hammer to get there. Pizza you'd want to send on the 61-day route. But turns out the daily releases is big. And then the other thing is we could send mass. Remember, 0.5% to the surface of Mars. By the way, that's being very, very gracious. It's a lot less than that, but 0.5% is a good number. Special strengths, rapid, release every day, massive tonnage. Okay, so we've looked at these three missions. I've talked about it before. And if you just divide by 20 metric tons, which will get to GEO and beyond, which is what we're talking about, those missions are almost impossible. I wouldn't want to say impossible, but they're almost impossible. Here's an example. We're going to talk about it later in detail, so I'm going to just use this. If you look at the green line and believe that that's the needs for the humanity over time for electrical power. Now, David's going to talk about this in detail. That's where we want to be, the green line. The orange line on the bottom is rockets. That's 1,000 launches a day. And then the blue line that slants up is space elevators. The only way to satisfy Dr. Mankin's needs is to use space elevators. Then if you do some numbers for Mr. Musk, 1 million tons to Mars, don't even think about it, 40,000 launches. Even if you do 1,000 a year, that's still 40 years. Plus, that's 1,000 launches a year burning through the atmosphere. So the near future, we want to provide a permanent infrastructure for space. And so our concept is a bunch of space elevators around the equator. This is where we're at, and that's what we're really hoping to do is really start jumping into the engineering validation. Okay, are there any questions? Look at that. I've got 9 minutes to go for questions. I was hoping for 10, so that's close. Anybody? Any questions?
Can I ask a question?
Well, I hope so.
Okay, Peter, thanks for the presentation. And I'm going to preface this by asking about a couple of assumptions that you made. The first was that you're looking to do 30,000 to 173,000 tons a year in your proposals. Is that the order of magnitude? Right? Okay.
Yep.
So, you know, what you had said was that this is beyond Elon's envisioning, and we've been skirting around the Starship discussion. And I'd point out that 173,000 tons is only 1,730 Starship flights.
No. You gotta make sure you understand what the numbers mean. If they want to send 100 metric tons to Mars, okay, which is what they want to do, along with 100 people, they have to launch 5 times.
No, that's not what I'm saying. I'm talking about strictly for the idea of putting payload into LEO.
So right. Okay, so you get into LEO. Okay, so then, you know, it costs you a factor of 4 to go from LEO to Mars.
Understood. I don't even want to talk about going to Mars. It's outside of scope.
Oh, okay. Well, I don't want to talk about LEO. We don't go to LEO.
Well, doesn't the space elevator go to orbit for the sake of discussion?
No,
right? Earth orbit.
Discuss what we're talking about. Space elevators are perfect for GEO and beyond.
Right.
We can go to LEO, but it would have to be really in equatorial orbit. Most missions in LEO are high inclination, so we really don't want to go there.
Okay. Well, it kind of comes to the second question that I had, where you're talking about the rocket equation.
Yes.
And I would suggest that that might be the wrong question. It's one that we all focus on, and I understand the rationale of all of that. But if I look at the Starship and basically just say it's a magic device that puts 100 tons in orbit, I abstract all of the fuel, propellants, and all of that comes from the rocket equation, then the question from a pure, not from an energy perspective, like you're discussing with the rocket equation, but from an economic perspective, the question becomes, what will the Starship charge to put that 100 tons into orbit on a per kilogram basis.
Could make it free. I don't care.
Well, that's actually what we're intending to do. So this is one of the reasons why I'm here, is that I'm trying to put forth a proposal that we will offer free starships to LEO.
Sure, fine. Okay, we agree.
Okay.
I have no desire to compete with Mr. Musk. Mr. Musk has a delightful program. I love his activities. I encourage him greatly. He's doing a fantastic job. His strength is getting stuff to LEO and having all reusability. I don't argue that at all. Let it be free. It's fine with me.
Okay, good to hear. And then part of the reason why I'm here is, like you, I've gone through the space elevator discussions, and they're almost invariably driven on the idea that it lowers the cost of getting, out of the gravity well.
That's correct.
And
it was that was the thrust of it until about 2015. We don't care about cost anymore.
What's the primary benefit of space elevators then? If
it opens up missions that you can't do with space rockets.
Okay. So you're literally not targeting the area of us being able to put lots of payload into orbit.
Into low Earth orbit and medium Earth orbit. And, I'll start arguing with you if you want to go to GEO. We can do it cheaper to GEO, even if you're free. Okay, there's a lot of other costs like environmental impact, things like that rockets are kind of like not very good at. But, we can go from there. But, I'll just concede. If you want to do it free, it's fine with me.
No, I mean, my underlying mission in the market that we're looking at is, to be honest, doing the O'Neill cylinder conversation.
Oh, right? Don't even bring that up. Don't even bring that up. You cannot supply 11 million tons to L5.
I'll rephrase it. I have a project right now, Voyager Station, that's looking at going up by 2027. And they're doing all kinds of robotic assembly, all that kind of stuff. I'm trying to make the business case that we can do it in 100-ton chunks.
Sure, fine, go ahead. I agree. I'll support you. But it's in LEO. It's in LEO.
Mm-hmm.
Right. And I support it completely. You want to do that in LEO? I think Mr. Musk is doing a marvelous job. He's really remarkable. He's got great vision. And, by the way, he knows how to do his vision, which is really remarkable. And he's doing a great job. I concede. Let's support rockets to go into the orbits that are hard for space elevators. I think that's great.
We're going to switch gears over to Bill Bredney. He had a question.
Oh, good.
Thanks, Chris.
Peter, great presentation. I guess the question is that's on a lot of people's mind is, why now? What makes it now that we can get to this point, that we can do this engineering analysis? What is it that really turned the corner that got us to this point that we can really start talking about it now?
Well, I'm going to let Michael Fitzgerald talk about that in his 2 talks. But essentially, we've done all the preliminary technological readiness assessments on all the things, plus the space elevator tether is now doable. We have Adrian Nixon talking for, 45 minutes today on the material that will be our tether. Now, I want to make sure we understand what Adrian's going to be talking about is 2-dimensional materials, and we'll focus on single crystal graphene. But there are about 1,000. He told me the other day there are about 1,000 materials that are starting to surface that have the same types of characteristics. So we've had a whole new arena of material science surface, and it's just remarkable. And it can, now I'm going to stand up and say it can be our tether. Adrian is probably going to say something like, we'll have tether material by the time we need it or something like that. But the thing that changed was the International Academy of Astronautics studies that said the technologies are there, and the 2-dimensional material, 2D material that surfaced in the laboratories across the world. And those are the 2 big things that have happened.
Perfect. Thank you.
Awesome.
Oh, one other thing. Let me toss one other thing. The other thing is the globe, humanity started dreaming again about going off planet. That's a huge driver. I mean, that was really dormant for so many years. And that's really turned around. The National Space Society has really helped on that. Mr. Musk has his vision. Mr. Bezos has his vision. We have tremendous hope surfacing across the globe. And that's a third factor that I think is really important.
Awesome. Thank you so much, Dr. Swan. I think we actually up to 10 o'clock on the dot.
Right. Can you imagine that?
Amazing. Thank you so much, Dr. Swan. Creating space elevator is actually a huge job, but as all space infrastructure, we can very much make it happen. And these are the conversations that we need to be having. So from Foundation for the Future and Blue Marble Week, thank you so much to Dr. Swan and ISEC. For more information, please visit f4f.space and isec.org. We're going to be moving on to our next speaker, whose topic is Architecture of Galactic Harbors, Transportation System and Enterprise Enabler. That is Mr. Michael Fitzgerald. Mr. Fitzer served in the United States Air Force from 1968 until 1990. After graduating from the United States Air Force Academy and serving in Vietnam, he returned to Los Angeles. There, he joined the United States Air Force Space Effort, and for 20 years in the Air Force, Fitzer has worked on major space development projects. Among these, he co-authored Today's Space Elevator and 5 other major reports on space infrastructure. He is working on publishing his 36 architecture notes and the Galactic Harbor. About the Galactic Harbor. So help me in welcoming Mr. Michael Fitzgerald.
Fitzer, you're not hearing you.
You're muted, Fitzer.
Okay, is Mr. Fitzgerald actually here, or is he just muted?
His picture is up. You can see him talking.
He says he has some problem with the audio.
What?
Tim, do
Friday
you have
he called in.
the number?
He shows up as unknown on the screen.
Do we have a new phone number from the previous Google Meet? Is it a new number?
It's the same number.
Fitz is showing up as unmuted, so something up with a microphone locally.
Oh, he's going for a phone. Going to his phone, trying to back up.
On Friday, we hosted most of the ISEC folks.
What does that say? What's that?
Password, I think.
Password? Oh, phone password. Anybody want to send them that real quickly? Fabio, you got the phone password?
I have it if you want to do it audio.
Well, go ahead. Give it
Go
to
ahead.
him. Yeah.
Fitzer, the PIN number 618 742 140, and then enter pound.
Uh-oh, Fitcher's not doing well here. Do we want to do Jerry and put Fitcher on a little hold while he's trying to make it work? Fitcher, put your thumb up if you accept switch. Did he put his thumb up? I can't see it right now.
He's thumbing up. Yes.
Okay, Jerry, are you there?
Yeah, I'm gonna miss some of the people I invited probably, but so be it.
Oh, okay. Well, let's see.
Can
Anybody have? Yeah, Jerry invited about 100 people, so.
Well, I don't know. It's not quite that many.
can we move on to the next speaker after that? Dr. David Dotson, would you mind?
Yeah, David, yours is pretty unique and set. David, are you there?
Yep.
Okay.
Yes, I'm here. Can you hear me okay?
Yeah, so why don't we go ahead and do David? And Michael, we're going to put you next, so work on your phone conversation here.
All right. So
Okay.
we're gonna be
Pause.
David Dotson. If that's
Hey, Fitz, I've got a new phone number and PIN. I'm going to send it to you right now via email. Sorry to cut you off, David. Go ahead.
Okay.
Here, I'm just
Leo, you going to introduce him?
Yes. So we're going to be moving on to Dr. David. We'll be talking on the topic of space solar power delivery to orbit, enabling environmental programs. Really quickly, Dr. David Dotson is a computational physicist with a background in macromolecular modeling and simulation. He has always been drawn to the space sector and is working to advance the cause to permanent high throughput space infrastructure. Aligning people and resources to enable this mission is a personal professional driving force for him. David works as an independent consultant, specializing in bespoke system and software engineering for ambitious science and engineering efforts. So it's our pleasure here at Blue Marble Week to welcome Dr. David Dotson.
Thank you for that introduction, Leo. I appreciate that. Okay, I'll go ahead and share my screen. 1 second. Can everyone see that okay?
It's coming.
It looks great. Thank you, David.
Perfect, thank you. Yeah, so as Leo said, my name is David Dotson. My background is computational physics, in particular physics-based molecular modeling and simulation. I still actively work in that domain, and you know, I love that domain as an independent consultant. And I currently do a lot of work as part of the Open Force Field Initiative, and recently started work on the Folding at Home network as well, which is the world's first exaflop computing system, if you've been following the news during the pandemic. I'm a relative newcomer to the space arena, but my interest in space elevators has persisted since I was a teenager. And I'm in a position now where I can actively work to execute on this vision that we've all long had. I intend to leverage my technical expertise and passion for ambitious projects to do my part in making space elevators a reality, delivering measurable value for humanity in the coming decades. But that's enough about me. In this century, global electricity demand is expected to roughly double from its 2014 value of about 2,400 gigawatts to over 4,700 by 2050. Now, China is a large driver of this growth, but India and much of the developing world is expected to increase its demand over the course of this time. The electrification of transportation in the US will also increase demand for electricity domestically, displacing the current use of fossil fuels for this purpose as well. But, of course, this isn't the whole story. Addressing climate change is one of the major policy priorities for many countries this century. And to meet the commitments of the 2015 Paris Climate Agreement, many of the world's leading nations are aiming for net zero CO2 production by around 2050. Among these are Japan and China, having committed in the past year to 2050 and 2060, respectively, for that milestone. Other major fossil fuel consumers, such as South Korea, the EU, and the US, have declared similar intentions. And they're certainly looking to set a specific target for net zero. Now, all of this activity is intended to limit the global temperature increase to below 1.5 degrees C by 2100. Major CO2 emitters achieving carbon neutrality, followed by carbon negativity, is necessary for a 1.5 degrees Celsius trajectory to be possible, shown here in green. To achieve this, vast increases in renewable electricity sources will be required. Now, we believe that space-based solar power can be part of the solution to both of these problems. For those unfamiliar, space-based solar power, or SSP, is an idea that has been around for about half a century, first proposed by Peter Glaser in 1968. This entails a satellite, often positioned in a geosynchronous orbit, featuring mirrors and a photovoltaic array for collecting solar radiation in space, a microwave or possibly laser transmitter module directed at Earth's surface, and a ground station with a receiver, such as a rectifying antenna, that can convert the received beam into electricity distributed via the local power grid. Now, such a system features many advantages compared to a terrestrial solar farm. We get consistent high output, largely independent of latitude. The system is not subject to day-night cycles, reducing or eliminating the need for battery storage at the ground station. In other words, it's almost always noon at GEO. A microwave beam is generally unaffected by local weather or cloud cover. And we get greater land usage efficiency compared to terrestrial solar. So with all of that, you might ask, with all these advantages, what is the problem? Well, Peter hit on this. The problem is that mass to orbit remains a major barrier. For a system like the SPS Alpha Mark II, illustrated here, to deliver 2 gigawatts of continuous power to a 28.3 square kilometer ground receiver at 2.45 gigahertz with a 2.45 gigahertz microwave beam. With these characteristics, this requires a whopping 10,000 tons in orbit at GEO, or 36,000 kilometers in altitude. So to say it again, for a 2 gigawatt system, we need 10,000 tons delivered to GEO. And to put this into perspective, this is on the same scale as the total payload humans have delivered into orbit and beyond to date, measured in the tens of thousands of tons. I should say that despite this, we're actually confident that with the launch schedules being pursued by Mr. Musk at SpaceX and Mr. Bezos at Blue Origin, deployment of such a system could be possible in the next decade. And there's a real opportunity here. If we take the 5 largest US cities, we can ask the question, how many SPS Alpha Mark IIs, for example, would it take to provide for their average electricity needs today? For today's needs, we could meet New York City's entire average electricity needs with a trio of SPS Alpha Mark IIs. We could meet Houston or LA's needs with a pair of them, and Chicago or Phoenix with about a single system. Now again, these are for today's requirements, and they aren't factoring in the requirements for peak load, but it does give a sense of the scale. It wouldn't take too many such systems to provide electrical power for an entire large city. Now, I said earlier that we're actually pretty confident that deploying SSP by rocket is possible. And I'll make that clearer here. In this table, we have a selection of launch vehicles from SpaceX and Blue Origin with max cargo mass values for putting the payload into a geosynchronous transfer orbit. So this is not low Earth orbit delivery. Now for the SpaceX Starship and Blue Origin New Glenn, these are our best guesses from material published so far. But the takeaway here is that thinking in terms of a reusable 20-ton to GEO launch vehicle is a useful exercise for assessing feasibility. Launch of a single SBS Alpha Mark II requires 500 launches with such a vehicle, even the 10,000 ton requirement. Now, as we just saw, we need about 3 systems to cover New York City today. This would be about 1,500 launches. And we think this will be feasible by 2030 to 2040. Elon Musk of SpaceX has stated his goal of 3 launches a day to support his Mars colonization effort, or about 1,000 a year. And that kind of scale for an SSP deployment program would work for meeting the needs of New York City. This is on the order of magnitude of what you need. But what about scaling out to the needs of the whole country? Satisfying 1/8 of today's electrical demand in the US would require 30 SPS Alpha Mark IIs. And now you can do the math. This is 15,000 20-ton to GEO launches. On a schedule like Musk is aiming for, this is 15 years of continuous launches, again to meet 1/8 of today's US demand. Today's demand. If we zoom out even further, if we want to satisfy 1/8 of today's global electricity demand, this would require 150 such systems. This is 75,000 of those 20-ton to GEO launches, or about 75 years of 3 launches a day for this kind of launch vehicle devoted to this program. This is too long to be part of the global climate change strategy in this century. It turns out that to meet 1/8 of global electricity needs with SSP by 2100, if you wanted to do this with rockets or a 20-ton launch vehicle, an average of 3,500 launches a year would be needed, starting in 2030 and extending to 2100. This is a 30x increase from annual launches today, globally, very few of which are heavy launch vehicles capable of 20 tons to GEO. Now, I want to lighten the mood a bit. This isn't a talk about what we can't do, however. I'm going to argue that if you want to deploy SSP at scales meaningful for a global climate change mitigation strategy in the 21st century, you really need space elevators. Now, this table gives the space elevator development program proposed by ISAC. It begins in 2037 with the first such elevator up and running in an initial operating capacity, or what we call IOC. An elevator like this is proposed to have a transport throughput of 14 tons per day, and we have columns on the right giving the maximum mass deliverable in a year, as well as the accumulation of this number over each year of operation. Now, shortly after having a first elevator, we anticipate having a second the following, probably at the same site the following year. And the ISAC program proposes 6 elevators in total by 2041, followed by a conversion of these elevators to full operating capacity starting in 2047. Now, each full operating capacity, or FOC elevator, is proposed to have a transport throughput of 79 tons per day. What this gives us is by 2051, all elevators will be operating at full capacity under this program for an annual throughput of 173,000 tons for the whole set of systems. Now, this development program could enable deployment of SPS Alpha Mark II at large scale. If full scheduled capacity were allocated to this effort, 4 such systems could be deployed at GEO by 2040. By 2050, we would have 56 SPS Alpha Mark II systems at GEO. And at full operating capacity for all 6 elevators, the total throughput could deliver up to 17 systems into orbit a year. Now, this is a remarkable set of statements, and recall from the discussion earlier that each SPS Alpha Mark II would require 500 heavy launches to GEO. The throughput of these 6 elevators in 2051 to GEO is the freight equivalent of 8,500 heavy launches a year. So where does this leave us? If we take as our mission deployment of SPS Alpha Mark IIs at GEO to deliver 1/8 of the world's electricity demand in this century, can we actually do it? Well, we'll return to our first figure. This is giving rising electricity demand, both historically and projected, to 2050. We can use this projection as our starting point for modeling forward in time to 2100, and we've done so here. The solid green, orange, and blue lines on the left give the projection model from the US Energy Information Administration. That was displayed as the dotted line in the previous chart. Divided by 4, 8, and 16 respectively. So this gives demand 1/4 of the global demand, 1/8, and 1/16 of global demand. We observe that this model is relatively linear over its domain from 2030 to 2050. And so we can likely get away with modeling it with a least squares linear regression and extrapolate forward to 2100. Now, this may not necessarily reflect the reality beyond 2050. You know, it's hard to make these kind of projections, but it is a starting point for analysis given the shape of the projection before it. And now we can take our discussion on heavy lift rocket launches from earlier and ask, assuming 3 launches a day, that is 1,095 launches a year, devoted to SPS Alpha Mark II deployment, starting in 2030, how much power could be delivered by SSP over time? We show this as the red line here. As we noted in that discussion, it would take about 75 years of launches at this rate to meet 1/8 of current global demand. But we see here that the rate of demand growth for that 1/8 line in orange actually outpaces the rate of deployment. A far greater average rate of 3,500 launches a year would actually be needed to meet this orange line at 2100 if you were starting to do these kind of launches at 2030. But what about the ISAC Space Elevator Development Program? If we had the full throughput of the program allocated to SPS deployment, what we get is the violet trajectory. Note that the slope of this trajectory is constant after 2051, where the ISAC development program ends at 6 full operating capacity elevators. And the throughput of this program would be enough to deliver 1/16 of global demand by 2056 and 1/8 of global demand by 2068, or 728 gigawatts and 3.6 million tons of hardware at GEO. What's more, by 2100, this set of systems would have delivered up to 9.2 million tons to GEO and beyond, a total of 1,842 gigawatts if all of that hardware was composed entirely of SPS Alpha Mark IIs. This is nearly 1/4 of global electricity demand by 2100. Now, this analysis is rather simplistic, but the conclusions are robust given the wide gap we see between what is proposed for launch rates by industry leaders and what would be needed to deliver SSP at scale. Even though it appears unlikely that an SPS program deployed via rocket would be capped at 3 launches a day for 70 years, it is also unlikely that space elevator construction and advancement would stop in 2051 if the ISIC program is successful. The gulf in throughput for hardware delivery between these two systems is too stark to ignore. This isn't intended as a castigation of rockets, despite what it may sound like. What we propose is actually a dual space access architecture for the 21st century and beyond, utilizing both rockets and space elevators, leveraging their strengths. As we saw, it's possible, and we believe actually likely, that rockets will deploy the first SPS systems. Rockets are incredible Earth-to-orbit systems for deploying new space technologies and opening up entirely new activities. They will also remain the go-to technology for putting humans into space, in particular, moving them quickly through the Van Allen radiation belt. But space elevators are needed for high-throughput, massive hardware deployment. They give consistent, continuous movement of freight to GEO and beyond. And they truly enable space technology deployment, such as SSP, at a scale needed for high impact. Not single systems, but hundreds of systems. The core message is rockets and space elevators are complementary technologies for enabling humanity's expansion into space. And the time for a concerted, funded space elevator development program is now if we hope to leverage their strengths in this century. Thank you for your attention. Are there any questions for me?
Great talk, David. That's a good summary of where the space elevator can enable environmental health of the planet, which is one of the missions. Massive movement of equipment. Okay, any other questions?
David, can you confirm, a lot of numbers there, so I just wanted to make sure that I was correctly understanding what you said. You were saying 1,095 launches per year would take 75 years to get to a certain level of capacity?
Yes.
Okay. That's with only a single Starship, right?
So that's with, how do you mean only a single Starship?
Well, the numbers that you're quoting are the same numbers that I operate off of Elon Musk. It's 1,095 maximal launches per Starship per year.
That's 1,095 launches a year. Elon Musk is aiming for 3 launches a day.
Right, 3 launches a day per vehicle, right?
I don't think that's his quoted number at all.
Of course, 3 launches a day is for a specific Starship from a specific facility. So if you have a fleet of 100 Starships, they could all operate 3 times a day, and that was based on return time for GEO in orbit and all that kind of stuff. So it's definitely a maximal, but the numbers that I use is 1,000 launches per Starship per year at peak.
So that's contrary to my understanding of, and to be fair, Elon Musk has shared some of this just via tweet, so it's not necessarily easy to pull out the nuance.
He was just winging it, right? So he basically said, let's say you got a 4 to 6 hour turnaround time, right? That's where the number came from, 3 launches a day, based on the assumption that you had to do a certain amount of turnaround time and refurbishment.
I don't think you're going to have a vehicle prepped and ready to launch quite that quickly. Now, I'm willing to be surprised by Mr. Musk because he tends to do what he sets his mind to. I don't know that I've understood his statement as meaning that. That seems a bit aggressive.
I would suggest we don't argue the numbers that Mr. Musk did. David said 1,000 launches a year, period. If you want to launch a third of that by having 3 launches a day by a single vehicle, who cares? The point is that it's 1,000 launches per day. I mean, per year.
And the point I really like to make is that even if you scale this number up substantially, it doesn't change the conclusion. So you would require 3,500 20-ton to geo launches a year, starting in 2030, all the way to 2100, devoted to this program to reach this point, if you can see my mouse.
Understood. I guess my counterpoint and where Peter's going, who cares, is that we're looking at literally ordering 100 Starships for a purpose like you have as part of the program, so that, you know, if you wanted to get it done in a shorter timeline, you can throw more ships at it.
I hate to bring up a silly point because we don't want to downplay the value of rockets, okay? But we are addressing the value of space elevators. If you want to start discussing the value of rockets, you have to toss in some other factors, like the environmental impact of black carbon on the ozone hole for every launch. And that's been a constant in every environmental impact statement. But they always come to the same conclusion. If we only launch a few vehicles a year from every site, it will not be a significant issue. If you ramp up to the numbers that you're talking about, the impact must be assessed. Now, I don't know what the impact is. Nobody has done that statement. Nobody has done that. But if we want to start talking about impact, let's talk about all the impacts, financial, environmental, and everything else. And so, Chris, I don't think it's a time to discuss that. We would love, by the way, we want to invite you to have discussions on how do we go forward. You've got some really good ideas. But, you know, today we're going to be talking about the benefits and beauty of space elevators. And so my suggestion is let's take this discussion offline.
Happy to do that, Peter. Happy to do that.
I'll put my email in the chat for you.
Yeah, thank you so much to Dr. Dotson for the presentation. I do agree that space elevators aren't a big concern for space. Thank you again to Dr. Dotson. We're going to be moving on to our next speaker. I think is Mr. Fitzgerald ready for his audio? Audio working correctly?
Yes, then he walks away from the system. Hey, Fitzer, you're on.
Might we indicate that my talk has been delayed about a half an hour, please?
Yeah. Fitzer, you on, or are we going to have Jerry? We could have Jerry. If you want to put your two together, I suggest we do Jerry.
Yeah, let's just move on to.
We'll do Jerry. Go ahead, Jerry. Introduction by Leo. I'm sorry, Leo.
Sorry.
Jumping in there.
It's okay, no worries. Mr. Fitzgerald, we'll get to you right after Dr. Jerry Eddy, who will be talking about Green Road to Space carbon emissions. Really quick, Dr. Eddy is ISEC's Board of Directors Secretary and the study lead and editor of the 2021 study entitled Space Elevators and the Green Road to Space. Over his 42 years of teaching, he was a professor of physics at Indiana University at Pennsylvania and Science Department, chair at the Stony Brook School in New York. So it's our pleasure to welcome Dr. Jerry Eddy.
Thank you very much. I'll try to share my screen. Do I need to push another button here, or are you seeing it? It's okay?
Yep, you're good. Thank you.
All right. Whoops, that's not good. Okay. So ISIC has just completed this 18-month study, the Green Road to Space, and it should be, what's showing on your screen is the cover page of the report and the fact that it is now available on our website, and you can download it and peruse it at your convenience. You'll see there's a significant list of authors. There are several chapters that have been written by different people. As you've heard, David, Dr. Dotson has written chapter 3 and presented it to you already. It was supposed to follow mine in the first place. Okay, so the main purpose of the study was to see if and in what ways the space elevator could environmentally benefit the Earth. I will outline what we found, show some detail of the major findings. The study assumed a complete operational space elevator system, which is called galactic harbors, except that we also considered, to a certain extent, the environmental impact of the construction and the operation of the galactic harbor, in which we found to be near zero environmental impact. We then focused on what benefits the space elevator could have on the Earth itself. Three major things that were considered were not new ideas, but ones that were dreamed of in the early days of the space program. These, of course, are space solar power, which David presented, nuclear waste disposal, and Earth-Sun shades at L1. In each of these, we contrasted the use of the space elevator to that of using rocket launches to accomplish the same end result. The author of the space solar, well, I was about to introduce David, which of course we already have done. I will cover the other two ideas and touch on a few additional ones that were considered. Bert Malloy did the main research and wrote most of the chapter on high-level nuclear waste. The idea of sending nuclear waste off into space is not new and was basically shelved because of the consequences of a possible rocket failure with nuclear waste on board. The space elevator eliminates that possibility. Bert researched all types of nuclear waste, but focused on spent reactor fuel and nuclear weapons because of the extremely long half-lives there that are involved. His research looked at all the various current ways it is contained and stored. The main result of this study found that it is a monumental problem and has minimal success for safe and long-term storage. So how much nuclear waste are we actually talking about?
Hey, Jerry, your slides are not moving forward.
There we go. Okay.
Nope, still got the original.
Oh, God.
There you go.
All right. I don't know what I did to make it happen, but okay.
Uh-oh.
Well, we'll find out on the next one. We're not interested in the details of this chart yet. I'll be explaining those later, but the total that I'm interested in here is the fact that it's 810,000 tons. Naturally, we want to dispose of the high-level waste in such a way that it is no longer poses a threat to Earth and our way of life. Currently, the consensus among nuclear nations is deep geological repositories. There are several interesting driving functions that are at play regarding this approach. Some of this waste has to be stored for up to 500,000 years. Therefore, disposal implies it must be extraordinarily unlikely for humans to encounter it accidentally or purposefully, and that no known natural or geological processes will make such exposure possible. The U.S. to date is the only nation to have actually done a significant amount of construction on such a site, Yucca Mountain in Nevada. However, the many delays since the project started have made the future of the Yucca Mountain facility extremely uncertain at best. Finland started planning for a similar project in 1983 and plans to finally apply for a license this year, with hopes to begin actual depository operations in 2025. Yes, 42 years later, actual usage may occur. Sweden had a similar problem, and their project is presently on hold. France chose a site in 1999. Construction was expected to begin in 2022, with initial waste disposal by perhaps 2030. But opposition to the project appears to be intensifying. Russia may also be getting a bit closer, since it has selected a site. Opening is not planned to occur till 2030. I need my next slide.
Fabio, can you move the slide forward, or can you put up a slide or something?
I used to have had a thing at the bottom of the page, but I'm not seeing it.
Yeah.
Hey, Jerry, I think
Yeah.
you're splitting on your other monitor. Can you move your mouse to your other monitor and click? There you go. Yep.
Oh, there you go.
Okay, good. Simple. Thank you. Thank you, David. So, how is it presently stored? This slide shows one example which has been recently developed and is now widespread. It is a method of chemically immobilizing the waste, which involves heating the waste with glass-forming materials to an extremely high temperature until liquid glass is formed. This is then poured into steel containers, forming a material like ceramic, and then permanently sealed called vitrified. These containers contain about 9.5 tons and can easily be carried by a space elevator, which can handle loads up to 14 tons, as we've already seen. One of the main problems is that spent nuclear fuel bundles can no longer safely remain in the reactor and be of significant economic benefit, have to be removed and stored under several meters of circulating water in an extremely large pool. Construction from reinforced metal-lined concrete. The pool is usually adjacent to the reactor building. This is commonly known as wet storage. Later, the spent nuclear fuel rods is either sent to a reprocessing laboratory or goes to a repackaging facility, and then to dry storage. Reprocessing the spent nuclear fuel leads to newly usable fuel. Reprocessing also leads to high-level waste products of only about 1/5 the original volume, but still dangerously reactive for several hundreds of millennia. The table also shows estimates based on the planned expansion by several nations for periods from 2019 through 2030 and 2031 through 2050. So the total already accumulated from weapons is shown additional here, vitrified, repackaged, and wet, along with the two future estimates, giving the total of 810,000 tons that we mentioned before. To take West to space on the space elevator would mean that it would be limited to the carrying capacity of the tether climber, initially 14 tons a day. Since some of the storage containers are heavier, they would have to be repackaged into smaller containers. It is likely that because of the climber's limitation, high-level nuclear waste containers in the future would be redesigned to allow direct shipment to the galactic harbors. Looking at the throughput, we see that the mature set of 3 galactic harbors in each of the 2 tethers, a total amount of cargo that could be carried would be 84 metric tons per day and 30,660 tons per year, from about 240 to 247. The chart shows that a projected throughput in the future, when additional elevators are added, would increase that amount greatly. So what happens after it arrives at apex anchor? We see that in this diagram, you see the Earth, you see the elevator out to 100,000 kilometer altitude. When the elevator is in position toward the sun, the load would be released. And we see that the apex anchor velocity is such that the difference allows a velocity of 21.94 kilometers per second. which would put the package into an orbit around the sun, but could still reach the sun when it got to perihelion. So when the craft reaches aphelion, an attached rocket would be fired to give it a new orbit well within the Earth's and never to have to be dealt with again. Having a safe, permanent storage way of dealing with high-level nuclear waste would encourage a greater use of nuclear power to meet the future electrical needs of our planet, and doing it in a non-polluting manner. The second benefit that I want to talk about was proposed by Dr. Roger Angel, a professor at Arizona University in 2006. He proposed the idea at a National Academy of Science conference in May and received a grant from NASA just a few months later in October. He proposed to put a sunshade in space at the L1 position between the Earth and the Sun. It is where the object with the correct orbital velocity would stay permanently in orbit directly between the Earth and the Sun. The plan is to make trillions of 2-foot in diameter discs, ultra thin, about 1 gram each. As shown in the diagram, the distribution of the flyers is designed to spread out in an area. This is how Dr. Angel described it. The plan would be to launch a constellation of trillions of small, free-flying spacecraft 1 million miles above Earth in an orbit aligned with the Sun, called the L1 orbit. The spacecraft would form a long, cylindrical cloud with a diameter about half that of the Earth and about 10 times longer. About 10% of the sunlight passing through the 60,000-mile length of the cloud, pointing lengthwise between the Earth and the Sun, would be diverted away from our planet. The effect would be enough to uniformly reduce sunlight about 2% over the entire planet, balancing the heating of a doubling of atmospheric carbon dioxide in the Earth's atmosphere. Researchers have proposed various alternatives for cooling the planet, including aerosol scatterers in the Earth's atmosphere. The idea for a space shade in L1 to direct sunlight from Earth was first proposed by James Early at the Lawrence Livermore National Laboratory in 1989. The earlier ideas were for bigger, heavier structures that would have needed to be manufactured and launched from the moon. Angel said, I wanted to make the sunshade from small flyers, small, light, and extremely thin spacecraft that could be completely assembled and launched from Earth in stacks of 1 million at a time. When they reach L1, they would be dealt off the stack like cards into a cloud. So there would be nothing to assemble in space. The lightweight flyers designed by Angel would be made of a transparent material 1 meter in diameter, pierced with small holes. Each would be 1/5000th of an inch thick and weigh about 1 gram, the same as a large butterfly. It would use MEMS technology mirrors as tiny sails that tilt to hold the flyers in position in the orbiting constellation. The flyer's transparency and steering mechanism prevent it from being blown away by radiation pressure from the sun. The total mass of all the flyers making up the space sunshade structure would be 20 million tons. At $10,000 a pound, conventional chemical rocket launches is prohibitively expensive. Angel proposes using a cheaper way, developed by Sandia National Laboratories for electromagnetic space launches, essentially a railgun, which could bring costs down to as little as $20 a pound. Once propelled beyond the Earth's atmosphere and gravity with electromagnetic launchers, the flyer stacks would be steered to L1 orbit by solar-powered ion propulsion, a new method proven in space by the European Space Agency Smart 1 Moon Orbiter or NASA's Deep Space One probe. The concept builds on existing technologies, Angel said. It seems feasible that it could be developed and deployed in about 25 years at a cost of a few $1 trillion. With care, the sunshade could last about 50 years. So the average cost is about 100 billion a year, or about 2/5 or 2/10 of 1% of the global domestic product. He added, the sunshade is no substitute for developing renewable energy, which is the only permanent solution. A similar massive level of technological innovation and financial investment could ensure that. But if the planet gets into an abrupt climate crisis that can only be fixed by cooling, it would be good to be ready with some shading solutions. The idea was to do this only in a global emergency. So how could this be done? Well, in a very similar manner to the nuclear waste. You see the same initial velocity given to the flyers, but then when they reach near the sun, the first burn would occur, putting them in a orbit inside Earth. Then a second burn would be necessary to make that orbit more circular and actually then be adjusted to reach L1 position. The total mass needed is about 20 million tons. Again, an enormous amount of rocket launches would be needed to handle it, as Dr. Angel realized. Thus, the Saturn V rocket would take 1,200 years, certainly longer than our modern rockets, but they which would still be quite a long time. With the space elevator at initial operational capacity, it would take about 652 years, again, a very long time. When the elevator reaches robust performance, however, we see that it could be done in 11.5 years, a much more reasonable time. But if the planet gets into an abrupt crisis that can only be fixed by cooling, it would be a good idea to be ready with some shading solution that has been worked out. The space elevator could do it in a crisis and make cheaper and greener than any other means. I have a few other ideas to give you some thought on. First of all, polluting industries on the Earth could be set up at GEO. Thus, raw materials could be sent up on the climbers and finished products returned to the Earth. Since refining happens to be the most polluting industry, it would be obvious to refine materials collected from mining asteroids at GEO before sending them back to the Earth. And of course, these refining industries could be set up using the space elevator. Industries making heavy devices for space, particularly, could be done at GEO. Materials sent up on the elevator, then assembled in the weightless environment of space. So my time is about up. I'd just like to point out that there are a couple more chapters in the report that continue with this theme, that the space elevator is the green way to space. I'll be happy to answer any other questions that you might have.
Dr. Jerry Eddy, does anybody have any questions for him?
Since there is a few minutes left, I might point out one of my other slides here that you might find interesting. This shows the 12 items that the Environmental Protection Agency considers in giving during an environmental impact study. Very few of these pertain to the space elevator. The very few that do would be in terms of the operation of the spaceport or earthport, and those are almost the same as any oil platform. Thus, we can claim or do claim that the space elevator in operation would be near zero impact. Thank you very much.
Awesome. Thank you so much, Dr. Eddy. I know that the geoengineering is a very interesting topic. You have a couple more minutes. Do you want to elaborate a little bit more on anything?
Let's see, there's one other item, I think. Maybe if I can back up one slide. No, I guess not, unless there's questions.
All right. Any
Well,
questions?
can I make a little addition here? I think the report that Jerry is editing and the other authors are contributing chapters to is a monumental movement forward, recognizing that there's a difference between rockets and space elevators. We believe that it's a dual space access architecture that we need to go forward with, and we need both, but we have to make sure we understand the impacts of both. And the real thing that people don't comprehend, at least I'm projecting they don't comprehend, is that if you have train tracks to space, you can do missions you have never planned on doing before. You might have talked about them, but you'd never planned on it. And I use the example, the L5 colony. You know, Dr. O'Neill and Jerry actually met Dr. O'Neill way back, and we talk about that. It turns out that Dr. O'Neill came up with this concept and had his students designing this colony in space back in the 60s and 70s. And we've talked about it. And the only answer that anybody came up with is, let's go form a corporation on the moon and develop it on the moon and ship it to L5. Except that implies you put a colony on the moon that has to do oxygen and water and structures and everything for someplace else. And so, wait a minute, they got to develop their own colony on the moon first. Then you can do your colony out at L5. Because the answer is you could not lift off 11 million tons to L5. So the point Jerry's making is we can do environmental lifts and take stuff to L5 and not impact the Earth. And we can enable missions that you can't do with rockets, really. So that, I mean, everybody's admitted you can't do L5 colony with rockets. So it's kind of intriguing. And I think this report is going to stand up by itself and say space elevators are a good choice. And the only question is, can we build it? Now, the space elevator guys say we can. So we have to prove it. It's on our shoulders to prove that we can put up this environmentally green transportation permitted infrastructure for space. So thanks, Jerry, for doing that and leading the activities.
I'd just like to add one thing, and Peter mentioned that I met Dr. O'Neill. I actually was at a conference on small accelerators, which was my specialty, and he was the keynote speaker. And one of the interesting things is that the purpose of the L5 colony was to build and place solar collectors.
Right. So you had to build a colony at L5 before you could do SPS.
Basically, yes.
Yeah, interesting. But of course, you can't do the colony at L5 until you do the colony on the moon.
Yeah.
So taking space elevators, putting them in that equation circumvents so many problems. So we need people to think about space elevators enable missions. They're not just cheaper. They enable the missions. It can't be done otherwise. Okay.
Exactly.
Thank you, Jerry. That was great.
Thank you.
All right, awesome. Thank you so much, Dr. Eddie, for that. I think we're going to go on to Mr. Fitzgerald if he has his audio ready yet. Not sure if he's...
Jerry, you have to stop sharing. There we go.
Fitz is showing as muted now.
Are you ready, Fitzer? Yeah, he's got his phone. He's about ready to go.
While Fitzer is working on getting his phone lined up, I wanted to point out the conversation that was going on in the chat between Pete Swan and Swan. I don't know if you remember Major McLean. He was Captain McLean last time you met him.
You went on mute, Michael. Captain McLean was the last I heard.
Oh,
Okay, I don't know if you remember the conversation you're having with Sean McLean. He's now Major McLean. He was Captain McLean back when he came to one of the early, maybe 2010, maybe 2012 Space Elevator conferences. So he's been watching this thing from his position at Space Force for quite a while. I just wanted to let you know, the relationship there. He asked a pretty interesting question that's worth scanning the chat while we're waiting for Fitzer to join in.
Hey, Sean, I was in the Space Force before they called it the Space Force, okay? Okay. I love what you're doing. Whatever you're doing, it's good.
all right. So before we actually go into Mr. Fitzgerald, I think he's still having audio issues. I do want to see, I think we have Emily Mishler. Emily, are you here on the call?
I am, yeah.
Right, perfect. So we have an announcement for Emily Mishler. She's here, a part of Foundation for the Future. We have an announcement for her. I don't know if you're ready to go on right now, Emily.
Sure, I'm actually just going to keep my video off, not camera ready, but I am ready to give a little blurb. So my name is Emily Mishler. I do some of the development work with Foundation for the Future. And I know that we've all been really impressed with the incredible speakers, the agility, and also the nimbleness of many of us. So really appreciate your patience with all the glitches today. And we are so grateful that as a Foundation for the Future, and also with March 2021's Blue Marble Week, we're so grateful that you've stuck it out with us today. We're really inspired by the advancements our speakers, allies, and the Foundation for the Future are making in building the future of space exploration. And this future in space and beyond, as we've seen, is being built one relationship, conversation, and connection at a time. To continue this momentum in building and contributing to this caliber of event, this level of agility, the conversations we're having, and this community, we need your help. And that's not just those who are in the Google Meet, it's also those who are listening live. So we need your help as allies, attendees, partners, advocates, and friends to spread the word about our important work through social media, invite like-minded and like-hearted peers to our events, and to help us connect with the philanthropists and organizations who, the philanthropists and organizations who believe what we believe, that our future in space is ours for the building and the time is now. So we're really excited to share with you 2 different avenues to becoming involved if you're interested in financially supporting our work. And just to clarify, Blue Marble Week is a monthly event that is presented by Foundation for the Future. So if you'd like to get involved in either capacity, Foundation for the Future is your go-to. So on the corporate level, we have the opportunity to sponsor Blue Marble Week. More information is going to be available at the link that we can either put in the chat or make available through a QR code that we have. And the Foundation at large on a monthly and annual basis. Again, that is on a corporate level. So if you'd like to visit our website, it is found f4f.space. And we have more information on how to get involved, how to donate, really how to financially contribute and or connect the dots with us as we continue this exploration. On a personal level, if you, your friends, or family are interested in supporting us, we're soon to be launching a monthly membership through which you can contribute to and support building space infrastructure and economy for less than a cup of coffee a month. So our ask here is to help us bring space home, because the time is now and the world can't wait. And it's evident based on the professionals and experts that we have in this community that the time is ripe. So if you have any questions, please do not hesitate to reach out to us at the Foundation for the Future. Our contact information and a link to donate is available at our website, and more information can also be found there. So if you have any questions, please feel free to reach out to me or any of our executive members, Lila, Tim, Leo, Michael, Lane, anyone that we can provide more information and help clarify a path forward. We would love to continue to build this future with you. So thank you, and please don't hesitate to reach out.
Thank you so much, Emily. Emily is a part of our family here at Foundation for the Future, and she will actually be a part of a panel on Thursday. So please be sure to check it out. Moving forward, Mr. Fitzgerald, I don't know if your audio is working now. If not, then we can move on to the next speaker.
Fitzer says he was on. Do you want to try again, Fitzer, with your phone? Did you hit mute, unmute? We ask all these dumb questions because we have no idea what we're doing here. we have two major presentations by him. We need to work with that.
Yeah,
No, can't hear you. Anybody have a clue? Want to send an email to Fitzer on how to? It worked on Friday. Bummer.
yeah. We'll try to get that resolved internally. In the
Well,
meantime,
how about if somebody like Michael or Leo, if you call Fitzer on his phone number, I'll put it in the chat, and then you could hook him in a joint call or something.
yeah, Michael, is there any way that you could help us with that really quick while we present?
I'll try that. I don't have Fitzer's number direct.
I am going to email it to you in two minutes as soon as I get it.
Okay.
Okay. Yeah, let's go ahead. Let's go with Kevin, I guess. Kevin, you ready?
Yeah.
All right. I'm ready for Kevin, man. I've been waiting.
Yeah. Perfect. So Kevin Berry is actually going to be talking to us about remarkable economic returns from permanent space infrastructure. Kevin Berry is actually a student of history, an avid gamer, and a business analyst. He has published several papers in historical economic trends and how they apply to commercial space development, observing the correlation between the rise and fall of civilizations and the quality of their infrastructure. Kevin Berry is an active member of ISEC and part of EFRAF's financial subcommittee, as well as infrastructure consulting specialization in space, business development, financial analysis, and thought leadership. Thank you so much, Kevin Berry, for being a part of Blue Marble Week. Take from here.
Thank you. And I will take and share my screen here. Should have my presentation ready to go. Right. Everybody can see my presentation all as well?
Perfect.
Right. And let me just get rid of the CC on this. Okay, so I just want to start out by saying thank you all for being here, and I want to address Chris's points from earlier. Unfortunately, it seems that he has left the call today. But you know, when considering the economic value of a space elevator and the true value that we can derive from it, the purpose of my presentation today is to really change where that paradigm is heading. In order to do this, I'm going to go over 4 different major points to analyze what is the value of a space elevator, how do we fund one, and you know, how is the space elevator conversation need to be changed in order to fully understand and validate the reason for building one. It is, at the end of the day, no matter how you cut it, a very expensive endeavor that, because it's never been done before, is just inherently risky. And being able to address those concerns, I think, is the chief reason for having panels like this today with Blue Marble Week. So I know that many of you here, I'm just preaching to the choir. One of the first things to address is just simply, what is the value of space? Why do we even care? I mean, we've had plenty of panelists already today talking about the value of having, you know, hundreds of thousands of ton in orbit, but to what end? And I would argue that there are really 5 major categories of reasons to go to space. Extraction alone is one of the first things people can think of and understand, whether it's mining minerals on the moon, Mars, or even the thousands of asteroids that actually orbit even closer to Earth than the moon, let alone the asteroid belt itself. You know, the mineral values in these generally have mineral concentrations in excess of 150 times the richest veins that we can find on Earth in terms of density. And you can find figures that give, frankly, ludicrous values, where asteroids in the asteroid belt have an estimated mineral value in the quintillions of dollars, more than a 7-fold increase the entire Earth GDP. Space solar, as has been discussed here, is an immense resource, to say nothing of just even orbit around Earth. there is a huge amount of solar capacity that we can embrace, building up to sort of the very, very long-term ambitious goals of something amounting to a Dyson swarm. And even just water in space, based on our launch costs and based on the difficulty of getting things there, just having liquid water in space is worth thousands of dollars per kilogram. And, you know, as rockets have gotten better and better, this number is dropping, but it's still an extremely valuable commodity, even though it is basically free on Earth, just simply because of its outside of the gravity well. Scientific, you know, this is one of the primary uses of space, is to go in, analyze on the International Space Station different experiments in microgravity, better understanding the radiation environment, astronomical observation outside of our atmosphere, where we get a more unobstructed view of the universe around us. There's certainly far more than I need to discuss here about the scientific value that we can derive from being in space. Observation and communication from satellites, GPS, the Copernicus constellations, Starlink's ambitions to provide global internet. There are many uses of having near Earth observation satellites and communications relayed through orbit. And it has allowed a massive proliferation in the ability for humanity to communicate all over Earth and increasingly in space as well. Looking a little further into the future, constructs will also eventually start to make a major impact on what is the value of space. That, quite simply, expansion into space affords a massive opportunity, even beyond colonization. The mention of constructs like the giant O'Neill cylinders, which provide centripetal acceleration in large rotating cylinders, space hotels, refueling depots, stations. There are a myriad of different objects of various mega engineering scales that could eventually be constructed in space, as there is almost an unlimited amount of real estate to expand into and to construct. And finally, you know, we've touched on this in the previous presentations, there is an immense existential value to being in space. You know, life is exceedingly rare on Earth, if not unique to our planet. And being able to not have all our eggs in one basket on Earth is of great value. And besides, taking and focusing humanity on looking up and to the stars is a much better use of our resources and our time than trying to look around and point fingers at each other and use our, you know, capabilities as a species to, you know, try and fight over limited resources on Earth, when there are so many things that we can extract and utilize and use in space. So these 5 categories are sort of the building blocks of why we would even care about going to space in the first place. And, you know, as we've begun to mention here, there are lots of ambitious opportunities. The space solar power, as has already been discussed, the increasing number of mega constellations, developing a cislunar economy, and the Artemis program's goal to create the Gateway space station and eventually develop a connection to the lunar surface, whether it's for mining helium-3, going after lunar ice, or any other number of uses that we can have. The moon, as our closest celestial body, is a very reasonable target. Moving on beyond that, this is the graphic, which I'm sure you've all seen, of Musk's ambition to colonize and utilize the surface of Mars. And all of these have huge mass requirements. To figure out how to get to these places is very difficult. And this is much of the limiting factor that my colleagues have already addressed. You know, getting these objects into space is, with the rocket equation, very draconian. You know, I won't reiterate what she said, but, you know, in short, even with 3 launches per day, which is 10 times our current rate, that would take 183 years just to get this 1 million tons to Mars. And, with space, solar power, any number of the other things that we've already discussed here, that number just continues to bloat and grow. And while it is certainly plausible that Starship will be able to launch multiple vehicles, there very quickly becomes limitations of the environment, of being able to achieve more launch windows. And ultimately, even if Starship is everything that we hope and dream it can be, it still has a limitation of sending rockets only every 26 months to Mars, because we have to wait for planetary convergence and to travel along the most efficient paths. And there's a 9-month journey in between when we leave Earth and when we arrive at Mars, and having to wait on the other end. And these factors just make it so that it is very difficult, and there are very high barriers to entry to accessing space for any of the reasons discussed. But I would argue that actually kind of our most limiting factor is shown. This is an old picture of what Singapore looked like. And that there isn't sufficient infrastructure for space commercialization. And in many ways, space is an outpost. It's something where we can send objects, they're there for a couple of years, but then, or maybe 15, 20 years, but ultimately, they have to just be put in disposal orbits or left where they are, like a car running out of fuel on the highway. And, it's not really a commercial environment so much as it's a speculative venture, and that without building up that infrastructure, that's really all that's ever going to become. Building up the highways, the trains, all of these metaphors of infrastructure we have on the ground is what is going to be necessary to achieve true commercialization in space. And so for my purposes, I've looked back at history and how we value infrastructure. And I think one of the simplest analogies of why infrastructure is so valuable is this simple analogy here. If you have something like a rowboat and you're trying to cross a river, rowboats are an easy technology. Like rockets, they exist, we have them, you can use them to cross the river. But if you are a farmer and you have a few thousand tons of grain, even though you have a rowboat, and you could probably build a whole bunch more rowboats, it becomes wildly impractical to manage shipping 1,000 tons of grain across even a small river just in a rowboat. Your chance of spillage, your chance of just congestion in the river just becomes overwhelming very quickly. And by comparison, a bridge is much more expensive and difficult to construct that first time. But it allows, wagons to cross that bridge, and it allows something like the concept of shipping 1,000 tons of grain across a bridge to be almost trivial. That there doesn't even need to be a toll. That bridges allow and facilitate access in a way that just simply wasn't possible before, even though transport may have been. And that is, I think, that the core of what infrastructure does, is that it allows decreased transaction costs and increased access, giving you new market opportunities, and that it is observed empirically that a linear decrease in transaction costs has an exponential effect on the market growth and gain, just from the network effects and the growth of opportunities that become viable once you have these decreased transaction costs. And so when you take and have a conversation centered around how much can I charge for somebody to cross the bridge, it's really kind of a self-defeating argument, that infrastructure at its very core is about decreasing transaction costs. So by charging a transaction cost, you are in fact countering the original purpose of having it in the first place. So as a historical example, I looked a lot into the Transcontinental Railroad. And the Transcontinental Railroad, shown here sort of in the orange and green line, was a very significant project for the United States to embark upon. And it allowed transport between New York and California to go from a 6-month harrowing journey to a 1-week casual trip. That in the end, it allowed the country to be joined in a way that it never had been before, not just because of the train line, but because of the telecom line, which you can see here on the right-hand side. That connecting these two sides of the country had a big impact, and it made new businesses entirely possible. Oranges grown in California were suddenly be able to be sold in New York, something that would be unthinkable without it. And to pay for this very expensive, difficult thing, which many other people have discussed, there were two companies, the Union Pacific and Central Pacific, which competed and were paid per line mile that they constructed. And this competition meant that, you know, they were trying to see which of them could build further, and they were paid in large part by grants from the US government of large swaths of land. In fact, 20 square miles of land per line mile of rail built, and that the value of the railroad was not in the railroad itself. In fact, within 10 years, despite all of the success I've just mentioned, the Transcontinental Railroad companies all went more or less bankrupt. The only ones that kind of survived was Southern Pacific, and Union Pacific was, you know, heavily subsidized and basically prevented from failing. But all of these railroads were actually not very good businesses. But the financiers of the project, the US government, and even the individuals behind this became exceedingly wealthy because of the massive increase in value that the Transcontinental Railroad provided. And that the land, all of the mines, all of the cities along the railroad were really where the true value lay. They didn't make money from having people pay fares to ride on the train. That was necessary to maintain the train, but the rail itself was not about the transaction costs on the railroad. It was about the opportunity to say, I want to go mine something in the Rocky Mountains and bring it to Chicago. And that suddenly all of the value of the Rocky Mountains was at the access of the whole country. And that the immense value you get from just the ability to move something from one place to another was what created so much of this value. And in many ways, to finance this project, the land itself was used as the speculative value and basis to pay for this, and that it wasn't based on the value of the trains. It was based on the value of the land and being able to reach that land, and the value that the land would be after the railroad was constructed. When before it was constructed, the land was basically free. Anybody could go out and settle it at no cost, and yet the land around the railroad was so much more valuable. Now, looking at another case, Panama Canal, which is a full presentation and story into itself, but much like what we are trying to talk about here with the space elevator, the Panama Canal actually had a long history dating all the way back to Thomas Jefferson and Napoleon. Thomas Jefferson, when he originally commissioned Lewis and Clark, he also sent out explorers to explore whether there was a passage or how you would get across through Latin America, and actually purchased this area that you can kind of see here in yellow and red, that the easement that was acquired by Jefferson was what actually enabled the construction of the Panamanian Railroad, and that the American Railroad, which was constructed several years before the Panama Canal existed, was actually the fastest way to cross between the oceans, and was a huge part in the actual success and construction of this gargantuan mega project, which created Gatun Lake and many of the other structures shown here. But that the development of the infrastructure of building an entire city for the workers, of bringing in the different drilling rigs and being able to bring them along a railroad, were all required to do this. And the US government used its naval power in both oceans in order to protect and even change the governance in Panama to facilitate the creation of this project. And that, if it weren't overshadowed by the beginning of World War I, only a few months after the completion, the Panama Canal has had massive geopolitical impact in allowing the United States to connect its coastlines in ways it would not have been able to do before. And this is another key point about infrastructure, is that infrastructure in many ways has an understated impact in our economy because, again, as a business, it just doesn't really perform very well. This project took more than 100 years and bankrupted France to construct. But it has since paid huge dividends in the value it has delivered for countries around the world in being able to traverse this canal only about 15 miles long. And so, when we look at the space elevator here, and this is ISEC's rendering of what they think one of the three main nodes is going to look like. It doesn't really make sense to talk about it on a cost per kilogram per year because space elevators are not about charging a transaction cost, nor does it really make sense to look at it from what does it cost to build this thing? Can we charge like overhead fee? Like, how do you value space elevator? Nor does it make sense to be like, well, whatever Bezos or whoever else will pay us, that's how valuable it is. We could have a further conversation about what is the cost of not having a space elevator? How much is it going to cost us to solve it in other ways? And I would say that at the end of the day, they're just not a good business. There's no way to cut it that space elevators are in and of themselves a good business, but they are great economics. They facilitate a huge proliferation of economic activity, seeing what could happen in the geo region, in the apex region. The ability to connect to anywhere in the solar system is of immense value, and that the value of a space elevator is not about what is the space elevator worth. It's about what is space worth and what does the space elevator allow us to access and allow the economy of Earth to reach out beyond our orbit and reach these other things, and that the space elevator is in many ways a very effective tool to do this. So digging a little bit into the nitty-gritty, the history of the space elevator is also quite interesting. In short, I think that the biggest premise for me in understanding of a space elevator is to embrace that the space traction elevator is a relatively new concept. People have thought, Tower of Babylon style, or this Eiffel Tower that is actually a tower to space for a long, long time. But the traction cable, in the idea that the space elevator is hung in the sky based on the centripetal force that is felt by just swinging around Earth, is a new concept that was developed by Yuri and was, made much more publicly available by Jerome. And that, largely the recent history that we've seen with space elevators has been around this identification that the material of the traction cable itself is really the bottleneck. And there has been hype, based on the development of carbon nanotubes, and that this sort of following the hype of, well, what is this prerequisite material? How do we get it to start? And all of that hype that we first saw when we had carbon nanotubes, it kind of fizzled because there wasn't a clear way of delivering on the material promises of that. And now we have, sort of this iteration, which I'll leave Adrian to discuss further, of the development of more 2D materials, which have similar tensile strengths, but more ability to be created and, in future to be manufactured at the scale necessary to achieve these projects. And that, the benefits of a space elevator allow this space infrastructure that we've discussed about how there's a massive movement of cargo along the space elevator, but it's more than just the ability to move something in orbit. Honestly, rockets are pretty good at that, especially into LEO. Space elevators are much more about the ability to move things far beyond geo. That, David and Goliath style, when you take and you have 100,000 kilometer long sling around Earth, the kinetic energies that you can throw an object off of the end of that just dwarf anything that a chemical or even nuclear powered rocket can achieve in the short term. And leaning into that more and using the acceleration you get from falling away from GEO along the space elevator allows you to achieve immense speeds to deliver mass in reasonably high quantity anywhere in the solar system, if not interstellar. And that is just something that is just not achievable by rockets. Even if there is a level of price parity, of price cost, the uninterrupted exchange, the reliability, and the ubiquitous access to space elevators makes it so that, much like the original bridge I was talking about, a bridge is stable. You can depend on it. You know what throughput it has. You can plan for it. You can do the thing. It won't congest the river with traffic. It won't have spillage. It doesn't create as many problems as you get when you try and do it piecemeal. And that the business opportunities that this allows in the different economic regimes is really the main focus of where we should be looking. And so, looking at how to fund this, drawing upon those historical cases, it seems that there's much of a balance here of financing of any project. You have to take and say, finance does not create value, but it does allow you to borrow against the future and say, this thing that I am going to give you access to has more value, but I need to pay this barrier to entry cost to get there. And if you can substantiate the value, much like what was done with the Transcontinental Railroad, of how valuable that land will be as your collateral, and you get a loan from a financier, whether it is a bank, a government-backed debt, however you get it, that finance allows you to reach beyond what money you have available. That rather than funding this based off of equity infusions and grants given to the space elevator, those are not necessary ultimately if you can prove there is a greater value in having a space elevator than there is in not having one, and that I can pay interest on the difference. Then you are able to build towards and finance the creation of a space elevator based on the infrastructural investment. And infrastructure, again, from a huge preponderance of evidence, is a very low default rate. Even in developing countries in Africa, we see that infrastructure development has a failure rate of less than 3%. And it has returns for terrestrial infrastructure in excess of 20% compound annual growth. And that is just a very reliable institutional scale investment that can be made when you have the patience of large, long-term institutional investment. Even if it doesn't necessarily make sense as a short-term business opportunity, because it might take 10, 15, 20 years to build it in the first place. I'm just going to gloss over ISAC's approach here, as I'm sure it will be discussed in much greater detail by my colleagues here. But in general, ISAC's approach is to have various ground-based infrastructure from the HQ, ocean transport, and the marine node and the earth port connecting along the tether cable to the GEO node, allowing for interplanetary payloads going up to Apex, and to facilitate this tenuous line here, this tether connection with the development of 2D printable materials, and that to build up the engineering validation and to move through this chart here through engineering verification, design validation, to demonstrate how the product can be done through the process of building out the Pathfinder, seed tether, and eventually the initial operating capacity of the space elevator. And then moving on to reinforce and build up the structure to achieve the full-scale vision. As Swan stated earlier in the presentations today, we are just moving out of this technological feasibility stage where we have shown in a lab that the materials that we can develop do have this technical capability. And going through engineering verification of seeing how this material behaves outside of the lab, bringing it up to scale. Those are all projects that do need solutions. And I don't today have the answers of what those will be, but the process has begun. And as this process begins, the business development and the concept of how do you fund this, how do you go through that research, how do you build it up from the dream that we have today to the reality that we can build in the future. And that's the next part that I want to kind of go in and discuss. In general, I think that the discussion between public, private, and sort of hybrid public-private partnership is a discussion that is perhaps beyond the scope of the presentation today. But I'll leave this slide up here briefly just to get a concept of how private entities generally have more agile product development, quicker start, and are faster off the block, but they just don't have all the advantages that you get from a public in terms of better geopolitical negotiation, more legal integration just out of necessity, and there is more challenges that you have in public where it's harder. It takes a lot more public agreement. You have to have longer agreement horizons dealing with the political cycle. There are a lot of challenges to public and to private, and that most large-scale projects of this magnitude really do need to embrace the advantages of both systems, much like the Panama Canal did during its creation, heavily supported by the U.S. Army Corps of Engineers, but also by a large amount of Texas oil and gas industry that provided a lot of the equipment necessary to actually create the canal in the first place. And so this business development approach, which I have worked on and developed with ISAC, shows that we're just at the very early days of this process, and that as ISAC has developed a increasingly robust technical plan for what we're hoping to achieve, the next steps here is to show what a 1,000-meter tether would look like, even on the ground, to start building a Space Elevator Institute and develop that legal infrastructure, show how the space elevator works in space, and then after we've demonstrated it and gone through all of the engineering rigor to validate and prove this technology, start to develop the seed tether, develop the main Earth connections and all of the different nodes in the system, and build towards operating capacity. And through this whole process, going through and acquiring seed funding, moving on to Serial A based on the proof of concept shown here, allow a much more segmented approach where institutional funding, while the ultimate goal, is just an unrealistic ask to ask for the billions of dollars necessary to build the whole program. This incremental approach will have a much greater success pathway to achieving the space elevator in the long term. And so just to reiterate, right now, the needs for this is to build up the seed funding, to have core staff, business development, and to move this idea from a place of science fiction and a place of dreams, that we can have presentations and calls like the ones we're having today to say, how do we take these next steps? How do we finalize this technological feasibility and start to demonstrate the architectural design of Fitzer and Swan and all the other members of ISAC that have been working on diligently during the technical phase, and start to build up proven prototypes. And so with that, I'll kind of leave it here for Q&A that any of the audience may have.
Thank you so much, Kevin. The United States has always been a pioneer of infrastructure, and space infrastructure is no different. And the space elevator is just a part of that next leap. So while keep an eye on the clock, because we're going to be moving on to our next speaker at 11:45. We have a question from Chris Kent, who asked, as infrastructure, what would the life cycle of a fully functional first generation elevator be?
Sorry, I couldn't quite hear your question. Could you say that again?
Sure. He asked, as infrastructure, hold on one second. As infrastructure, what would the life cycle of a fully functional first generation elevator system be? He went on to further iterate with the bridge analogy. Some bridges are long-lived, some not. Most are upgraded in place. The climbers' parallel rail cars are presumably those would be swapped out for new models over time. But what about the tether itself?
So for the tether itself, I believe there are other people in this who can more cogently answer the question, but it is actually designed to be somewhat modular, like specifically to address the issue of just space debris alone. The tether is designed to have a multiple approach and to be replaced about every 7 years in different segments that it can be actively fixed and repaired. And as you correctly noted, or like Swan gave earlier with the repainting of the Golden Gate Bridge, it would have a level of ongoing maintenance cost, but that the comparative outlay of capital necessary to contribute that once the space elevator is in place is relatively trivial. That the sort of the goal of the space elevator is to achieve parity where whatever transaction cost it may charge would be for that ongoing maintenance, not for the initial capital construction of the project. And that is really a negotiation between what materials do you have, how much can they be repaired, and at what cadence does that need to be done.
That's really good. Inara actually gave a good comment. She asked, we need to get the general public to understand the vital need to establish large-scale space-based infrastructure, which is very important. Do you want to add to that in any way?
Yeah, I mean, I would say that in general, I think one of the biggest pieces of infrastructure is the importance of declining costs and declining cost curves. That, when we take and look at something like the expansion even to America, the New World, with the increase in availability of sailing technology, development of compass navigation, of accurate timekeeping for sailing, you saw that as you have a linear decrease in cost, you have an exponential growth of economy on the other side. And this has been observed too in aviation in the last few decades here. We saw that, from post-World War II, where aviation was almost strictly a military focused endeavor that was something that was just in development. Right now in space, we're seeing kind of those parallels that, the Apollo missions were the, Wright brothers plane of our era, and that building towards, that first commercial plane is a really challenging task, and getting to that level where in a matter of post-World War II or World War II, only a few soldiers had been on planes to by the 1990s, it was pretty much everybody in the middle class had been on a plane at least once in their lives. And I mean, that level of transition, that exponential curve, the cost of flight between World War II and the 1990s only dropped a little bit. Like, it was not a big change, but that drop in price made it so it became a near ubiquitous asset. And so when you build infrastructure of any stripe and you can decrease those transaction costs, it has a transformative effect on the economies that it in. And we've seen this again and again throughout history, whether it's canals, railroads, the Transcontinental Railroad, the building of the interstate highway system. Another great example of the interstate highway system is a garbage business. It costs a lot of money, it's not in well repair, and you earn nothing for it. The price of gas tax has been falling objectively since the 1980s, and yet the value to the United States is incredible. That a space elevator, like any infrastructure, is not a good business. There's no way I can say that it is, but it is fantastic economics, and it has this effect of being able to give a pile-on of, we can achieve all of the immense value in space by having a space elevator. Or really, today the discussion is about space elevator, but there are other technologies that exist that a space elevator enables, whether it be, an orbital ring or any other massive projects that are just not practical without having a space elevator as that first piece. And as our, lunar space elevator talk in a couple of days we'll discuss here, fantastic idea too. Very difficult to build one until you have a space elevator off of Earth. There's kind of a prerequisite step for all of these ambitions that we have. And once you have one, the other things become relatively trivial.
Very much so. So thank you so much, Kevin Barry. I'm going to ask if you could please unshare the screen. And we're going to be moving on to the next speaker. And as always, you can get more information at isaac.org and at Foundation for the Future's website at f4f.space. I think that, Michael, I think you were working with Mr. Fitzgerald's audio. I don't know if it's working okay now.
Okay. Can you guys hear?
Yes, we can.
All right. Fitz, speak up.
All right. You know, I have an old saying that I use myself, and this is just enough turmoil to make this memorable. You won't remember what anybody says here, but you'll remember Fitzer and his phone problems. It's probably what we're going to remember. I had a friend once who was a second lieutenant, just graduated from the academy. Peter was Jim Hogarty. He went to his first meeting at the Pentagon and was told to sit in the corner and take notes. Halfway through the meeting, he decided to use a cup of coffee. So he went to the general's table, pulled out a coffee cup, and every coffee cup hit the floor. And everybody in that room remembered Jim Hogarty. Rest his soul, by the way. He just recently passed. It's all part of the rain dance. I'm not going to say anything more than just this is the way it is. Look, all right, let's go to the next magic step, by the way, which is to turn out my charts. All right, let me see if this is working. And I'm doing this one, I think. Tell me if you see the charts, please. There's the architecture of galactic harbors.
Not yet.
What are we doing? It's always the worry. I'll ask Pete to immediately turn on his charts to make sure that we're seeing charts.
Okay, let me go to. Wait a minute. Okay, I'm on speaker. I'm going to make his charts appear.
I probably don't hear you very well because that's just the way it is. But
do you want to share your slides?
Okay, here we go. Oh shoot!
All right, perfect.
Okay, I'm about there. Share, turn, raise hand.
Okay, we see the charts. All right, now Fabio, I'm going to move through these quickly.
Sure.
But let me tell you what the story is real quick. About 7 years ago, Pete Swan called me and said, Fisher, we need to talk to a bunch of people that are working on a thing called the space elevator. And we need to get over the hump of what is the space elevator and how does it work. In that context, Pete and I and several others came up with the notion of next chart of exactly what we're going to do, okay? And it ends up being the galactic harbor. I love to tell the destination at the start, not at the end, and that's what I'm doing here. All right, next chart. This is one of my favorite charts. This is a picture from Google Maps, I think, Google Earth, of the Los Angeles Long Beach Harbor. And Vern Hall is going to follow me soon. He is the chief engineer of the redefinition of these two harbors. They're separate harbors, and he was in charge of the Los Angeles half. These are sister cities that never liked each other. But the point is, I live just off the upper left-hand side of this picture, and Vern Hall lives just off to the lower left-hand side. And I arrived in Los Angeles in 1974, and I have been driving past or through this harbor for 40 plus years. The transformation was magnificent. And the secret of Vern pulling this off, as it were, and his partners over in Long Beach pulling this off was simple. He had authority to do so. He and his team. And I want you to remember that for the rest of the morning. And this is sort of serendipitous in the sense that Kevin and Jerry and David have already told you we got to do this. This is essential. I humbly point to this picture of we've done this before. Next chart, please. There you go. All right. The first thing we did is we need to differentiate between what we're doing and what we envision. If you go back into your mind as to look at that harbor, there is a main channel in every harbor in the universe, although I've only checked on the planet Earth. The Space Elevator Transportation System is the main channel of the galactic harbor. The rest of the galactic harbor, which is all that stuff you saw that was dirt in my image, that's where the enterprises live. So I'm about to tell you what is the baseline Space Elevator Transportation System, based on the vision that there will be a galactic harbor. Okay, next chart, please. And what we did was we said, I know where I'm going when I get the transportation system, but I'm going to worry about the transportation first. And the notion of what you see there is a 100,000 kilometer tall harbor, quote unquote, or main channel, if you will. And that's it. That's what we're talking about. And the simple argument is, with the Adrian will show you here in a few minutes, a strong enough tether or tether subsystem, as I say with a wink to my friend Adrian, that we can do this now. All right, so we're building let me do it this way. We're going to start with the apex up at the top. It is the counterweight. That is where things leave. I'll show you that in a moment. The geo region, that's where the businesses will be. And the Earthport, which is the transportation nexus between Earth's transportation system and the Galactic Harbor transportation system. There are 14 kilometers on our baseline, 7 going up, 7 going down, it doesn't matter. Just keep the mass balanced, and a tether on the left-hand side and right-hand side. Now, the initial ops will be, well, skip that. I'll get to that later. All right, next chart. So I'm going to describe what is the transportation system. This is Vern Hall's baby. It is the Earthport Floating Operations Platform, and if you ask me why they have a floating operations platform, it's because that's what we need to make things happen. Okay? And I'm going to hang up on this guy so he doesn't interrupt me again. Now, the floating ops platform is the nexus between the transportation system of the world, and look, it is container shipping compatible. Next chart. Down at the lower, kind of the wharf level, or the arena, the surface level, and you'll see a bunch of room, the doors open on 2 of them, and there's 13 or 14 of those. And they're all clean room capable, and they're putting the stuff, the cargo, onto pallets, and they're going to slip it onto a small controlling barge sort of thing, and they take it over to the tether, and we'll send it up the tether. Now, let's think about this for a millisecond. This place is a permanent place. We may send one out after a couple of years and change it out like it changed cruise ships, but this is the nexus of the planet Earth's transportation. We're taking stuff headed to the geo or to the apex or elsewhere in the solar system. Next chart. The upper floors of what I just showed you is the op center. Need I say more? And I'll say a bit more in a few charts. Every single thing on every single climber is tracked via this operations center. Every single thing that's flying around inside the galactic harbor, and I'll show you that in a moment, is tracked at this operations center. This is the frontline operations center. The headquarters operations center is over on Access City, and I'll get to that, or Vern will get to that in his presentation. Next chart. This is the baseline. There's nothing here that needs to be technologically invented. Okay, next is the georegion. Next chart. What I've selected here is the imagery of the graphic that I put together actually 3 years ago, I think, Pete, right? And everything up at the georegion is, quote, attached, if you will, to the geosynchronous belt, the geobelt. I show green orbits. There should be figure eights, but I ain't good enough artist to show a figure eight. The green are surveillance satellites, small CubeSats that are running around making sure that everything in this region is where it's supposed to be. Now let's take a look at this region, notice. When I came aboard in 2013 or so, or 14 maybe, the geo part of the space elevator was one satellite at geo about 400 meters across, if I remember. This is 200 to 300 kilometers across and approximately 400 kilometers up and down. I know there's no up in space, but you get my drift. In other words, this thing is bigger than the state of California. And that is where the enterprises will be. That is where the power, space-based power stuff will be, in that blue cylinder. Next chart. This is our baseline vision. The apex region, next chart, is where things arrive and depart. And they go interplanetary. And now Pete Swan has described the fact that at 100,000 kilometers, you depart at 7.76 kilometers per second. And that's enough delta V, if properly guided, that's a customer responsibility, it can get to Mars. Now, that is an amazing baseline. And when we talk about a preliminary technology readiness assessment, which is where we're at, ready to start into phase B, okay, we're ready to start engineering what you're seeing in the last three charts. All right, next chart, please. Now, we're not dumb. We can't do everything. So we're expecting the business community to do some things. In the terminology of architecture engineering, they're called adjuncts. In other words, to make it simple, if you build a car, you're kind of expecting that there'll be a gas station around there somewhere. If you're building an electric vehicle, you're expecting that there will be recharging stations, if only in your own garage and elsewhere. That's an adjunct. We have 3 adjuncts at a minimum, and let's go through these, and this is very quick. And each of these is worth a master's thesis. Next chart, please. The first, there are 3 of them. And I kind of forget. Let's go to the next chart, please. This is the space debris adjunct. I wrote about it in architecture note number 25. It's online, et cetera, et cetera. There are 4 sub-functions that are going to be provided. And most importantly is the 4th one down, is that there is an active defense. We had a handshake with Jerome Pearson, rest his soul. And he recognized that if we were going to be a space elevator, then we needed an active defense component. But that was going to be provided by what the U.S. Space Force has in mind. And that program, called EDDI, is underway. They're having an operational flight sometime the next 18 months. They're having arguments with themselves about exactly which flight they're on. In other words, the space elevator has addressed, quote unquote, the debris problem. I described that in Architecture Note 25, and this adjunct is part of our baseline. All right, next chart. everybody in this room undoubtedly has heard about space situational awareness. We are part of that. We are an anchor user. The Combined Space Operations Center in this adjunct will advise us when things enter or even approach the various regions that I just showed you. They will be actively tagged. I don't want to go through that in any depth, but we're going to keep track of these things. And if they don't do what they're supposed to do, actions will be taken. Not by the space elevator people, but by the Space Operations Center. This asset, the Galactic Harbor, is important and will be defended by the Space Force. Now, with all due frankness, there's an international context here because the Galactic Harbor will be an international thing. That part of this adjunct is not resolved. I don't mean to say I'm, solved everything here, but in a baseline sense, I've talked to people that I've known at the 1-star level, and they said assets in space will be protected. We have a policy problem, but other than that, we're cool. Top of that, chart 18 will show. Fabio's looking for his button, I think. There you go. Anything that's sent to the Earth port to go up the climber to get to either the GEO or the apex, we need to know what it is. So we have a very aggressive tracked plan, support, and management of stuff that's entering the Galactic Harbor via the transportation nexus. Okay? That activity is housed in the Access City, and Vern will explain that when it gets to be his turn, which I intend to be quickly. In other words, if some robot, if you know what I mean, up at GEO, okay, needs a wrench, even the wrench will be tracked inside the pallet that is assembled at the Earth port, inserted into the climber, and dropped off at GEO. Now let me segue here just a little bit. I have not talked about the Enterprise system. That wrench will go to the Enterprise. It'll be taken to the place where somebody is doing satellite repair. Now, I make this a very simplistic point, is that we're there to service the Enterprise. And I think that goes to the heart of what Kevin Barry was saying, is that nobody's going to pay for there to be a transportation system if it doesn't go anywhere and doesn't transport anything. Well, we're addressing that in the manner in which we baseline the Galactic Harbor. And one more thought after is this is only the baseline. Between you and me and the fence post, if you know what I mean, we have several alternatives. We have a multi-stage space elevator. We have a thing I lovingly call the 5-leg tripod. We have, I tease Adrian all the time about I need a slightly different tether because I want to know what's going on, etc. Well, this is an active activity, and we're for example, we're having meetings. Weekly, Adrian, on the climber tether interface study to figure out exactly how much traction we're going to get in what Yuri and Jerome figured out was the best way to get to space, which is a traction technique. We have baselined this. Now, with all due humility, and not much really, but the point I'm trying to make, 2 times in my career, I have started programs that are larger than the $15 billion necessary for a space elevator transportation system. I've seen it, I've tasted it, I know what it takes, and I'm not bragging, I'm pleading. We need to do this. It's essential. End of thought. How's my time? I lost track a little bit. Go to 19 here, Fabio, please. I'll take questions if I can hear them. If I don't hear them, I don't plan on answering them. Oh yeah, my pretty picture. We are bringing the third dimension to the transportation network. And I think that's the theme of Vern's presentation. All right, I'm done with this one. Bill Britton's got questions. He's writing rapidly, but we'll get him later. Adrian's probably going to pick on me later.
Hey, Fitzer, just before we lost that slide there, I thought I'd just add one little other piece to build on the conversation. Those shipping containers you were showing have actually been incredible as a demonstration of how useful they are, and that it's been observed that the advent of shipping containers has had a greater effect on globalization than all of the free trade agreements that have happened since World War II, because it was the first time we saw a reduction in the cost of shipping in thousands of years of naval trade. And that by carrying that paradigm through to applying it to space, you would have those similar kind of gains.
This is Vern Hall speaking.
This is a good book about global shipping.
Kevin, you just took the quote I was going to give you. I'm sorry. Kevin, during my presentation, I was going to quote you, so you've kind of preempted me, but absolutely right.
Okay, I think
I
that's
recommend
excellent.
we go to the next topic, and I'll come back if necessary. Gentlemen, yes, gentlemen's appropriate. There's 9 pictures of guys here. Sorry, I know Lee's around somewhere. Lila. My other presentation is, frankly, a long story about how much testing is to be required. These dispersed mega projects, and I'm talking about something, first of all, bigger than California and 10 Californias away. We have to test everything massively. And my other presentation, which Dr. Swan, I think we ought to skip, frankly, because it simply reinforces the fact that if you decide that you know what to build and have enough confidence to test it inside out, you'll get to where you're going. All right? If you can test what you think you see, then you'll get to where you're going. So
Fitzer, we need that second presentation. We need you.
Turmoil, and we'll skip on to who's next, Vern or Adrian? Is that age before beauty, or vice versa?
No. Hey, Fitzer, we need you to go through your charts. 2 or 3 reasons. One is you have a lot to say, and I know it's hard on the phone, but we really, really need to see your charts and the conclusion that we're ready to enter the second box. And, that's basically where you're going to be. If you want to not have, 45 minutes, you want to cut it down a little bit, that's fine. But we definitely need to go through your charts. So please go ahead and present the second lift. And Fabio, that would mean you'd have to put the second batch on, please.
Yeah, Fabio, why don't you put the second set of charts up and let me skip through them on like the first 5 or 6. I don't know exactly. There's major points that, there you go. I'm seeing.
A half an hour is good. Good, Fitzer. Don't worry.
Okay,
don't worry about it.
As you can. And this is, go to number 3. You know it's me, so what the heck. One of the things that ISEC really is absorbing here is the notion that we need to take a look at the system engineering problem of a thing this big. So we're calling it architecture engineering. And with all due humility, I have used architecture engineering for the last 15 years. Bill Britton and I use it on something we don't talk about. The notion is, in the first bullet on the right-hand side, we are assembling the incompatible. What can be possibly more incompatible than something in the middle of the Pacific Ocean that we're struggling to keep from moving, and something departing the apex going at 7.7 clicks per second? The answer to that question is that we build intelligent interfaces, we do modeling and simulation, and we don't change out things, we evolve things. Okay, click. Next chart, please. We resolve this notion of assembling the incompatible, and this includes all of the segments in the transportation system, by enforcing or creating intelligent interfaces. And what they are is information exchange requirements, but they have been muscled up with artificial intelligence. And the artificial intelligence is built on the next bullet. Data collected during development and operational testing and modeled and updated constantly with operational data. Okay? Now, you go talk to some vice president, he's going to say, jeepers. I'm sorry, with all due respect, this is being done now. It's called cookies. Next chart. Next chart. Y'all know this. Next chart. What we're trying to enforce is that anything that happens in the transportation system, if it affects the behavior of something else in the transportation system, the affected system must be notified. Now, I thought Bill Britton would faint when he saw this, because he's been in ops management for probably longer than he's like to admit. But that's the essence of the manner in which we're intending on building space elevator in the Galactic Harbor. Next one, chart 8. Let's go to the next chart. This is the notion of the sequences. Usually when you build something, you have a system requirements review, a data review, and then you have a design review. Now, because we're doing all this testing to proceed, we got to get to testing fast, quickly. And that's what the sequences represent. We will do single string testing. There's a long story. We will do, if anybody's ever been involved in a major project, there's this thing called thread testing. Bill Britton nodding, thread testing. Thank you, sir. We're going to do operational testing, operational mode testing. We're going to, disaster event testing, jeepers. And then finally, we get to sequence 5, and that's like spring training. We go out and we practice all the various kinds of testing, all the various kinds of operations, all of the what ifs that my foreman tells me I need to worry about. And that's in segment 5. Now, between you and me, as the saying goes, you don't leave limited operational capability, segment 5, until you're done. But on the other hand, at the beginning of limited operational capability, segment 5, you can start doing business. So if you have something important to deliver to GEO or to the Apex, you can do it in segment 5. All right, so Tim Chrisman asked me, I don't know when he asked me this first, but I'm going to say it now. He said, how much do you need and when can you start operating? I said, 10 to 12 billion. No, I said 10 to 15 billion in 10 to 12 years. And that's what segment 5 is. Okay, Michael?
Okay.
All right, you see what I mean?
Yep.
Initial operational capability is when you hang the shingle. That's when the enterprises have already moved in. When we're selling to Congress, and we are, and we can have that discussion elsewhere, but if we're selling to somebody that's going to fund this, we need to say, we can start delivering stuff in 10 years for 10 to 15 billion. And then more stuff later. Duh. How many planes did FedEx have at, where's Kevin? Kevin, how many planes did FedEx have at the start of FedEx? 3, I think, right? Good heavens. How many years did Amazon lose money? You know, see, that's all going on in sequence 5. We're all grown-ups here. That's really important to understand that we're not going to leave segment 1 until we're satisfied. Next chart. Thank you. Yeah, next chart. This is all artwork, and I hope you love it. Bill's going to fall on the floor again. The P. Swan's going to say, "Oh man," and Michael Lane, stop giggling. Every one of those steps, every one of those sequences has an entrance criteria and an exit criteria, a simulation requirement, test data requirement, and you've gone to some senior vice president and said, "Sir, this is how much risk we're buying down by doing this." I have a dear friend, classmate. He says, "Fisher, you never sell anything unless you break or you break or satisfy rule number 1 on the military side." He says, "Explain to me what war you win when you have this and what war you lose if you don't have it." Well, that's what Kevin and Jerry Eddy and Dave Dotson have all explained all morning. And what Vern will say, and we're just doing the same thing, vertically. But we got to test and test and test. Okay, I got a couple more cute charts here, and let me go through them. This is going to start instigating questions, but next chart. The simple visualization of the sequences is shown here. We get to IOC. Each one of the steps that I showed earlier has been passed. We exited things, and we got to IOC. And the block before IOC is when we had limited ops, and that's the first flight. Okay, that's the first deliveries and whatnot. Okay, next chart. Now let's go slow here, just so we get the art. Let's suppose we've gotten to IOC. Let's just suppose, and somebody like Michael Lane says, "I need something bigger and faster because this customer needs it." And we say, "We don't make promises, Michael, but this is how we've integrated in an on-ramp logic. This is the adaptive evolution rule that I showed you on chart 1. So when you get to number 3, you take the data out of already performed sequence 3, you go to a new sequence 3, and then you do new steps. So the step before the last green square, you can promise the customer, Michael, that you can do this. And then the parallel with IOC square is the process of integrating it into normal operations of the various Galactic Harbor elevators. Okay? That's what we call adaptive evolution. It's critical. And Adrian, we might need a stronger tether to do some of this. Okay? And et cetera. Maybe we need better surveillance too. Next chart.
Very high.
Okay, I'm going to skip this one. This is obvious. What I was trying to make a point here is we're going to have parallel ops going on constantly, in my vision of what we're doing here. And this is another master's thesis, Kevin, if you want to work on it. Next chart. Okay, now this is cute. Every one of us in this room has heard of rapid prototyping. Well, this is what rapid prototyping looks like in my sequence thing. Every one of those boxes, right, has entrance criteria, simulation, test, et cetera, et cetera, et cetera. Every one of them requires you go to the senior vice president and get money. But in this case, it's rapid prototyping because you want to insert that adaptive improvement quicker. You dig? All right, now let me go to the next chart. Well, the senior vice president says, okay, I approve the rapid prototyping, but tell me when it breaks. That's a life test. Quote, long-term maturation. That's what that looks like. How am I doing? You getting the picture here? Next chart. This is when you're doing all that, because that's what you need to do. You got several customers, they have different wants and needs, and then you got to summarize it and put it into an improvement. Now, what's important about this chart is you go to the right, and that's supposed to represent that I've taken a normal improvement, a rapid prototyping improvement, and maybe even a long-term improvement, which is not shown. And I add up the assets, right, that are needed to do. In one case, I got 1, 2, 3, 4, depending on how you count. I got 4 boxes on top of each other. This gives me a great view of the asset requirements that I need to get through that day or that month or that year. And we've all been in this box or one of those boxes before. What I'm telling you here with express clarity, I hope, that the testing, observational awareness of what we're doing is critical. Next chart. All right. Now here's a story about that somewhat eclectic last thing I just showed you, and you're going to get test data all over the map. You know. Next chart. My simple argument is you need to put that together in a taxonomic order. And if you don't know what taxonomic order is, oh Lord. Bill Britton, you know what taxonomic order is? This is it. This is what makes it happen. This is the essence, okay, of the operator of the Galactic Harbor. All right, and I think that's sort of my last chart, but there's one more chart. And we'll be doing this for each of the segments, which is what this story is supposed to be. All right, summary chart, I think, is next. That's the operational Galactic Harbor. All right, that's the act, you know, and you got to be up there to do it in most cases. I probably got you ahead of schedule. Sorry about that.
Okay. Pitcher, I have 2 questions for you. Can we go back to chart number 6, Fabio? Way back to 6. Well, you can do that one right there. There you go. That's what we need right there. Okay, Fitcher, you show a dot right here at the entering the engineering verification. What I'd like to do is have you explain 2 questions. One is, how did we get out of box 1? And that's the first thing, you know, that we need to understand as a group. And the second is, what's next in box 2? And those are significant questions, and, you know, you got plenty of time to talk about it.
The engineering validations or verification, whichever word you want to use there, the engineering validation step, verification step, must be accomplished by the builder, because the builder is going to take the information that he learns from all of the tests I was illuminating in the last 10 minutes, all of those, right? And he's going to put them together taxonomically, as I say, and build his or that company's or that corporation's or that joint venture's Galactic Harbor. Okay? So now let's go back one step. Why should somebody be doing all that if he is depending on technologies that are not feasible or provable? What ISEC has done is, frankly, largely an Adelphic approach, and Kevin Berry is the only one in this audience that knows what a Adelphic approach is. We've gone around and asked people, how about tethers this? How about CubeSats that? How about sensors this? How about simulations of those? Will there be enough of a workforce? Will there be educational institutions that I can depend on to create the kind of people that can go from 1 to 2 to 3 to 4 here? And the problem we have, I don't know who the we is in that sense, but I'll just leave it there. That we have is China is working that problem, if you know what I mean. All right? And sorry, Kevin, one error on Kevin's charts is they have dismissed carbon nanotubes totally and gone totally to two-dimensional materials. Okay? I see Coleman's comment. Coleman works with the Florida Institute of Technology, and I appreciate your comment. You can depend on them. The question is whether they're going to show up in the magnitude and for the quantity. I think we'll have the talent, and you may not have the experience. You dig? There's an experience thing in here. Okay. Is that enough, Pete? You get my drift?
Well, we did a lot of technological readiness. We did a lot of technological readiness assessments, preliminary at best, but I mean, we looked at so many things. And so the transition from box 1 to box 2, I think is real. We can stand up and say that we're ready to join the engineering verification. And your point is extremely important, which is that we transitioned from more of a academic arena to more of a testing arena. And of course, the testing needs to be done by technical and large organizations that have real capability to test. An idea of hanging a 1 kilometer meter wide single crystal graphene tether from a bridge and then running a tether climber up and down that's essentially full size, or at least a model. Those types of testing have to be, conceptualized, laid out, planned, and then executed. And those are the steps we're looking at now. What do we need to do to enter that second box and get going?
Well, yes, and one of the things we did, and Pete knows this, but for the rest of you, is we took the technology readiness level and we set it aside. And we went out and about, and if we found companies that were working on something that addressed the technological feasibility of the elevator, we said, thank you very much. We won't tell anybody, but we acknowledge your existence. It's called state of the art. In some cases, we found out there were 2 or 3 companies doing it, and that's known as state of the industry. Now, what's important about those 2 differentiations is that these companies are not going out and looking for some sort of badge of accomplishment called a TRL. They're doing it for the corporate profit motivation of a company. God bless them. And I'm proud to say that between Pete and me and Adrian and 6 or 7 other guys on the ISIC staff, we were able to go talk to people. Okay? I still miss Mark Hasse from the University of Cincinnati. He has forgotten more about, two-dimensional materials, except for Adrian. He's a smart man. He's probably, the reason we haven't seen him is because he's working for somebody. That's what we want.
Yeah, it turns out that
we went from box 1 to box 2.
Yeah, you're perfectly correct. We in ISIC were focusing on the reality of what's happening out there. In the first IAA book and then the second IAA book, because it was a global book, they used TRLs as a standard. And we showed that the TRL levels for all the engineering was well along, significantly along enough to enter a program, except for the tether materials. And then that's accelerated rapidly since those books were put to press. Now, it turns out that all of us are sitting here looking at the entrance into the second box, one of the historic points that I like to bring out from my 2 mega projects is when we started those mega projects, we were small groups, 6, 10 people in a conference room saying, yes, we're going to go do it, or thank you for the $1 billion or something like that. We did not have answers, okay? We had boxes I called scheduled miracles. In the engineering world, when you take on mega projects, there are questions for the future, and you have to address them as significant questions and address them. I'll use one example that I think is so relevant. Turns out in Motorola, when we were doing Iridium in the early days, we came to the conclusion, I should say the technical guys doing the digital switch that would be in space came into the CEO's office of Motorola, so we're talking big time, and said, we can't do Iridium because our digital switch isn't fast enough. So the Motorola CEO said, well, wait a minute, you got to explain that. And they looked at our schedule and had a box there, and we call that miracle number 1. And he looked at it and he says, what are the requirements? And so we laid out the requirements, and he laughed. I mean, this is the CEO of Motorola, laughed at it and said, get out of my room, man. We're going to have that capability in speed and quantity in 18 months. We were not on the to know route. We were not in the processor arena knowing what Motorola was projecting on its capability in digital switches. And so he said, well, do you think if I use the modern modern digital switch, it'll work in space? We all looked at each other and laughed and said, sir, we can make anything you make work in space. And what we meant was have to put a heck of a shielding on the outside of it. But we made those digital switches work. Now, just to put that in perspective, most space programs freeze their design 2 years ahead of launch. Sometimes it's like 6. But anyway, 2 years before launch. We decided for the digital switch that we would wait all the way to 6 months before launch. In fact, they were ready 7 months before launch. But the point is, when we're moving from box 1 to box 2, there are still mega questions that go with every mega project. I'm sorry, Fisher, go ahead.
Yeah. Let me emphasize that a little bit. There are still questions, but what our assessment is that we can resolve it with engineering. But I know most of you on the line here remember that the United States of America was trying to, in 1960, launch a quote spy satellite. The first 13 satellites failed. The first 13 launches of the satellite failed. And it was a combination of launch failures and satellite failures and recovery failures, just imagine. And one of the things that we're going to have to deal with in the Galactic Harbor is to deal with the notion of failure. Now, first of all, I don't like the word failure. I like rather the notion of test insufficiency, because it turns out, especially in today's age of artificial intelligence, that we can learn so much by failures, so much by insufficiencies, so that when you in the world of government, that they're looking for avoiding risk, we in engineering absorb the risk and learn from it. That is an impressively important story. All right. For one, one of my famous lines. I'm sorry, Michael. Here's a famous line for you. There are false alarms, but some alarms are more false than others. And what does that mean? He says, well, I know jumping 98% of the way across the canyon is a quote failure. It's an insufficiency. and that gives us a target for whatever it is that we're testing on what needs improvement. Maybe it's operational, maybe it's material, et cetera. And I know everybody's nodding their heads out there. It's kind of, this is like the bobblehead, that sort of thing. That's what the Galactic Harbor is saying. Let's start that engineering verification, engineering validation activity, and get it done by industry. All right. I'm getting to be embarrassed here. I feel like I'm stealing the audience because I want to hear from Adrian and Vern. These are the people that have done it. And we need to get them online here somehow. And Rob too. You've been done it.
I just want to make sure everybody understands. I was not there in 1960. Okay, counter to your belief. I'm not that old. So anyway. So, Adrian, are you ready now? Can you go early?
Yeah, sure, Pete. We're flexible. How about you, Rob?
Yeah, good for that. Yeah.
Yep. Rob and I are going to do a double act.
Thank you, Fabio. Thank you, Michael.
Yeah. Just one quick question to the organisers, really. We've sort of been going constantly. Do you want us to dive straight into our presentation, or would you value a 5-minute comfort break?
Yeah, actually, if it's okay with you, Adrian, I'm going to present co-host, which will then present Emily, and then we'll get on to you if that's okay with you.
Fine by me. We'll wait.
Perfect. Thank you so much. I want to say thank you so much to Michael Fitzgerald for that amazing presentation. Up next, I'm going to actually present my co-host for this event. It's Lee Steinke. Lee is actually a geophysicist and business executive with a track record of delivering hundreds of millions in value through leadership of science, strategy, and operation. Her career spans Fortune 100 to small nonprofit organizations, and she has most recently been on the executive leadership team on a $1 billion PE-backed energy company. She shares the advisory board for the Rocky Mountain Association of Geologists and volunteers at Space Foundation on a program for the United Nations Office of Outer Space Affairs. Ms. Steinke holds a bachelor's degree for UNC Chapel Hill, a master's from Yale, and an MBA from Wharton. So without further ado, I want to present my co-host, Lee Steinke. Oh, Lee, I think you might be muted.
Thank you so much, Leo.
No problem. Thank you so much, Lee.
I'd like to take this opportunity to reorient everyone to this event and the organization that created it. And then I'll turn it over to Emily Mishler with Foundation for the Future before introducing the next speaker. Please feel free to drop your LinkedIn profiles in the chat to leverage the networking benefits of this event. Blue Marble Week is a nonpartisan conversation about near-term space infrastructure from now through 2035. This monthly event is organized and produced by the Foundation for the Future. And the Foundation for the Future is dedicated to the creation of a public-private partnership for space infrastructure development. To support this cause or to sponsor Blue Marble Week, please visit our website at f4f.space, that's the number 4. We are grateful for the support of both our corporate and individual partners. And now I'll pass it to Emily Mishler to go into a bit more detail.
Absolutely. Well, thank you so much. All right. How's that? Any better? Wonderful. Well, it's a pleasure to meet you all and be here today. My background is in philanthropy and creative solutions for revolutionary ideas. I've recently become affiliated with the foundation and from the nonprofit perspective, and have become a partner in building the development arm of the operation. So what does that mean? That means we're financially positioning the foundation to be able to continue this important work for years, if not generations to come. From our conversations today, it's abundantly clear that our work is disruptive, necessary, and the time is now. And that means we need your help. I've been both incredibly impressed with the comprehensive vision, expertise, dedication, agility, and momentum of the speakers today, and the vision of the Foundation for the Future, the powering force behind Blue Marble Week. I believe we can all agree that the future the Foundation is building is inspiring and worth investing in. This future, in space and beyond, is being built one relationship, conversation, and connection at a time. In order to continue this momentum in building and contributing to this caliber of event, conversation, and community, we need your help. We need you, our allies, attendees, partners, advocates, and friends, to spread the word about our important work through our social media, invite like-minded and like-hearted peers to our events, and to help us connect with philanthropists and organizations who believe what we believe, that our future in space is ours for the building, and the time is now. We are so excited to announce 2 different avenues to become involved if you're interested in financially supporting our work. On the corporate level, we have the opportunity to sponsor Blue Marble Week. More information is available at the QR code below. Perfect. Thanks so much, Lee. And the Foundation at large on a monthly and annual basis to support our important work and forward movement. If you, your friends, or family are inspired to support us as well, we welcome your contributions to support building space infrastructure and economy as we move forward. So our ask, help us bringing space home, because the time is now and the world can't wait. If you have any questions, please don't hesitate to reach out to myself, Lila, Tim, or any of our executive team or board members. Our contact information and a link to donate is available at the QR code available on the screen and is also available through our website, f4f.space. I'm happy to stick around and field any questions, and if not, thank you so much. I'm happy to turn it back over to Lee or Leo and our MCs for our regularly scheduled programming.
Thank you so much, Emily. I'll stop presenting that QR code now. Our next speaker will speak on graphene progress and its promising future for space elevators. Adrian Nixon is a founding director of Nixene Publishing Limited and editor of the Nixene Journal, an international publication on the fast-moving world of graphene and other 2D materials. Mr. Nixon has over 20 years of experience as a scientist at an international chemical company and holds several patents for his research there. He also served in global market information management and as a management consultant with a top firm. Mr. Nixon holds an MBA from the University of Bradford in the UK and is a chartered chemist and member of the Royal Society of Chemistry. He serves on the board of the International Space Elevator Consortium. Mr. Nixon, you have the screen.
Thank you very much. And Rob and I will introduce ourselves because we're doing a bit of a double act this time. So I'll be sharing my slides and Rob's going to start and then you'll see us chip in. So let's see if I can get the presentation up and running and we'll get the slides sorted. And can you all see this?
Yay, technology works.
Hey, brilliant. Okay, over to you, Rob.
Yes. Hi, everybody. Good afternoon. And, well, thanks from me and Adrian to ISEC and Foundation for the Future for giving us this opportunity. I'll do the first sort of section. Can you flip the slide, please, Adrian? So I'll do beginning. I'll do a quick sort of 101 about graphene and 2D materials for those of you who don't know much about it. I'll probably focus on the graphene powders and things like that and give you some examples of applications for the graphene powders. And then I'll hand over to Adrian, who will talk about graphene, graphene sheets of graphene and the space elevator, graphene films, and how that will work. So if you can just flip over again, Adrian. Yeah, so my name is Rob Wheeldon. I'm a director of Nixene Publishing. I've been working with Adrian for probably about the past 5 years now on Nixene Publishing and in the graphene and 2D sort of world. I originally was a business coach with well over 20 years experience helping small businesses sort of start up and grow. And more recently, as I got involved in the graphene world, I was one of the judges on the first graphene hackathon in 2019. And last year I was a tutor on the now Nano Centre for Doctoral Training at Manchester University on the commercialisation side of basically helping PhD students commercialise their research. Adrian, do you want to add anything to who you are?
Well, the excellent introduction covered everything, really, apart from
Yes.
the fact that I've just got 20 years of experience in industry. And one other thing, while we're talking about graphene in this presentation, we could open it and expand out in the Q&A perhaps to cover other 2D materials which have been alluded to already, but also carbon nanotubes as well, because we're not, just because we're presenting about graphene doesn't mean that we're against carbon nanotubes at all. So we're monitoring what happens there industrially as well. So we can pick up on that in the Q&A at the end. Back to you, Rob.
Okay, can you flip the slide? And I'll just say that, this is who we are. We're Nixine Publishing. We produce a monthly journal on both sort of technology and the market information around graphene and 2D materials. We're in our 5th volume now, so we've been going for 5 years nearly. Then we produce individual reports. So we've recently done the report for the Foundation for the Future. We're speaking at the NASA commercialization in space next week. And we've contributed to a report to Congress on graphene and 2D materials. So if you dig that report out, you'll find us in the reference section. Can you flip the slide, please, Adrian? This is where we're based. We're based at Manchester University in the Graphene Engineering Innovation Centre. Manchester is the home of graphene. They've got the National Graphene Institute, which is the research side of things with the Nobel Prize winners. And the Engineering Innovation Centre is the business side of it. It's about helping industry gain access to the academic research and the facilities, but it's industry-led. So if you've got good ideas around applications for graphene, you go to the Engineering Innovation Centre. GEEC is how it's referred to, and you can partner with the academics and basically try your ideas out. It's about rapid development, it's about rapid sort of prototyping, it's about failing fast, which I think somebody mentioned earlier, and helping you get that idea on the road up and running. So next slide, please, Adrian. So graphene, what is graphene? Well, for those of you who don't know, it is carbon. It's carbon that is 1 atom thick. So it's the same as diamonds and coal and stuff like that, but they're 3D materials. Graphene is a 2D material. It's 1 atom thick. Next slide, please. So where's it come from? These two guys are the Nobel Prize winners from Manchester University, Andrei Geim and Kostya Novoselov. What's interesting about graphene, prior to 2004, this stuff was considered impossible to exist. People had talked about it and thought about it, and theoretically maybe, but it was considered impossible. And what these guys did in 2004 was isolate the world's first 2D material at the university. They've got a sort of Friday afternoon program where they just I hesitate to say goof around, but they follow the research that they want to do rather than the funded research. And using Scotch tape and pencil lead, they isolated a 2D 1 atom thick layer of carbon. They then went on to characterize the properties of this graphene, and that's what they won the 2010 Nobel Prize for. So if you flip to the next slide, Adrian, we'll understand some of the properties that they learned from isolating and characterizing graphene. So it's 200 times stronger than steel. That's why it's probably going to be a good candidate for a space elevator tether. It's the world's best conductor of electricity. Basically, it's 1 atom thick. The electrons shoot across the top, and it conducts electricity really fast. It's stable. It's non-toxic. It's flexible, it's transparent, it's very, very light. But also, another reason why it's potentially a good candidate for an elevator tether is it's got the highest melting point of any material in a vacuum. It's 100 times more tear resistant than steel. It's the world's best conductor of heat. And these amazing properties, I mean, if graphene was a superhero, you know, it was a person, it'd be a superhero. But we're still finding new properties. So, for example, in the last 6 or 9 months, people have discovered that it's the world's most fatigue-resistant material. So you can poke it millions and billions of times and it won't break. And it's the world's most impermeable material. So if you made pipes out of it or cartons out of it, you could keep helium in it. Helium wouldn't go through the barrier. A single layer of graphene, a sheet of graphene, is as impermeable as a kilometre of glass. So it's astonishing material. It's a proper superhero. Next, please, Adrian. So this is on the left is the National Graphene Institute. That is where the Nobel Prize winners are based. It caught the attention of lots of important people, and China's been mentioned a few times today already. In 2015, President Xi Jinping of China visited the National Graphene Institute, and since 2015, the research in China has ramped up big time, and that's only the stuff that we know about. And I'm sure there's a lot going on in China that we don't know about. And if we don't sort of really get on the case of developing graphene applications, then I really do believe China is going to, if it hasn't overtaken us already, it will do pretty soon. Next, please, Adrian. So what does graphene look like? It comes in sort of two sort of forms. On the left, we've got graphene powders. Most commercial applications at the moment are based around graphene powders, and I'll give you some examples in a short while. Graphene powders are available commercially. They're available by the ton. There are lots of companies around the world manufacturing graphene powders in a whole variety of ways. On the right, you've got a photograph of a single layer film of graphene on copper foil. If you look to the left of that picture, you can see Adrian's highlighting a sort of line. That's the boundary between the copper foil on the left and the slightly shinier film of graphene. So what you're looking at there is actually a 1 atom thick layer of graphene on a piece of copper foil, which is pretty cool if you think about it, being able to see 1 atom thick. Well, I think it's really cool, but I'm biased perhaps. Okay, so what do we do with graphene? Graphene powders, can you flip to the next slide, please? If there was one thing that graphene could do tomorrow, this would be it. I just think this is truly amazing. If you put tiny amounts of graphene oxide into concrete and cement, you can increase the compressive strength by at least 25%, which means that if tomorrow everybody started using graphene enhanced concrete, and we know that concrete is probably the second largest sort of creator of carbon dioxide in the world, we could probably knock about 2% off CO2 emissions tomorrow if everybody started using graphene in their concrete. Now that is an amazing thought. People are starting to use graphene in concrete. Here's an example in Cancun. It's the Yucatan Convention Center. They've used enhanced concrete initially on a parking lot, and against the sea wall, and they found it so effective they actually built the whole convention centre out of graphene enhanced concrete. Interestingly, okay, it makes concrete stronger, but it also has a number of properties like rebars inside the concrete won't rust as quickly. Hence, that's why they put it on the seawall to test it. There are some experiments or research going on in the UK with using concrete in the field, and they're finding it's more waterproof. It's just amazing. And if there's one application for graphene powders, this is it. But anyway, away from Earth. Next, Adrian. Here's another example of use of graphene powders. Northwestern University have been exploring printing 3D or using regolith to 3D print graphene enhanced regolith. And basically you can make building blocks out of it. So if, for example, you're on the moon, you've got tons of regolith. If you're on Mars, you've got your regolith. Enhance it with graphene, use stuff like polylactic acid, polyglycolic acid, which is in compost and human urine, which will be there anyway if you're on the moon. You can actually make some really good building blocks. So effectively, you've got the material to build stuff on the moon, build stuff on Mars. And it's strong. It's like concrete. It increases the tensile strength. So that's just a brilliant application. Next, please, Adrian. Well, I would say this is a good one as well because I'm a Brit. But this is a rocket. It's going to launch next year. It's a private, low-cost orbital company, Orbex, and the Orbex rocket will carry 150 grams of payload into space. It is primarily built with a 3D printed engine and a carbon fiber and graphene enhanced body, which makes it lighter, improves the strength, and lightweighting is what works. It's cheaper to fire it into space. Next, please, Adrian. So that's a British example. Here's a US example. Ford cars. The Mustang F-180 in 2019 started to use graphene enhanced components under the hood in the foams and the insulation that's under the hood. They were expecting an improvement in mechanical properties, and yeah, they got it, 20% improvement in mechanical properties. They were expecting improvement in heat endurance, and yep, they got that, 30% improvement in heat endurance in the foams and things. What they didn't expect was an improvement in noise reduction. So you get a performance enhancement in terms of noise, 17% reduction in noise, completely unexpected, but amazing. And particularly at this time, if we're using our cars more as mobile offices, since we can't go to the office, or the old office that we used to go to, things like noise reduction is actually a real benefit in your cars. Since then, they've been putting it into seat foams and a whole bunch of other stuff. And we believe that last year, over 5 million graphene enhanced automobiles were manufactured in the US. So pretty much every Ford car that comes off the production line now has graphene in it. So that's a bit of a romp through what some of the amazing properties and applications of graphene and graphene powders. But Adrian's going to tell you the really clever stuff now about graphene films. Adrian.
Thanks very much, Rushton. Now, as an audience, you might be listening thinking, what's all this got to do with space elevators and space? And why have we taken you through graphene powders? when the really interesting stuff is in film. The reason is that it's because there is this duality in graphene at the minute. So if you're coming to the technology from the outside, you'll just hear the same word graphene, but it could mean the powder or it could mean the graphene sheet in the film. And this whole field is moving so fast that those two are being confused. So what Rob's done there is given you, hopefully, a very good understanding of the basics and taken you through some of the applications of the powders. And that is literally a tip of the iceberg. We could have gone on 10 times longer and picked whole different things. Now I'm going to focus on this graphene sheet in the film. Now, coming back to this copper foil that you can see here, this is an actual sample, picture I took at the Geek a couple of years ago. And the company that made this covered the graphene foil with covered the copper foil with graphene. As Rob's already told you, you can see down the left-hand side the bare copper, and then you're actually seeing a one-atom thin film of graphene covering the rest of the foil. Just think about that. What you're looking at here, as well as just the technical achievement of just actually being able to see one atom thin of a material, this was considered impossible before 2004. And that's a staggering achievement that we've got industrial processes that can make this stuff already here in 2021, when at the time that Brad Edwards' report on space elevator tethers had concluded carbon nanotubes were the key thing, but the problem is nobody could make the carbon nanotubes long enough. Just 1 year later, in 2004, graphene was isolated. It's interesting just thinking about the context there. So, coming back to the space elevator. Now, we're all fairly familiar with the space elevator, but it does bear just going over the basics very briefly for people who might be watching this on video later. That there are various components. The space elevator is a very big structure. We've got the surface of the Earth, and then we have an Earth port, which Fitz has been describing very capably, and then we have a geostationary node and an apex anchor. And then connecting all these is a stationary piece of material that goes all the way from the surface of the Earth right out to the apex anchor. And that's 100,000 kilometers long. And that piece of material is what the climber grabs hold of and then pulls itself up and down. And you can see the scale of this. This is the biggest engineering project of mankind. But, you know, hey ho, we all like big stuff. Now, that whole project was looked at by Brad Edwards and the team after NASA arguably probably came up with the first realistic proposal for the space elevator with Jerome back in the 70s. And then at the turn of the century, NASA's Institute for Advanced Concepts looked at this technology and said, look, is it really doable, or is it science fiction? And the report that came back, which reported in 2003, basically said, yes, everything is doable with today's technology, apart from one thing, which is the material you make the tether out of. And at the time, there are candidate materials, but nothing that could be made long enough. And therefore, the project has been stalled for the past decade or so. And it's sort of been tucked away in a cupboard. Now we're coming out into the open again because materials technology has moved on. As Pete Swan said, stuff is happening now and happening really quickly, and I'll take you through what's been going on. So, just coming back to look at graphene, as I said before in the introduction, we're not just focusing on graphene, we are looking at other materials, carbon nanotubes, other types of 2D material as well, but for our purposes, let's just focus on graphene for the moment in the time that we have. Graphene has a tensile strength of 130 gigapascals. It's also incredibly light, as Rob said. Just think about this, 1 square meter of the stuff would weigh 0.77 milligrams. Now, you put those two things into context, what the Nobel Prize winners did, they articulated this by saying, if you made a 1 square meter hammock out of graphene and you got 4 people holding it at the corners, you could take a 4 kilogram cat and put it on the center of the 1 atom thin hammock, and it would be strong enough to hold that cat. And yet the material itself would weigh less than one of the cat's whiskers. That's sort of giving you a rough idea about how strong and light this material is. And those two properties are exactly what we need to be for a tether candidate material. And I've been working with ISEC for the last few years, presenting with these guys. They've been sort of stress testing the science behind what we've been coming up with. and it's passing all the tests. So there's no doubt that graphene can be a candidate tether material. The question now is, can graphene be made at the industrial scales needed? And interestingly, when I first started engaging with ISEC, we didn't know that it could be produced industrially. We guessed it could be, but nobody had actually done it. Since then, a lot of work's gone on with what's called the chemical vapor deposition method. So this is how that graphene sheet film, if you like, that you saw on that piece of copper was made. So we start off with a blank piece of copper foil, or there are other metals that do this, but we'll stick with copper for the moment. And you take methane, I think you guys pronounce it methane gas, natural gas, CH4. So you have a carbon atom in the middle and then 4 hydrogen atoms attached to it. Get that very hot up to about 1,000 degrees. What happens is a series of complicated reactions, but in essence, the hydrogen pulls off and the carbon lands on the surface of the metal, where the metal acts as a catalyst, or if you like, a dating agency for the carbon atoms, and they land on the surface and then connect up. Now they connect up in the lowest energy shape that they can, which turns out to be this hexagonal chicken wire that Rob showed you, that hexagonal mesh of carbon atoms connected together that is graphene. And then when the surface of the graphene's, the copper's covered, then the reaction halts, and then that means you can peel off the graphene from the metal surface, and you're left with this 1 atom thin layer of graphene sheet. That's how it's made. They're the principles, and that's called chemical vapor deposition. You might hear the term CVD. That's how the film is made. Now, there are different types. You've already heard the term single crystal graphene being mentioned already. So just to give you an understanding of what that language actually means, on the right-hand side, single crystal graphene means this perfect repeating pattern, this hexagonal molecular pattern of graphene, perfectly repeated with no holes or gaps. What we're actually finding at the moment, the industrial process of making what's called polycrystalline graphene, there's a variety of reasons for this being made at the moment. But you can see where I've highlighted the bonds in red, and you can see there are sort of 5, 6, 8 membered rings, and then there'll be holes as well, vacancies we call them. This polycrystalline graphene is nearly as strong as single crystal graphene, but these defects do weaken it significantly. So it's good enough for a variety of processes at the minute. This is where the state of the art is on the left, but we're moving very rapidly towards industrial processes being able to make single crystal graphene already. So what do I mean by a crystal? Not what you'd expect. So when I say the word crystal, I'm using this in the term a physicist would mean a crystal. Crystal to you might conjure up an image of a diamond in your hand, or a quartz crystal, something that's very hard but very brittle and would shatter if you threw it on the floor. But in this context, crystal means a repeating atomic pattern, and it could be, in terms of graphene, it would actually be something which is flexible and stretchy, a bit like plastic film you use for food wrap. I think you guys call it saran wrap in the States. We call it cling film in the UK. So that's a good analogy. The picture here isn't graphene, by the way. This is plastic wrap, just to be crystal clear. So the thing is, only single crystal graphene can realize this tremendous strength of this advanced material. So we're not only after making 1 atom thin layer of graphene, we're actually trying to make 1 atom thin layer of graphene, which is perfect at this single crystal scale. But not only that, we need to make it at a macro scale, which means making it not only at square centimeters, meters, but also kilometers, hundreds of kilometers, thousands of kilometers, hundreds of thousands of kilometers big. And that is a single molecule. Is it even possible to do that? Well, it turns out, yes. And Rob's alluded to the Chinese, and a few other presenters already have mentioned China. Single crystal graphene was first made in China, and they called it single crystal graphene, which is why we're using the term. The way that they did it was they annealed a piece of copper foil to get all the crystal boundaries out of the metal in the first place. So you start off with a single crystal of copper, and then on top of that, they then grew domains of graphene. Now you can see here on the left-hand side of this bottom shape, On the copper, the Chinese started off by making hexagonal domains, individual seed crystals, if you like, of graphene. And then they got them to grow and grow and grow and aligned them in a way so that when they grew and butted up against one another, they seamlessly connected and stitched together to form this single crystal. Hopefully that gives you an idea about how they did it. Interestingly, around the same time, just about a year later, Oak Ridge National Laboratory did the same thing, or something very similar. But the Chinese got there first. And Peking University in Beijing have made a single crystal of graphene. This is a single molecule, which is 50 mil by 500 mil. So half a yard long, 2 inches wide, that sort of scale. And that's a single molecule. And it's worthwhile just stopping and thinking about that. These are some of the biggest molecules ever grown. So is it possible to make sheet graphene at industrial speeds? We already know now that it's possible to make single crystal graphene. And we know from that test that's been done already, but in Peking and Oak Ridge, that it's possible to make the single crystals. So we now know we can scale up and scale up and scale up. The rest is process optimization to make the bigger size of single crystal. But we've got to make it at industrial speeds. Graphene is only 17 years old. Is it even possible to think about an industrial process? And it turns out the answer is yes. There are processes going on in Europe, Asia, and America already that are targeted at making industrial scales of graphene. At the moment, the state of the art, or the state of the industry, as Fitz quite cleverly nuanced, is to make polycrystalline graphene. So if you remember that stuff I told you with the red lines in it, so it's not perfect graphene at the minute, but hey, we've only been going for 17 years. Let me show you some of the machines that can make this. So Rob actually took this photograph, and this is in the basement of the GEIC, the Graphene Engineering Innovation Centre in Manchester, that building you saw earlier where we work. And this is in what's called the CVD lab. What you're looking at there is a Graphene Flagship supported project. Now, the Graphene Flagship is a €1 billion project that's been set up in Europe to fund research into graphene. And this machine here is made by a company called Extron. They're in Germany. There are only 2 of these machines in the world, and we've seen one of them, and this is the Neutron. It's a roll-to-roll process, so it makes graphene. Can you see at the top inside this machine here, where the front cover's been opened for us? You can see the top reel of graphene, of copper foil here, and it goes down through this tube furnace, which takes the temperature up to 1,000 degrees C, carefully introduces the gases that needed, and then at the bottom it reels up underneath here with graphene coating the copper foil. And we don't know what the speed is, because that's a trade secret, but they have the manufacturers have told us that this has got the capability to make 20,000 square meters of graphene a year already. Thing is, now the company here has yet to develop a separation process to get the graphene off the copper foil, but there are lots of researchers working on that in Europe already. Over to America, General Graphene in Knoxville, Tennessee. Fitzer was saying in his presentation that we've been talking to all sorts of different companies. Well, this is one of them, and General Graphene provided these images for us. What they've developed is a horizontal roll-to-roll process, industrial process. So this, they have a long machine here with a horizontal furnace here where the copper foil enters the furnace, the gases are introduced, the temperature gradients are controlled, the crystal growth is controlled, and then it's reeled up at the other end. Now, the clever thing that General Graphene have done is, as well as creating graphene on the surface of the copper foil, they've actually developed a transfer process. So they can now take the copper foil from this machine here, and they've now got a continuous process where they can then take polyethylene terephthalate, plastic film. This is plastic that your plastic bottles are made out of, water bottles and soda bottles. Flexible plastic comes down in contact with the graphene layer on the metal foil, and using a trade secret process, they've got the graphene to come off the copper onto the plastic. The copper is then recycled and reused again. Already the company have told us that they can make up to 100,000 square meters per year. It's important to say here, they're not targeting space elevated tether, They're targeting the electronics industry at the moment because they're making polycrystalline graphene. However, ISEC have met with General Graphene. We've had conversations with them already. We know that they can make single crystal graphene domains already up to 300 millimeters square. And the conversations that we've had with them so far say there is no limit to the size of the single crystal graphene domain they can make. So they can make these big molecules, they can make them fast. And if they get the resources to develop the process further for other markets. At the moment, they're focused on making graphene for electronics. But interestingly, we also talked with the lead scientist, and the guy that developed this process, he actually came from Oak Ridge National Laboratory. So this was a secret process that spun out from Oak Ridge and only came out into the open in the summer of 2020. So it's only a few months that this has actually been public knowledge. Interestingly, the head scientist who invented all this is actually a space elevator enthusiast as well. So we have somebody on our side. What's it look like? This is General Graphene's picture. So we can see here that the important thing I want you to focus on here are these 4 samples in this picture here. On this side here, this is just a polyethylene terephthalate plastic with nothing on it. Then we've got 1 atomic layer of graphene on the surface. Then we've got 5 atomic layers of graphene and then 10 atomic layers. They've already developed the process to take graphene off from the forming substrate and then layer it up in increasing layers. And that is one of the key production steps that we're going to really have to pay attention to in making a space elevator tether. Because as you probably gathered already, the space elevator tether is not made of just a single piece of graphene, a single atomic layer. It's lots and lots and lots, tens of thousands of single atomic layers all stuck together, going vertically up into the sky in a ribbon. So that's where the process is going. So what I want you to take away from this is, in the States already, you've got industrial scale manufacture of graphene. Just 17 years ago, this was impossible. These guys are not only making it, they can also make very large single crystals of graphene. They can also transfer the graphene from the copper foil onto other substrates too. So the trajectory for this, I'm sure you can actually see it's not far off, giving us a really solid foundation for manufacturing graphene tether. But we're not there yet. That's important to know. We don't go away from this saying tether can be made tomorrow. That's not right. There's still more development work that needs to be done. Can we make it fast? Well, again, this is another secret project that came out into the open last year that we found out about. And the key thing I want you to see here is the speed highlighted in this red circle here. The Koreans have already developed a vertical roll-to-roll process, very similar to the Extron machine. You get an idea of the scale there with that man holding the copper foil. They can make graphene at 60 meters per hour, which is a meter per minute already. And this is really important because what we know from talking to some of the leading scientists in the world, one of the questions we've asked is there an actual fundamental speed limit for making graphene? Because the length of the tether is such that we're going to have incredibly fast manufacturing speeds. Meters per second is probably the area that we're going to be in, and probably a bit faster. And we needed to know, is there actually a fundamental speed limit to which you can make graphene? And it turns out the answer is no. You're not limited by the atoms coming together. There are other mechanical limitations that would come in. And what the Koreans are showing us here is they've already got the speed up to a meter per minute and making high quality graphene there. So we know that we should be able to move and optimize this process to go faster and faster and faster. Really impressive stuff. And a lot of this has been going on in secret. So we've gone from impossible to industrial in just 17 years. 2004, a year after Brad Edwards' report, second issue came out. Then before that, graphene and 2D materials were thought to be impossible. Then the Nobel Prize is awarded. That triggered a technology hype phase. People dived in, and then they suddenly found, oh gosh, we just got graphene black powders. They added them into things, it made it worse. Lots of investors lost their shirts. You'll probably talk to people who say graphene's overhyped. That comes from that 2010 and probably through to about 2014, 2015 phase. We're through all that now. As you've seen from Rob's presentation, we actually know how to deal with powders. They're making fantastic additions to all sorts of industrial scale stuff. 5 million Ford cars out there already. The pace with which graphene is progressing, the manufacture of the sheet graphene and single crystal graphene is moving faster than anybody ever expects. We're monitoring this on a monthly basis, probably actually a daily basis. And every single month that we produce an issue of the journal, we get surprised at the rate of development that's taken place. So what I want you to take away from this is sheet graphene, single crystal graphene, these are important terms. It's separate from the powders, and the single crystal sheet graphene is the material we're focused on for the space elevator tether. This ain't science fiction anymore, guys. This is industrial reality, and the trajectory this is on is moving so fast that we can almost guarantee that the industrial capability to make space elevator tether will happen at some point in the future. Just a question now, resource, time, effort being put in to optimize these processes. So that's us. That's our questions. Hopefully that's been of interest. I'll stop sharing the screen and we'll take you back and we'll see if we can take some questions. Was there anything else I missed, Rob?
No, I don't think so. I
What do you reckon,
noticed that
guys?
Dennis asked a question about powders and phones in the cars. How does it reduce the noise? And it's to do with the size of the holes or bubbles in the phones.
Yeah, Dennis, it's polyurethane foams, and when there are bubbles that form in the foam as a result of the manufacturing process, and what the graphene powder seems to do, it makes lots of smaller bubbles which attenuate the sound. And as Rob said in his presentation, that came as a surprise. Nobody expected that.
Great. Sounds great.
This is Vern. Adrian and Rob, every time I hear your presentation, I learn something. It's fabulous what you guys are doing. I maybe learned that my new SUV has graphene in it. Who knows?
Yeah, you've got graphene in it.
It is a Ford product.
Yeah.
But I do see, serious comment, I think if we focus on the elements of the space elevator beyond the tether, the climber itself, the containers that will be released at GEO, and elements like that, you can see quite a bit of applications for graphene powders, even to make them stronger, lighter, etc. We make the climber lighter. The implication, of course, is the payload can be bigger. So it's tremendous future there.
Yeah, and Rob, you pointed out the Orbex rocket body. That was
Orbex rocket.
Yeah, that's what got me thinking exactly.
Yeah, and Vern, this is one of the things about working in this field. We're right at the edge of what's possible, and it's not just us not just you that would learn from this. We're learning all the time as well, and because graphene is a multifunctional material, as Rob showed you, world's best conductor of electricity and heat.
Oh, unbelievable!
Impermeable. You name it. You can think about applications that we haven't even dreamt up yet.
Well, the concrete example with the being electrically conductive, you could design a building that could monitor itself.
Yeah, and as
build the sensors into the fabric of the building, so it just tells you when it's going to fall down, I suppose.
And as Fitzer was saying as well, we're going to need testing, we're going to need sensors, we're going to need data sources and information about status that we can't even dream up yet. But actually, this material is probably capable of being created to build things in. We're already getting things like radio frequency antennas being made from graphene. And actually, graphene is now moving into the terahertz region of the spectrum. So it can actually emit terahertz, it can actually detect it. So we could find that graphene underlies the next generation of terahertz telescopes, perhaps.
Well, just thinking of the antennas that will be involved in the operations at GEO with the flying robots, the climbers themselves will have, if you can eliminate the weight and the bulk of those, and it's a tremendous application there also.
Yeah, and Michael, when we were practicing this, you showed me your jar of carbon nanotubes. it might be that the lessons we're learning from manufacturing 2D materials might translate over to manufacturing carbon nanotubes. And the moment carbon nanotubes can't be manufactured in any, the longest I've seen is 500 mil, but really when they're talking about ultra long nanotubes, they're still talking about millimeters.
Yeah.
So this could unlock processes that we don't even know about yet.
When you were showing those pictures, I took my glasses off and got in really close to look at the pictures, and then I went to General Graphene to look at their stuff. Their machine is pretty interesting compared to what we were doing. We were doing a CDV version also, but as Pete said, it's about time to throw those out, because what we created, almost 15, almost 20 years ago, it's junk. I mean, it was junk then, and it's definitely not even in the ballpark now. So I was wondering exactly what you just mentioned. Are there ways to use the new techniques and kind of reverse engineer and figure out what we were doing wrong?
Yeah. And don't beat yourself up about making junk. You've got to fail a lot, as Spitzer said as well. This is tolerating failure to learn. We're standing on your shoulders and the work that's gone before.
You're standing on a lot smarter than my shoulders. Let's be really clear. Like we stopped for a very good reason. There were way more people smarter at this than we were. But thank you. I appreciate it.
Yeah. Pete, do you want to say anything, or Fitzer, do you want to say anything about General Graphene in this forum?
Well, Fitzer would be the one to say it. I don't know if he's got a connection through Michael now. But the real kicker is we have efforts across the globe to work with whomever has good technology and materials and stuff like that. And we had a meeting with General Graphene with many of our board of director members, and Adrian was there, and Rob, I'm not sure whether you were there. I think you were, but anyway, it was a good meeting talking about where they were and where they were going. And I'll tell you what I gained from it was there was a really, really smart lady who came from Oak Ridge and joined the company. And this is an extremely important point I want to keep making to everybody. She left the research organization in the government to go into industry because she believed in the material, and she believes she can make magic material like a space elevator tether. She's there trying to figure out how it's accomplished. You don't get products like that in government research organizations. You get them in private industry where they make their money and have a good career. So the discussion with General Graphene was marvelous and really encouraged me that the tether for the space elevator will be ready before the pundits think it will be. And it's like so many other technologies, the uses out there are monumental. And when the uses start demanding the material will develop faster. One point I wanted to make, Adrian, is we at ISIC and Adrian in Manchester have been working with the British Interplanetary Society. And we wanted to have a one-day society meeting that would be this magic material with space. Now, we didn't call it that, of course. But one day would be space structures and space. The morning or the afternoon would be space structures and stuff like that. And I have an experience in the R&D arena where I asked some people building futuristic satellites, what would they do if their spacecraft weighed 1/4 of what it is today? And it's remarkable what they can do if they can, have 3/4 of the mass thrown away. And so the application of these materials, as simple as holding hydrogen in a tank, can really, really make a difference. And then the battery mass, holy Toledo, the battery mass, things like that. So we wanted to have a one-day British Interplanetary Society meeting, and the morning would be the materials with spacecraft and stuff like that, and then the afternoon would be, voila, a space elevator needs a tether. And we were well along the way. We had set a date and everything else, and then the coronavirus came along. So We probably will have something in the next 9 months or a year. We've got to get into the schedule. Those guys are really busy. They have a lot going on.
Hey Pete, just a couple days ago, one of my professors, Dr. Chris Welch, just 2 days ago became the new president of the British Interplanetary Society, and he's a big space elevator fan, going all the way back to Clark. He knew Clark. He's British. He knew Clark.
Yeah, I know him. And I've been a fellow of the BIS, and I don't get too impressed because I was a foreigner, and all I needed to do was send money and say I was in a PhD program, and they said, "Oh, you got to be a fellow." And so anyway, so I got to be a fellow, and I have really, truly enjoyed the professional relationship with the BIS because it's a remarkable organization. In fact, I mean, just a little aside, I think ISIC is set up as a model based around the British Interplanetary Society. We're like a small little parallel organization. But anyway, it's remarkable activities. So I think, Adrian and Rob's presentation shows that there is great hope on the material being ready when our mega project is ready for that material. They're both going to take 10, 12 years, but we should be able to beat the 2035 goal of the Foundation for the Future. So, we should be right in there with that activity.
Yeah. Fitzer, did you want to add anything about General Graphene? Because I know you've been talking with them. You're still trying to connect through. Rob, there was another question here from Inara in the side panel.
Where is it?
Is anyone working on graphene cables for use on Earth infrastructure?
Graphene cables.
So we've been talking about this quite a bit, actually. You could make bridges out of this, suspension bridges. You can make suspension bridge cables out of layered graphene. But also there's one bunch of people that have sort of brushed up against us on the in our network, and they're looking at using these flying windmills, Rob? They're like a tethered aircraft.
Yeah.
And the propellers whiz around, but then they generate electricity. But the problem is they've got a problem because they can't get an electrically conductive cable that's light enough and strong enough to connect the ground.
Oh.
Rob, if you're talking, you got to hit mute. Sorry.
No, someone just moved. Someone just removed Adrian from the meeting. That's not very good. Bring him back.
Help.
Somebody else we've been working with, one of the if you could lay, if you've got your sort of data cables and things like that, if you can lay strips of or any other cables, a trail of graphene, you've got a cable that can go underground and then basically tell you when it's broken. One of the problems that people have with the cables that break underground is where is it broken? So you might have to dig up, yards and yards and yards of pavement, sidewalks or roads to find out where the cable is broken. Whereas if you put the sensor along the cable, it can tell you almost exactly where it's broken. And we've been talking with utility companies, water company in the UK, around their pipes. A lot of the pipe work in the UK is old, and so what they do is they put in a plastic sort of inner, they're old metal pipes, and they put a plastic inner in. But if that breaks, the leak can turn up a mile from where it's actually broken. So if you can build sensors into your piping, you know exactly where this sort of, where it's broken. Brilliant.
Yeah, Rob, I can understand when the pipes are 500 years old that you need a little bit of help.
Yeah.
We don't have anything 500 years old in the U.S.
Yeah. Yeah, but just the idea of building these sensors into things, you know, the idea of remote sensing in a building, is just pretty cool.
Yeah, and thankfully, my cable wasn't broken, so I'm back.
Adrian, this is Spitzer. I finally was able to get back in. Yes, you know, it's amazing, Michael. Like I said, enough turmoil to make it memorable, and it's almost as tough as being thrown down the elevator shaft by the undersecretary. So, General Graphene has something that we all on this phone call should learn, is that when a reasonably well underwritten company, okay, has put together a formula and a plan, they can make amazing products or projects or progress or all of those things. And that's what we're seeing with General Graphene. So when I introduced Tim to General Graphene 3 or 4 months ago, the first thing Tim did was said, I need to see some samples, you know what I mean? And we turned that around in, 7 or 8 weeks over Christmas holidays. The notion that we have a single molecular layer of, and I have to say arguably, single crystal graphene being made may actually set aside the progress that the Peking University progress was all about 4 years ago, because the samples, at least arguably, came from the CVD production line that General Graphene is putting together. Now, it was sort of handheld. It was, you know, hand carried down the line, as it were, and whatnot. But I expect, frankly, the same kind of progress in the other engineering shortcomings that we're dealing with. And what is engineering shortcomings? Engineering shortcomings means that we need to test things and figure out the difference between success and where we're at. And General Graphene has demonstrated that to all of us here. And they have been very open with their progress. Okay, Pete, I'll surrender my phone again.
Now that you're in, make sure you stick in, because you're going to run the panel in a little while.
Okay, I'll run the panel in the blind as long as somebody can put the charts up. Yes, sir.
Yeah, we can handle that. Okay. Any more questions for Adrian and Rob? It's getting a little late back there, so we want to, you know,
it's dark
pat 'em on the back. Yeah.
Yeah, I actually had a question for your Adrian and Rob here. Kind of in the previous panel that was outside of this, you guys spoke about graphene, and it's kind of amazing the amount of progress, as you said, just even from a couple months ago when you gave a similar presentation. And you were talking about how there was a limited focus in the United States on manufacturing even polycrystal graphene, as opposed to the benefits of the powder, just for its utility alone. How do you foresee, you know, building up the requisite scale, like the demand for this kind of product at the kind of scales we're talking about? Because correct me if I'm wrong, but the space elevator, you know, we talk about it being 100,000 kilometers in length, but we don't need just 100,000 kilometer strand. We need perhaps hundreds, if not thousands, of layers of 100,000 kilometer single crystal graphene sheets, and like that becomes an industrial scale, which is not going to function if the space elevator is the sole customer. So what do you foresee as sort of the additional customers? Just like we've discussed briefly, like measuring pipelines, but how do you see a greater, shall we say, you know, thousands of kilometers scale demand that pushes this market moving forward?
Rob, do you want to start off and I'll take over?
Well, at the moment, it's still very much it's about the markets to start with. It's still very much a producer-led market. So people are making stuff and then trying to find a use for it. And so it's a push. We're pushing powders out. We're pushing, you know, General Graphene. We're pushing out, polycrystalline graphene sheets and things like that. Something has got to flip so it becomes a market pull. You're beginning to see that with the powders. So if Ford are putting it in all their cars, there's a pull. So if there's a pull from the market, somebody's going to dive in and say, right, we can meet that demand. For the powders, there are lots of new ways that people are coming up with to manufacture graphene powders. James Tour at Rice has got his flash graphene. Was it graphene CR? Used biochar to make graphene. So basically, you're making graphene out of trash, out of vegetation. But with the Fords and potentially with concrete, there's going to become a market pull. For the sheet graphenes, we're still very much in that early days where we're pushing stuff out, and trying to work out, what can we do with it? Okay, we can make sensors with it. We haven't got the quantities to make elevator cables, even for, your skyscraper. But that might be the next sort of stage.
Yeah.
I'm
Yeah. Sorry, I thought you were finished. We do have some additional questions in the chat for when you're finished.
Okay. And then there's the getting the volume. You're only going to get the volume when there's a market pull.
So yeah, if I can just take over from Rob, I know Michael, you wanted to ask a question too. Oh, okay. So specific market pull for sheet graphene at the minute, because it can be made in small quantities. And for electronics markets, we're already seeing things like Hall sensors being made, and these are particularly they're so good. These are little sensors that detect magnetic fields, and 2D materials are brilliant at detecting these, because you can hold one of these sensors and rotate it in the magnetic field, or the magnetic field can rotate relative to it, and it doesn't get affected because it's a two-dimensional structure, whereas normal sensors, they have the third dimension, and the magnetic field warps where the electrons move in it. So these new graphene sensors are already beating the calibration equipment that's being used to test sensors. It's now being, there's a company called Cardia in California, not far from Fitzer and Verne. They're using CVD graphene to make sensors that can detect COVID. And so you've got now a lab on a chip where you get an instant electronic readout that tells you if you've got COVID, what stage you're at, have you had it, or are you about to get sick? So they're on the market pretty much already about now. As we start to scale up and get larger quantities, the stuff on mobile phones here, cell phones, when you drop this, it breaks. And the reason it breaks is because the material on the screen, you can already make flexible displays, but you can't make the touch screen bit flexible. That's something called indium tin oxide, which is transparent and electrically conductive. And if you remember back to Rob's presentation at the beginning, you might remember that graphene is transparent and electrically conductive. And although it's not cheaper than indium tin oxide, it can do something ITO can't, which is you make a mobile phone screen with graphene on it, you can roll your phone up, or you can drop it and it won't break. And flexible touch screens are a $98 billion market just by itself, Kevin. So these things are starting to kick out. In fact, where you're going, Kevin, with your question was, what markets are there now which will provide economic returns so that we can build up to make a space elevator tether? It's not that the markets don't exist, although there's some market education to do. It's one of the things as we project forward is these markets are so lucrative and so demanding that they might distract us from making a tether in the first place. And then they'll scale up and scale up and scale up. One other thing, just very quickly, you can layer graphene up, thousands of layers, and you'll make something that's as thin as saran wrap, and that would stop a bullet. And as Fitz is quite keen to point out, very lightweight and very strong materials are what are required for an awful lot of aerospace applications, defense applications, things like that. So you can imagine, that you could have bulletproof armor which weighs next to nothing. somebody Rob and I know is he's an ex-Navy SEAL, and he knows just how valuable it is to have very, very lightweight stuff, because the special forces often drop their armor plating just for lightweight movement about. So does that sort of begin to answer your question, Kevin, about where the economic returns are and where the trajectory could be?
Can I put it in a little perspective on infrastructure? It turns out that this whole push that the Foundation for the Freedom or for the Future is going with is space infrastructure. But in America, and I'm sure it's true in the rest of the world, infrastructures are falling apart. I mean, it's about 50, 75 years after World War II. I've got to subtract here, 75. And we put in a lot of infrastructure in the 50s. And that infrastructure, bridges, buildings, everything else, is starting to wear significantly. And my vision of polycrystalline is you make sheets of that, wrap it around a cable on the Golden Gate Bridge, and you've extended that cable life by, pick a number, 50 years. And if we could get infrastructure demanding sheet graphene, we're talking about a tremendous need that would drive, it would be a demand pull, but it would be extremely important to the nation's health, globally. If we make sure that bridges don't fall down and infrastructure is working and the power cables are working and all that kind of stuff, which is, part of the Congress's push to have some infrastructure money invested. I think that's an area that has not been approached very much with the new materials.
I agree with you, Pete. Rob, do you want to say something briefly about, sorry, Michael, do you want to say something briefly about graphene asphalt?
Yeah, in the UK and in Italy, they've been putting graphene into asphalt. So in Italy, they've done tests on a stretch of road near Rome, and more recently at Fiumicino Airport, they've put graphene in one of the taxiways. In the UK, they've been testing it out on some of the highways. And basically, if you put graphene into asphalt, it improves the strength and temperature sort of range that you can cope with. It decreases rutting, so you don't get the sort of grooves in the roads as they get used.
It basically doubles the service life of the road.
Yeah. I mean, again, it's small quantities, and it's things like that. Once you start getting it into construction, into roads, into concrete, into buildings, that's when the real market starts to grow.
All right.
We're talking about cables, elevator cables. You could build a building as tall as you ever want.
We better let Lee get
we are actually out of time for this segment. Perhaps we could revisit another day. There are additional questions popping up on all our different platforms, so a lot of interest in this topic, but I don't want to cut Dr. Swan short. So the next presentation will be on dual space access architecture, combining advanced rockets and space elevators. And once again, please welcome author, professor, veteran, and president of the International Space Elevator Consortium, Dr. Pete Swan.
As soon as my slides come up, yeah, that'd be good. Okay, it's working here, I hope. One of the things I'd like to do is thank the Foundation for the Future and all the people that have been involved in that, because it turns out that your objective, your mission, is really quite important to many, many people, including us. For some reason, this little guy is not working too well here. Let's try it again. Share screen. There we go. Oh, I just have to put the button in the right place. Can you imagine that? Radical. Okay, let's see. Here we go. Now I hit this over here and hit that. Okay, I think we're ready. What I really want to do is kind of congratulate all the previous speakers, because they came up with some really, really significant points. And that's where we're going. We have a group of dedicated professionals that are charging off in different directions. And, you know, the role of the ISAC is to just make sure that they're somewhat in parallel. So we're out there having great successes individually. But the real kicker in this whole day is most of us have said that space elevators are essential. Now, we all know what essential means now in today's world. You know, the new normal is different than the past. And essential workers is really a praise out there. What we want to say is that space elevators really, really need to be done if we want to really move into our dreams that so many people are expressing. So our mission is to move massive cargo in a green manner to GEO and beyond. And as we discussed earlier, the price of travel is not the issue, it's the economic development that would occur when we get out there. And I'm a true convert to Kevin's whole philosophy. I think there's really a lot to be said for that. So the strategic approach we need to take is, how do we go from where we are to an operational space elevator? And the way we do it is we join rockets. We encourage rockets. The advanced rocket people are doing marvelous jobs. They're providing systems that will fulfill our needs, such as low Earth orbiting constellation of satellites, and doing weather satellites, and doing all that kind of stuff that's been traditional. What we want to do is join that road to space and provide another capability, but basically to provide mass to GEO and beyond. And if you remember on previous charts, I said 22,000 tons was what we've put into Earth orbit since 1957. We want to propose a lot more than that. We want to be an aggressive teammate of rockets. I just put this in there to make sure everybody remembered where we were. But the first step is we want to have an evolutionary approach for humanity moving off planet. But the strategy is dual space access architecture. A lot of this is in our book that we put on the website. So, if you check that out, you'll be in pretty good shape. In addition, we were talking earlier in Fitzer's discussion about the categorization of the technologies. Where were we? What was the success in different areas? These two books really hit that pretty hard. And they do use the traditional TRL level, technology readiness level, to try to combine it. And it was contributions from 40 space professionals from around the world, the Ukraine, Russia, China, places like that. So a permanent space access infrastructure, it's going to provide jobs. And that's really what we're after in the sense of future missions to space. And the real kicker is we're going to provide freight to GEO and beyond. Now, the strengths of Space Elevator, if you notice, I didn't really talk about that in the last talk. The strengths of Space Elevator are remarkable. And if you take out the equation about price and you just discuss it as a capability, you just shake your head and say, what a marvelous opportunity. How many people were looking at, San Francisco from across the bay in the early days and saying, oh, where can I get a boat? What can I do? Or take the road all the way down south and back up. Nowadays, you just hop on a high-speed train, or you get in your car and you go across the Golden Gate Bridge, and all of a sudden you're there. That's the idea. We want to change the approach. And, the characteristics of a bridge are very, very similar to what we were proposing. So the key is we want to have a combination of rockets and space elevators. But of course, you have to recognize the shortfalls of both of them. The conundrum of rockets boils down to how much delivery mass do you provide to the destination? If you want a pizza on the moon, you'd like to order it and have it come in a timely manner, but you'd also like to have it cost less than a full set of rockets. To deliver something to the surface of the moon, it takes about 99.5% of the mass to get there. Now, we argue that the first stages are reusable nowadays, and they're a lot cheaper and everything else. That's not the point. The point is you only deliver 0.5% to your destination. Whereas if you take other infrastructure approaches, you can deliver 70, 80% to your destination. So the delivery of product to the destination is the real strength of space elevators. So we're ready to really start the development program. We've talked about that before, but our strategy of the dual space access architecture is what we're going to talk about now. And we get into some details about each of the sets of strengths and weaknesses. We all have some, both strengths and weaknesses, but the promises of space elevators are so remarkable that we really need to go forward with it. Mass to orbit. We came up with these numbers over 20 years. Turns out Brad Edwards started way back in 2001 or so and came up with the number 20 metric ton tethered climbers. And we all argued with him about how much would be tethered climber and how much would be payload and everything else. Took about 2 or 3 years before we finally came up with the answer. About 6 metric tons of climber and 14 metric tons of payload. Well, let me tell you, we had that discussion again very recently. We're having a tethered climber design study. They're talking about the interface between the tethered climber and the tethered material. And you're going to hear about that from Dennis Wright in a few minutes. But the real kicker is the terminology is still being discussed. How much mass can we really move by space elevators? In addition, the Japanese corporation, the Obayashi Corporation, published in 2014 a document that said, I can design and build a space elevator. And they had a different set of criteria, starting criteria than we did. Ours was robotic only, future, we'd have people. They started with people. We need a space elevator that moves people. So with their starting point of moving people, they came up with 100 metric ton tethered climbers. Well, if you put that in the criteria to start a design, you obviously need a safety factor for humans and radiation shielding for humans, et cetera, et cetera, et cetera. So they came up with 100 metric ton climbers instead of 20. Their payload was 79 metric tons delivered to the end. And that's what they came up with back in 2014. It turns out to achieve that, they needed 2 tethers together. So their one space elevator tether actually had 2 independent tethers running parallel. And you can basically think that as a demand for safety, reliability of 2 versus 1, like airplanes having 2 or 4 engines. So the numbers of mass to geosynchronous and beyond have traditional traditional development, and they've come up with some pretty good numbers. Now I'm just going to use this as an example. You saw this earlier with David Dotson, and it's a very, very important concept. Not the numbers and everything, although they're important also, but David did a good job of expressing the need. We need space-based solar power. But I'm going to show this as a mechanism of having a dual space access architecture. Okay, let's look at that orange line. That's what we need. That's what we need. You can look at these numbers again. All this stuff will be on the web and in the video. And so we have a need on that orange line. If we launch 1,000 times a year, now that's just a random number, but basically 1,000 times a year at 20 tons to geo, and that's what a Starship can do. 20 tons to geo, that gives you that bottom line. And if you notice, it's approaching the blue line, which is minimum need in electricity. And it doesn't get there for a long time. So what we want to do is we want to use rockets has the initial capability of putting prototype satellites in low Earth orbit so Dr. Mankins and his team can test the technologies. He can work on the efficiency of solar collectors. He can work on the transition of the energy from the solar collectors to the antennas, radiating it down. He can work on thermal characteristics of the satellite, et cetera, et cetera, et cetera. We can do that in LEO, where we can actually get to it every day and work on it and all that kind of stuff. Even have humans up there assembling the major parts. Remember, these satellites are 10,000 tons. Now, the prototypes wouldn't be 10,000 tons, so you'd be working on smaller ones. But the key is working LEO. Well, rockets are great for that. So what we want to do in the solar power satellite program is use rockets to start the program. Put the prototypes up in low Earth orbit, and then even put the primary number one operational satellite up the geosynchronous. Whoops, 10,000 tons divided by 20. So how many is that? That's a bunch of launches, but we can use rockets to put the first one up. So then once you have the first one up, now you need to assemble a lot of them at geosynchronous. That's where we bring in space elevators. So it's a dual space access program. Rockets to get it started, space elevators to really fill out the demand and put the mass up there, the geosynchronous. Now remember what we're doing. We're going to have 350 satellites that are each 10,000 tons. So we have to put them up at geo, and then we have to use Fitzger's concept of assembly in the geosynchronous region where we're going to have tremendous business develop. We're going to have franchises. We're going to have all kinds of activities at GEO, one of which is assembling space solar power satellites. So you take a whole bunch of 14 metric ton payloads and you pull them over and you put them together as Lincoln logs till you get 10,000 pounds. And then you take that solar power satellite and move it in the GEO arc to where it needs to be. So it's assembly at GEO, but you're only going to get that mass to GEO in a timely manner if you use space elevators. So that's a dual access strategy, combining both rockets and space elevators, leveraging the strengths of both and putting it into a program that will implement your needs. Now, we've talked about reference missions, or I have earlier in my first talk, but if you're going to do solar power, 5 million tons to GEO, or you're going to put 500,000 tons onto the moon, or you're going to do Mr. Musk activities for 1 million tons to Mars, you really need to have a combination. Mr. Musk has claimed, I listened to him the other day, that he's going to have his starships going to Mars in the 26 time period. What's that? It's 5 years? 5 years. And he's going to have people going to Mars before 2030. Before 2030. So we're not going to be there to support him at that point. So he's going to move his people and his supplies to Mars on rockets. Then he's going to move his people and everything to Mars. And then we can come in and move the heavy stuff for him. So the idea is we use the strengths of both activities. So if we look at Mars and say, how do we get there? Today, and by the way, Mr. Musk's plan is you wait 26 months, and then you have a window, and then you launch into the minimum energy transfer, which is about 3 kilometers per second departure from the low Earth orbit. That's not true. It's 3.3 kilometers per second release from the sphere of influence of the Earth, which is way up there. And then it takes 7 to 9 months to get there. But you have to wait 26 months. So what we want to do is we want to show what the strengths of space elevators adds to the equation. The new concept, if you depart from the apex anchor at 100,000 kilometers up there, you have tremendous potential and kinetic energy. You can get to Mars in 61 days. Now that's the best. Overall, you can get there in like 400 days on the worst lineups, and the average is about 140 days or something like that. So you can get there relatively fast compared to today's world. And here's the secret. You can toss it toward Mars every day. Now, some paths are a little longer than others. It might be 400 days to get there. But what you do is you put your hammer and nails in, routine stuff on the 400-day trip, and you put your pizza and beer or whatever on your 61-day trips. So the kicker is space elevators can provide massive approaches. I'm going to just visually show this. Don't worry about the words and all that kind of stuff. This is what we did in the last 9 months. 3 missions left from Earth to go to Mars. What was it? UAE, United Arab Emirates, China, and America. Took 7.5 plus months to get there. UAE was the 5th nation to arrive at Mars and go into orbit. The Chinese were the 6th nation to arrive. We arrived after those guys, and we waved at all the other hardware we had in orbit. So, that was fun. But the point is, it was a significant achievement for the UAE and the Chinese. Okay, this is a little pretty picture of departure. The Earth's going 29 kilometers per second. We leave the sphere of influence, which is 1 million kilometers up there, at 2.9. So we've got to leave from the low Earth orbit 3.6. We lose a lot on the way up. Here's our little pretty picture. We're departing at 7.76 kilometers per second. If we had an optional anchor that went all the way up to 150,000, you go faster. If you go to 163,000 kilometer altitude, you can leave our solar system without a rocket. Okay, pretty picture. If you have more energy, you have a bigger ellipse. That's just to show the size of the ellipses versus a Hohmann transfer that just barely makes it to Mars. What we want to do with that high velocity, though, is not do the traditional approach with the ellipse. We want to cut the corner. So we enter these ellipses, they're called orbits. We enter the elliptical orbit on its side and take the fast transit to Mars. Now, if you miss it at that point, you could probably meet it over there on the other side. So there are all kinds of options, but the real kicker is we're doing it differently. And we have a buzz schedule. Whoa, wait a minute. I want to go to Mars. I want to send my hammer. So I go over to the Indian Ocean Space Elevator and leave on Tuesday. And it takes 400 days to get there. And then I come over here and I want to send pizza. So I go to the Pacific Space Elevator and leave on Thursday, and it gets there in 79 days. So the real kicker is it's routine. It's every day. You can release every day. 61 days, rapid, and massive capability. So what we're providing is so much more than rockets can provide. This is an old chart that shows that we've only done 22,000 tons. If you notice, 22,000 tons, 16 and a half is just putting the space shuttle up there. By the way, I counted the space shuttle, because it was an orbital mission, so I counted it. So that was most of the mass. So it's kind of like scary about that. But anyway, if you want to use Mr. Musk's mission, just as an idea, then to do his job, he needs 40,000 launches every 26 months. He has to launch a whole bunch of stuff. So at 40,000 launches, that's a long time. So that's a little shaky, but that's what he has planned. I propose that what we want to do is have Mr. Musk send his people and all the early hardware as soon as he can and start his colony. But then when he really gets hungry and he needs a lot of logistics, he ought to call for space elevators. Now, the real kicker is space elevators are evolutionary. It's the first big step. We kind of stumbled off on the Apollo program and stuff like that. What we need is an infrastructure that's a big step. But elevators are also revolutionary in that it changes the equation on delivery of mass. We're no longer limited by the rocket equation. I came up with a term I like, which is liberating movement of logistic cargo by electricity. kind of funny. But anyway, the kicker is we break the equation. Okay, that's what I have on the charts and everything. So
Well, you're really good with time.
oh, well, good. Hey, that's good. I got 2 minutes on my cutback time.
Yeah. So is there one question in any of the chats? Something from Kevin Berry. Just
Yeah,
very
I can
quickly.
just ask it directly. Dr. Swan, can you take and elaborate further on kind of the even potentially greater opportunity of not just departing off of the tip of the space elevator, but actually gainfully using the acceleration you get falling from GEO, and sort of the discussions that have been discussed about how that can be used to accelerate objects even greater speeds and thrown further out?
Okay, it turns out there was a recent paper by Professor Matthew Peat, and it's an interesting paper. Now remember, I taught orbits for 2 years at the Air Force Academy, so I think I understand a little bit about orbits. But anyway, he teaches orbits at ASU, and we've been working with him on the research. So he decided to publish a paper that took the release of payloads from the space elevator from archaic, which is what I look at, which is you get it up to the space elevator, you stop it there, and you pump it with gas or whatever, put people in it, whatever, and then you release it. So your inherent velocity is 7.6 kilometers per second. Now, if you then do what he was talking about, you could release this the payload from the space elevator at geosynchronous and keep it on a nice line by having it attached to the space elevator, but not slowing it down at the tether end. You just let it accelerate from geo all the way out to 100,000 kilometers, and you now can leave the solar system with no rocket fuel. And then he had 2 more tiers. He's calling them tiers. Mine was tier 0, like mundane. That would be tier 1 to have an acceleration. And tier 2 and 3 added a capability to depart at an angle other than the equatorial plane that you're in. If you do a normal space elevator thinking, you release and you're in the equatorial plane, and all the stinking planets are in the ecliptic plane. So you have to have rocket fuel to change from equatorial to ecliptic. And he was able to show how he could do inclination changes with mechanisms at the end of the tether. And what he says at the end of his paper is he can get to any planet in a reasonable time, releasing from the space elevator every day of the year.
Wow.
Oh yeah, it just blows your socks off.
It does. We need to move on to the next topic, if that's all right. We don't want to cut Dr. Wright short.
Oh, no.
All right. Thank you very much, Dr. Swan. So Dennis Wright will be speaking on the status of necessary body of knowledge, International Space Elevator Consortium reports, the IAA and Obayashi Corporation. Dr. Dennis Wright is Vice President of the International Space Elevator Consortium, where he works on simulations of the physics of the space elevator, including its dynamics, its electrodynamics, and the effects of radiation. Dr. Wright recently retired from Stanford University, where he was a physicist in the Elementary Particle Physics Department of the SLAC National Accelerator Laboratory. He has been involved in more than 20 experiments ranging from low-energy photonuclear reactions to the ATLAS experiment at the Large Hadron Collider at CERN. Dr. Wright earned his PhD in nuclear physics at the University of Illinois at Urbana-Champaign. Dr. Wright, the floor is yours. Is anyone else hearing Dr. Wright?
Nope.
Dennis Wright? You've got your,
I'm muted.
have your
Am I
slide.
okay now?
There you
Nope.
are.
Okay, sorry, I was muted.
That's all right. We can see your, we could see your slides just a minute ago
Okay,
there.
they're
There we
coming
go.
back now.
Perfect.
All right. Yes, thanks for the introduction. And you'll probably notice I made quite a career change in going from the microscopic world to the macroscopic. And there has been a lot of learning on my part in doing that kind of change. So what I'd like to talk about today is the space elevator body of knowledge. In other words, do we know enough to go ahead and start doing a development project? And I hope I will convince you that the answer is yes. What do we know today? It's a pretty big body of knowledge already, and I'll try to summarize that, although in by no means an exhaustive way. We spend a lot of our time now on finding out what will we know. So we have to think of all those vague and nebulous things called the unknown unknowns and try to pluck things out of that region and put them into the known unknowns. And a good example of that is what's been going on with the recent study we have in ISEC, which is how does the climber actually grip the tether? And so we're learning a lot about what I considered to be a rather mundane thing, that is, what is friction? And it's turning out to be a lot of unknown things about friction. We have to measure it, very little theory predicting what it should be. So a lot of the parameters for the climber and the tether material itself are sort of moving into the known unknowns. In other words, what do we want to know about them? And finally, I'll summarize by saying, or trying to convince you that we do know enough to go ahead with a research program and development. We do have a rather large body of knowledge to draw on for the space elevator. As I mentioned, it's what I'm going to present is certainly not exhaustive. I have three main sources. The International Space Elevator Consortium does studies and papers, and we post those on our website. There are many studies and papers from the International Academy of Astronautics, so that's another source that we depend on. And the Obayashi Corporation in Japan is actively developing space elevators and running tests. So let's talk about the things that we know and the literature that's out there. We have a reference library at ISEC, and that's also on the webpage. And going through that, I estimated about 600 unique entries and divided into 19 sections. And these include the ISEC study reports, and there are 11 of these so far. Lots of articles on tether materials, about 90 articles and papers. And of course, the research on carbon and strong materials has journals of its own. So there are so many things to choose from. But 90 of them so far look pertinent to us. Tether dynamics and electrodynamics, we have 88 articles there. So how does the tether move? What does the electromagnetic radiation do to the tether, and how can you transmit power and things like that? Architecture. So Fitzer talked about this, and we have 79 articles talking about the architecture of the space elevator. Space elevator environment, lots of things here. What do we do about debris? What's the effect of radiation, and so on? And then related to the architecture, of course, is what we have about the Earthport, the GeoNode, and the Apex anchor. So we have a lot of these things that are published, available literature, and we build on these things. Now I'll talk a bit about the studies that we do. So at least once per year, and lately more than one, we have an in-depth study and consequently a report in which we cover a major item of the major space elevator issue. And these typically take about a year to do, sometimes more, sometimes less. And I'll just very briefly summarize those. You can find out a lot about these. They're all posted on the website, so you can read them at your leisure later. But to start out, we have two studies that deal with the space debris situation. So one in 2010 and an update in 2020. And they conclude that the problem is manageable. So I think Pete touched on this before. We have also 2 studies on the transportation infrastructure, which is quite relevant to the topics today. Space elevator concept of operations, what the space elevator will do for you. So 2 studies on that. 2 studies dealing with the design of the Galactic Harbor and the Space Elevator Earthport. And Vern's going to tell you about those in his talk. The concept of a multi-stage space elevator is quite interesting, and so we don't necessarily have to build it all out of one tether. We can have a first or a couple first stages built out of a rather unique concept. And to find out more about that, go see the report, because I haven't got time to go into that. The 2017 report dealt with our simulation needs. So how does the space elevator move once it's up there? And we have to, of course, know what kinds of forces it's going to exert on the Earthport. What do we have to do to stabilize it, to make sure that we understand all the forces and loads that go on the space elevator. So this can be done a lot by simulation, and we essentially laid out the roadmap for developing the simulator. 2016 report was for the GeoNode and Apex Anchor. 2014 dealt with the space elevator architecture roadmap. So how do we get there from here? And 2013 was the first serious look at space elevator climber designs. The conclusion here was that climbers could be built mostly, I say mostly, with present day technology, and spacecraft design is a well understood art. Now, as I said, you can see all these at the ISEC website under the Resources tab and the Studies tab. We have 2 other studies, and I'll talk about those a little bit later. Now, the IAA, as Pete mentioned, has put out 2 studies, and he mentioned both of these. One is the assessment of the technological feasibility and the way forward for space elevators. So 2 of the conclusions there were that given a tether material, space elevators look feasible. So that was important. And also, as far as the investor is concerned, it looks like such a mega project would be successful for investors. And then in 2019, there was another IAA study, Road to the Space Elevator Era. And the conclusions here were similar to the ones at the Climber study. That is, many of the components can be built with today's technology. And the tether material is, of course, the pacing item, but as we have heard, we expect that to be coming along soon. And there are lots of IAA papers having to do with space elevators, about 50 presented at the conference, the IAC conference. And I know there are probably more than this, but my brief search showed at least 15 Acta Astronautica journals dealing with space elevators. So that's the academic world, I could say. Let's move on to what's happening in the corporate world. And here we have a kind of a unique example. The Obayashi Corporation is one of the 5 large Japanese construction companies. So they do civil construction and big project construction. They are teaming up with the Japan Manned Space Systems Corporation, and they are actually doing some tests. As Pete mentioned, they have their own design based on a 2 tether system, both made of carbon nanotubes, and they assume a 100-ton climber, whereas we're assuming 20. And all of this is under active development. I believe they are the only people in the world who are currently paid to work on space elevators. So I think that's quite an achievement. They have actually flown ISS, International Space Station missions, testing likely tether materials and even tether climber designs. So they have flown experiments. And they have published several IAA papers and studies. So we draw on that knowledge as well, especially the experimental knowledge that they are gaining. The plans for Japan space elevator, they have a detailed deployment plan already worked out. They have costing and a construction schedule, so they're estimating 100 billion, and the schedule is for 2050 construction. And at the bottom of the page, you see a depiction of their station at the GeoNode, and that is basically a collection of inflatable modules that are at that position. So that's the knowledge base, my survey of the knowledge base as it stands at present, but we are, of course, increasing it. And our annual studies will continue. So we have many more important topics to look at. We have a research division. And several years ago, we went into the exercise of identifying some of the major issues that needed to be studied. And we costed them and made timelines for them. And so we basically have an idea that, given the funding, we know where to go and what to start doing in the research area. Testing. Fitzer mentioned this and emphasized this rather strongly. It's a huge part of what's going on. With a tether material on the horizon, we need to be planning specific lab tests. And right now, as Adrian and Rob mentioned, a lot of the market is for powders and small pieces of graphene, for example, but nobody is really looking at testing macroscopic pieces of this yet. And so that's a very important thing to get started. Now, let's go back to some of the current studies. As you heard from Jerry, the most recent completed study is the Green Road to Space, and he told you all about the evaluation of the environmental impact of the space elevator and the big advantage that it has over rockets. So that is in final review, and it's available on the website. And the study that I mentioned, it's going on now, has to do with the climber tether interface. So in 2013, there was a climber study in which they looked at various types of climbing technologies and how do you get the climber to grip the tether and so on and so forth. And there were lots of really ingenious methods put out. And in the current study, we think we have ruled out pretty much all but one, and that is the pinched wheel design. So we'll have a tether, and as you can see by the diagram, the purple cylinders are pressing the tether from either side to produce the friction force that allows the climber to be advanced. And one of those unknown unknowns, which now we think is a known unknown, is that we are quantifying the parameters that are impacting friction. And one thing we didn't really effectively appreciate until now is that now that we've gone to a pinched wheel design, we really need to pay more attention to compressive forces. So we're always worried about the tensile strength of the tether, and that's of course critical. But the tether itself has two jobs. It has to be strong enough to support itself, but it has to have a mechanism that allows gripping. And it looks like single crystal graphene may be rather slippery, and so we have to understand very well what the coefficient of friction is and how to increase that. And we think we have a way to do that, but we have a lot more to learn, especially when it comes to this interesting idea of molecular engineering and how we can modify sheets of graphene to stick together in a strong way and not delaminate as these climber forces are applied. So that's the current study, and it's going on. It may go on for longer than a year because we're finding out lots of things that we need to look into. Now, the research program, as I've mentioned, is pretty well laid out, and a lot of the materials, or a lot of the areas have been identified. So tether dynamics, as I mentioned, electrodynamics, radiation effects, the multi-stage space elevator, space debris, climber engineering, and space elevator simulation. So as I mentioned, we have, these are costed, we have personnel estimates completed, we even have Gantt charts. So we know pretty well what we need to do, and we are ready to go upon some funding. So research is there. And testing. Adrian showed the picture of the samples that we have from General Graphene. And so I think that's fascinating as well, that you can actually see a monolayer of polycrystalline graphene. Now, this is interesting because in our study, we are trying to find ways to test materials that we don't have yet. And polycrystalline graphene is a kind of a prototype. It's not quite the single crystal graphene that we want, but it might be good enough to start doing testing on it to give us some idea not only of what single crystal graphene might be like, but also to give us the experience of developing the tests and the material, the equipment that we need to do the tests. So practical questions are, how do you take a monolayer off the substrate without destroying the monolayer? And so on, things like that. How do you make a tensile strength test or a brittleness test or a compression test? So all of these tests are in the process of being identified. And the next step will be for us to probably work with people like General Graphene and Adrian and Rob, and trying to devise the equipment that we need to do the testing. So we need equipment, devising the tests, planning the tests, and much of this is underway. Another part of the testing, which is quite a bit different from the sample testing of the tether material, has to do with prototypes. And as I mentioned, Obayashi and JAXA are already doing prototype testing with climbers and tether materials, so that's great. A very interesting thing is happening with the multi-stage space elevator that I mentioned. So this is an alternative way to enable the construction of the space elevator using present day materials. So if we can build a multi-stage space elevator, then we don't have to wait for those materials. But a prototype, a 5-meter tall prototype, is being built in Panama to demonstrate the principles of the first stage of this multi-stage space elevator. So once again, I encourage you to look at John Knappman's, he chaired the study for this in the 2018 report. So please have a look at that. And now I'm to the end, and do we know enough? A lot of the work has already been done, and we've answered some of the big questions. So see the ISEC reference library and refer to the talks that you've heard earlier today. We have a very good idea of what we need to know. So we have a proposed research program. We know we need to do lots of lab testing, and we're on our way to defining what those tests should be. We will lean heavily on the testing already done by ISEC, Obayashi, the multi-stage testing. And based on all of this, I think we are really ready to start a development program. That's all for me.
All right, thank you, Dr. Wright. Our next speaker is Vernon Hall. He is the Earthport Harbor Master for the International Space Elevator Consortium and president of Galactic Harbor Associates. Mr. Hall is a professional engineer with a long career in the transportation industry, working on freeways, rail yards, ports, bridges, pipelines, and now space. He spent 27 years at the Port of Los Angeles, where he played a leading role in redeveloping and expanding it from a regional port into the largest container port and intermodal complex in the Western Hemisphere. Mr. Hall earned his engineering degree from UCLA and is active in a number of professional organizations. Go ahead, Mr. Hall. You're still on mute.
Okay, I assume you can hear me. I'm going to need, I think someone's going to put the slides up for me. I failed at the Friday test using Google. I think Fabio has them, if he's still here.
Yes.
Yep, Fabio's working on it.
Okay, great. Well, first of all, I'm honored to being the last presentation of this session of is quite an honor to me because as Lee said, I am a civil engineer, not an aerospace or a scientist of some kind, and the title, which I did not choose, is quite pretentious. But it is appropriate. So let's move on to the next place. Next slide, please. I actually got involved in intermodalism when I started with the Port of LA as a not so young civil engineer. It was a point where the entire port industry was transitioning from what's known in our industry as break bulk cargo. I think the best image, which I don't have for you, I'm sure you've all seen the film On the Waterfront. Well, Marlon Brando and his gang and Johnny Friendly are all gone. But at that point in time, it was still the way most cargo was handled. Ships came in, berthed alongside, and they were offloaded onto a dock or to a wharf using their own equipment. They were put on pallets. And in order to protect the cargo, they moved directly into a warehouse, or what was called a transit shed. All of that changed with the concept of containerization, which I'll show you in a minute. Next slide, please. You've seen this before. It's a piece of the image of the Galactic Harbor, the unifying vision. And of course, the focus today will be not on the Enterprise, but on the Galactic Harbor as a permanent transportation infrastructure. Next slide, please. Today, like most infrastructure, people take infrastructure for granted, as many of you may know if you're in that business. They only notice infrastructure when it fails to work. A great example a couple of weeks ago occurred in Texas. The power went out. The windmills froze. And all of a sudden, who's going to fix it? What happened? Is it the politicians' fault? Is it the utilities company's fault? Like I say, it's only noticed when it doesn't work. Same thing applies to transportation. I had a personal example of that myself. I ordered a microwave for Christmas on Black Friday. Going to be delivered by Amazon 10 days later. Halfway through January, I finally got it. Now, what happened? Well, it came from somewhere in the Far East, maybe China, maybe Vietnam, put on a container ship and delivered to the Port of Los Angeles. Unfortunately, thanks to COVID, the Port of Los Angeles wasn't shut down, but it was slowed down by labor. So labor is a link in that transportation chain. Anyway, there are many components in the transportation system. The obvious ones are ships, which have grown dramatically in size. Trucks as a basic, traveling our interstate highways. Trains, which have grown from local service trains to unit trains. Our nation and the entire world is underlain with pipelines moving liquid cargo around, and of course, aircraft. And there are hundreds of businesses involved in the transportation chain. Shipping and trucking lines are obvious, seaport and airport terminal operators, custom agents, officials, labor unions, and they're all interconnected in what's now known as the global logistics supply chain. Next slide, please. It's a bit of a complicated mess, as you can see in that little thing, image I pulled from the internet. Many players involved, but it's come together, and they're using ever increasing bits of technology. Blockchain technology, which I don't profess to understand, even though I've tried to, is now being used as a standard way of transacting business in the cargo movement business. They're using the Internet of Things. They're using artificial technology, remote sensing, analyzing metadata. They're even moving into autonomous ships, autonomous service craft now to tugboats and ferries in Europe particularly. And of course, one more, hold it. Okay, next slide, please. Forget the of course. Anyway, this is another image of the intermodal system, the massive container ship, the trucks that roam the highways, the unit trains, and the airplanes. But it's a two-dimensional system. It hugs the Earth. It crosses the Earth, it crosses each of our countries, but it, of course, doesn't go into space. Now, today's going into space by rocketry uses this system. Components are built somewhere, they're transferred by truck into Cape Canaveral or Vandenberg, but it's not an integrated system yet of getting into space. I think you also, but it's become the global logistic chain has become a profession now. In fact, you can get degrees in global chain management from such prestigious universities as USC, the Marshall School of Business. Excuse the phone call. But what one thing, and I think we know the answer, Kevin, is what one thing made all this happen. And that, of course, was, next picture, please. The container. This is the key component that created intermodalism. And that was the standardization worldwide of a shipping container. Let me refer to my notes here for a moment. This was actually a one-man's idea. His name was Malcolm McLean, a Scotsman who was a trucker working in and around the port of New York and New Jersey. He saw the inefficiencies of handling, double handling, triple handling cargo in break bulk. He saw the inefficiencies of moving cargo from ship to warehouse to train or truck. And you needed the warehouse because you had to protect the cargo no matter what it was. And so he came up with the concept of a standardized container that could be used by a truck, by a ship, and by a train. It started out much smaller than this, but a couple of dimensions are pretty much have not changed. That's the 8-foot width, the 8-foot 6-inch height, and the original containers were 20 foot in length. In fact, the term 20-foot equivalent unit is now standard throughout the world. He also, and this is very, I think, appropriate to what we'll talk about later, is how we start building the space elevator system. He also used and adapted existing equipment. They were shipping containers before, and so he started developing standardized truck widths, standardized trucks lengths. If you've seen the so-called big rig on the highway, it's basically a road tractor and a chassis. And the chassis is designed to hold the container safely and securely aboard. And then, of course, it's disconnected when it gets to its destination. So they standardized the chassis, they standardized the power requirements for the rigs. And as the industry evolved, the shape of the terminals at the ports and the shape of the terminals at the trucking centers changed. They needed more and more land. They started developing specialized equipment, such as yard hostlers, they call, that move the containers on chassis around the yards. I should have got some water here, I'm sorry. In the rail, using that same container, he first put the chassis on wheels with the container on it on a flatbed rail car. That was called container on flat car. When I first started designing facilities for that, that's what we were dealing with. Then he figured out a lashing method so the chassis didn't have to go with it. So it became container on flat car. And then the design of the flat car was changed to allow a lower bed so you could stack two containers on top of each other. And then the height of them became, of course, a key dimension as you cross the country, passing under bridges and going through tunnels. So this just continued to evolve. And I think that's exactly what's going to happen as we start developing the equipment, much more sophisticated, of course, for the space elevator. I did, there's a very excellent paper out written by Kevin Berry, and I'm going to quote him for it, and quote from it. And it says, the standardized shipping container accelerated trade, increased economic productivity, and made shipping a safer and more reliable sector. Brilliant words and absolutely true from my own experience. Next slide, please. So the beauty of it is you can manufacture your product, say, in China, shall we say, put it in a container, seal the container, lock it tight. The knowledge of what's in that container, along with everything else in it, will be recorded digitally, and it'll be taken to a marine terminal where it's loaded upon a container ship, along with literally thousands of others. Takes about 2 weeks to get from China to, say, the port of LA or the port of Long Beach. Lifted off, set briefly at a container terminal, and then transferred to either a truck chassis to go to a regional warehouse for regional distribution, or in many times put on a unit train, which is about a mile long, that will take it across country via initially the Alameda corridor, which I'll talk about in a minute, and then literally can go either to a distribution center in Chicago or all the way to the East Coast and possibly put on another ship. This was called land bridge. It was made possible by the fact there is an intercontinental railroad. So I hope you can see the parallels of what's going to happen as the space elevator railway or main channel, global galactic harbor main channel develops over the years. By the way, this was, again, I think Kevin said it clearly, that this was the transportation story of the 20th century, or one of them, the concept of intermodalism. And I was around to see part of it and actually contribute to it. I'm not quite old enough to be part of the opening of the Panama Canal or the actual building of the Transcontinental Railroad, but I hope to be around maybe to see the beginnings of the 21st, our transportation story of the 21st century. But anyway, the key thing is that the Galactic Harbor will tie an existing, ever more sophisticated system into that third dimension, taking things to and from space, and the nexus point for all that will be the Earth port. Next slide, please. I won't take you through all this, but this is one of the first things I did for Pete and Fitzer, was to come up with this little simple block diagram. We use the existing system of air, highway, and rail to get your product or your cargo or your payload to a Earthport access city, which is shown in the middle blue there. And at that point, it'll come under control of some operating company and enter that third dimension. From there, it'll be transported to I don't have the control of the pointer, I guess, but the blue box down from the top is the Earthport, and then from there it goes into space using the climbers via the terminal, the tether transfer facility. Excuse me, tether transfer platform. Let's take another slide, please. One of the aspects of the Earthport transportation system, or this Galactic Harbor Transport System, is reliable, regular, safe, secure, on-time delivery. Now, it takes a long time to get there on time, but it doesn't matter. Pete used the example of hammers and nails. If you have high-value, small mass cargo that you really have to get there tomorrow, today you put it on an airplane and get it there. However, for almost the history of mankind. If you want to move large masses of cargo or people long distances, you use it by ship and or by rail. Most of the great cities of the world, of course, are built on rivers or ocean fronts. That's because it's transportation of getting stuff there. And again, in the future or today, if you want to get things into space quickly or through the radiation belt, you're going to use rocketries. But again, the point's been made several times today. If we have large masses of payload and can be on a regular schedule, we're going to use the elevator. Next slide, please. So we've discussed they've been discussed before, and they're contained in one of the ISEC reports. Some of the key attributes of the Galactic Harbor are the access city. This is where the business will take place. This is where the contracts will be signed with the providers, with the cargo. It'll have, and it'll be the point where it'll go on to the floating ops platform, the tethered terminus platforms. I believe I'm working on something which will tend to standardize the space elevator containers, which will then allow us to standardize the climbers. The earlier ISEC report showed a number of different concepts, most of them cylindrical in shape, and most of the imagery is that. But I think there's a chance we might take advantage of the standardization that's occurring in today's conventional intermodalism and adapt that to the space elevator. But the key elements are safe, reliable, routine, cost-effective with minimal environmental impacts. The other thing that sets, I think, the space elevator's transportation system apart from rocketry is and this is what civil engineering look at, so I apologize to the space scientists that might be in the audience, but our goal is to create a regular activity. We send something up every day, and the something is about today the size and shape of one of those road containers you see on trucks throughout the country. To me, rocket launches are still events versus activity, if you see the distinction. And some of the numbers thrown out earlier are just a little amazing about how many launch events are going to occur in order to achieve some of these missions. I think there's a reason for skepticism there, shall we say. Next slide, please. Okay, this is a civil engineer doing naval architecture. Not a good idea always. But this is the floating operations platform taken out of the water. Obviously, it doesn't float above the water, but it does show the underlying structure. We have conceived this as a semi-submersible offshore floating structure. And in these big pontoons are all the machine spaces, the engineering spaces, the ballast tanks. It can be self-propelled. It can also be hauled around by tugs and so forth. Waterline is about at the face of that large flat dock you see there. That's where the cargo handling will take place, receiving and then departing for the tethered terminus platforms. I've also provided a little internal marina and the number of workshops that Fetzer mentioned earlier. The upper decks will be kind of like a cruise ship because they'll house a lot of people. And the top two decks in the gray there will be the home for the operations and control center, which will be, I think, due to the communications requirements and the directive requirements to operate the system, will be quite large and equal some of the ones we see on television and some of which you've probably all been to. And then the top deck, of course, will have helicopter pads and all of our communications, antennas, and so forth. I've even, you may notice, I don't know how big your picture is, but I've even thrown in a tennis court there and probably a golf putting green or two. Next slide, please. There's the control system we've seen before. Next slide, please. So I'm rambling a little bit. I'm in awe of all the information that has been presented today. But the key here is that as we develop the the Galactic Harbor's transportation infrastructure, it will indeed plug into and expand, that's the key word, the capabilities of today's global logistics supply chain. It will assure scheduled delivery of large masses of payload to GEO and beyond in a safe, reliable, and routine manner. And as several people have mentioned, it provides a complementary access to space, which is absolutely necessary to achieve the planned missions. So I'm sure I didn't cover everything I was supposed to, but I appreciate the opportunity and love to take any questions. Thank you. Or comments.
I see some discussion in the chat, but I think it may be left over from a prior talk. Any questions for Mr. Hall?
Well,
Can you talk about,
I have one quick question. Vern, there was a master's student that came from Finland or someplace like that and did his studies in Japan and then wrote a 400-page document on where we ought to put the space elevator. You want to comment on that? I think it's an excellent start at an analysis, and then you took it to the next level.
Well, I did. I wrote a little paper and presented a couple of years ago and I think it's online somewhere on our website. But the original studies conducted by ISEC about the port access city they kind of brushed it off. They had to be somewhere, near the equator. And I took it a little further based on just the realities of the existing system. And I believe that the access city should have a business climate that's acceptable to the international community, probably a monetary system that's accepted, an international airport because planes are scheduled and cargo planes arrive on schedule, and most importantly, a deep water harbor so that scheduled ships can arrive. This is so-called liner service. And then having a deep water harbor would also have a smaller harbor that could be used as a checkpoint for getting our cargo on smaller ships out to the port. Mental block here. Out to the earth port. The earth port should be, as we know, somewhere near on the equator. And I kind of came up with maybe Honolulu would be a better location than somewhere in the Galapagos Islands. So that's, however, the young man in question came up with the same answer, and other people have studied it from different directions, including climate, wave conditions, and all that. And they pretty much come up with the same conclusion that maybe our first earth port should be somewhere south of Hawaii, which is about a day and a half trip by sea from Honolulu. It's only a few hours, maybe an hour and a half by high-speed plane. You can be there in a day by high-speed ferry. So it's a pretty nice place to do business, of course, and get our project started with 8 locations, not 3 as you're proposing, but 8 locations around the world. It's quite an interesting story.
Why would you use an ocean-based platform when staying away from weather seems like a good idea? That question is from Martin Horowitz.
The main problem is there's not many good places around the equator where you could build one on land. And the equator, of course, is very benign. It's in the doldrums. And it's another, because that's why we conceived of the floating operations platform as floating. Certainly it could be built on land, or it could be built on an island. And I'm sure some of the locations that China is looking at will be exactly that. And I think if you look at the Obayashi plan, it's also shows the actual launch point reached by a causeway from existing land. I'm not quite sure where they're putting it, but so yeah. But the features that go into it can be built on a floating platform, we've tested my little concept against some reputable, world-known, well-known naval architects. They say, sure, we can build this. And by the way, it could be built today with funding. It's going to cost about $600 to $700 million. So,
How many jobs would that result in over, say, a 5-year period?
that's a study that yet to be done, but just to staff the floating ops platform, there's 100 people. It'll be the equivalent of a good-sized cruise ship. There'll be nice staterooms and nice dining rooms and entertainment, and of course interconnectivity with the world for entertainment and staying close to home. But the industry of offshore oil rigs, there's a whole bunch of people that are used to spending 3 or 4 months out there in the middle of nowhere. We'll make it nicer than that. I say we will. Somebody will make it nicer than that.
One of the biggest arguments for international water is the legal.
Yeah, I didn't touch on that. Yeah.
If you put it in Botswana, what legal rules, rule of law, et cetera, et cetera. So the real answer for a corporation to build something that would be at risk if you put it in a country that wasn't solid is damaging. We've almost concluded that it's got to be in the middle of the ocean. And then if you go to the middle of the Pacific, it is Pacific. There hasn't been a lightning strike where we're looking for 100 years. There hasn't been any hurricanes because they don't grow on the equator, et cetera, et cetera, et cetera, et cetera.
One of the things Fisher wanted me to touch on, and I think I failed to do so, was I think the first thing I told Peter when I met him, Pete Swan, when I met him a few years ago, was I didn't know what ISEC was. I thought it might have been a funded corporation. Of course it isn't. But I said, get yourself a bunch of international lawyers on staff, because there's going to be lots of, there's the law of the sea, there's the law of space, and all those things have to be dealt with. Rights, 200-mile limits, all that kind of thing come into play. I have experience with that, though. I think, Kevin, I don't know if you ever studied Kevin, have you ever looked at the Alameda Corridor, which I had a big part in developing? The Alameda Corridor is a railway infrastructure through the metropolitan area of Los Angeles, which was crisscrossed with rail lines that were developed by 3 or 4 separate railroads. In order to expand the harbor, the so-called 2020 plan, to achieve the image that Fitzer showed you earlier, both ports got together with the Army Corps of Engineers and developed the so-called 2020 plan. As mitigation for that, because it was going to bring rail back to the harbor and start developing mile-long trains and then have them impact as they move east out of LA, the traffic impact would have been amazing and intolerable. So we literally came up with a concept of a consolidated rail corridor. And ultimately, we created an authority under state legislation that allowed us to, pardon the expression, strong arm the railroads, and they're very tough to strong arm, and say, you will use this corridor. We'll build it for you. It cost $1 billion, which was a lot of money in those days. It's pocket change today, of course, but we will build the corridor. You will use it. And you will not only use it, you will pay us a fee for using it. Now, of course, their reaction was, what? Well, the answer that we replied to that was, you will use it or you won't use the harbors. You won't move any cargo out of LA or Long Beach. So you do need that kind of legal authority to do something like we're talking about to build space elevators.
Well, in one question, you mentioned the whole international water to avoid the sort of difficulties that would come from the majority of the countries that reside along the zone for this equator. The Atlantic is bad because the British Navy can threaten it, and hurricanes. I'm waiting for Adrian to respond because there's a lot.
The thing is, our aircraft carrier has all your planes on it. They're all American F-35s.
But the problem is there's a country in the Pacific that has demonstrated a willingness to steal whatever it wants, and not the U.S., which is also willing to do that. And so is there not a need for some sort of official or unofficial seal of approval from a major power?
Of course. And of course, the country you may be talking about is doing certain things in the South China Sea. Is that the one you're talking about, Tim?
I wouldn't be slanderous to the great.
No, I loved it. I spent a good month in the South China Sea in my Navy career. It's a lovely place. But no, obviously you get into, since that same country, if we're talking about this, it was also planning to build a space elevator and has the same vulnerabilities, whether it's on land or sea, I think, yes, of course. There will have to be international agreements, and there are agencies, and there may be new international organizations formed to cover space elevators. That's why I say we need probably 10 years of good legal work along with all the engineering we have to do.
Or Adrian's aircraft carrier to sit beside it.
From a logistics perspective too, don't a lot of you guys' design, you have the Earthport as the anchor, but you have certain conical designs, to say nothing of Natman's active structure, where you're going to actually have multiple positions in a general region kind of going into a cone, which would make securing the space elevator quite a bit more difficult. What distance apart would those be at the surface of the ocean in your designs to make that conical structure?
Well,
the first thing here is that we're just still looking at that as an alternative, and the answer to the question is it'll be set up as necessary, hoping that we recognize what we're just talking about is that there will be international agreement that there will be space elevators. I mean, I don't think we can turn this upside down saying because my legs on my tripod or a 5-legged tripod are too close or too far apart means there's no elevator or not. That has to be put on the table. We have to have a solution-oriented international agreement, because the inverse of that is unacceptable. We can't say I don't think we can allow, and I don't think the Chinese would allow, even in the non-competitive environment, that we won't do space elevators because of some sort of structural thing. That was certainly I proposed to do work on the Alameda Corridor. There was no question ever that there wasn't going to be an Alameda Corridor, because there was no question that we were going to have a mature Port of Long Beach and Port of Los Angeles. No question. And when the surrounding states realized that 35 to 40% of their employment was going to come from the fact that there was a Port of Los Angeles, even the Environmental Protection Agency, which is an example that Vern didn't mention, they retreated. That's a long story, but it was a non-threatening retreat. Everybody knew we were going to have a Port of Los Angeles.
Yeah, different take on.
And by the way, Tim, just right between the eyes here, that's what I meant when I talked to you several months ago. You need to define authority here. Okay, Vern got authority and did it. That's the image I think we want to protect here. Project. I said protect. Project here. Sorry about that, but that's what's happening.
Kevin, was that you with the question about the difference, the distance apart? Was that your question or that Tim's?
I mean, that was just sort of mine of how far apart. Because I mean,
well, what we have presented was basically a concept I came up with, that separating the ops platform or the ops center from the actual tether terminus. So I came up with the concept of many concepts you'll see in the literature, and many of them on on the YouTube show the tether rising right from the same place that you have the control center and all that, but that's probably not the best thing to do. So I arbitrarily chose 1 hour away by offshore service boat, and that's 20 kilometers. So if we have 2 tether terminuses and you put the floating ops platform in the center, you end up with basically a 20-kilometer separation. So you have maybe a 40-kilometer circle, and then you go to space from that, and it creates the spaces of the other regions. That's all going to change when we get in design. Like I say, I'm a civil engineer, not a nautical engineer, but the concept is to maintain at this point in development as much flexibility as we can. And these things probably will have to move. They'll move because of changing tides, weather. Again, we still don't know what the actual stresses will be, so that's where we need that simulation study someday. But it's all stuff that can be done right now with funding, of course. I think it's time for your next session.
All right.
Bailing out there, Vernon?
No, I'm here. I'm sticking around.
Okay, good.
All right. So as we head into our final event of the day, our expert panel, I'd like to thank you all for joining us for Blue Marble Week. The Foundation for the Future hosts this event each month in order to educate about and advocate for space infrastructure development.
Okay, I need Fabio or somebody to put the panel charts up. There's 2 or 3 of them, and we'll get to the third one quickly, just for reference points.
First, to continue the momentum generated by today's fascinating and practical presentations, here is Emily Mishler with the Foundation for the Future. I'm going to do a quick share.
Wonderful. Well, it's a pleasure to meet you all and be here today. My name is Emily Mishler, and my background is in the intersection of corporate philanthropy and creative solutions for revolutionary ideas. I've recently become affiliated with the Foundation for the Future, and from the nonprofit perspective, have become a partner in building the development arm of the operation. So what does that mean? That means we're financially positioning the Foundation to be able to continue this important work for years, if not generations to come. From our conversations today, it's abundantly clear that the work is disruptive, necessary, and the time is now, and that means we need your help. I've been both incredibly impressed with the comprehensive vision, expertise, dedication, and momentum of the speakers today, and I hope you'll join me. The vision of the Foundation for the Future is also equally inspiring and is the powering force behind Blue Marble Week and the events of the next few days. I believe we can all agree that the future the Foundation is building is inspiring and worth investing in. This future, in space and beyond, is being built one relationship, conversation, and connection at a time, as we can so clearly see here today. In order to continue this momentum in building and contributing to this caliber of conversation and community, we need your help. We need you, our allies, attendees, partners, advocates, and friends, to spread the word about our important work through social media, invite like-minded and like-hearted peers to our events, and to help connect us with philanthropists and organizations who believe what we believe, that our future in space is ours for the building, and the time is now. We're very excited to announce 2 different avenues to become involved if you're interested in financially supporting our work. On the corporate level, we have the opportunity to sponsor Blue Marble Week and the Foundation at large on a monthly and annual basis to support this important work. On a personal level, if you, your friends, or family are interested in supporting us, we welcome your contributions to support building space infrastructure and economy through the Foundation for the Future. If you're interested, more information for both opportunities is available at the Foundation for the Future's website, f4f.space, or by scanning the QR code found on the screen. So our ask, help us in bringing space home, because the time is now and the world can't wait. If you have any questions, please don't hesitate to reach out to myself via chat, Lila, Tim, or any affiliate of the Foundation for the Future. Our contact information and a link to donate is available at the QR code available on the screen and is also available on the website. I'll be here for any questions that you have and field any answers that might come about. But for now, I'll thank you so much and turn it back over to our MCs for our regularly scheduled programming.
All right, for our distinguished panel, The three of our earlier speakers, business analyst and thought leader, Mr. Barry, Mr. Fitzgerald, who has led projects larger than the space elevator projects, and nuclear physicist Dr. Wright, will be joined by Bill Britton. Mr. Britton is Vice President of Information Technology and Chief Information Officer at California Polytechnic State University. During his tenure there, he has built the California Cybersecurity Institute into a nationally prominent educational and research facility. From the inception of cyber and throughout his career with Cal Poly, at Parsons Cyber, and as an intelligence and electronic warfare officer with the U.S. Air Force, Mr. Britton has been on the forefront of developing and implementing new cybersecurity concepts. Go ahead and get started with the panel.
Okay, Fabio, pull up my first slide.
And Lee, thank you for that very generous introduction.
It was easy to be glowing about you guys.
Thank you, Leah. This has all been exciting for me because I've been dreaming on it, sleeping on it, worried about it, and frankly, I recognize the doability of what has been presented today because we know the path we're on and the path of the destination to where we're headed. I'm going to oversimplify what we said today. All right, the engineering and economics of a space elevator are obvious. But let's take a look a little bit at what else we need. My favorite story here is I was once invited in to be a part of a missile system. It was a very large project. And I walked into the conference room and there were two generals and three colonels all looking at stuff on the table there. And I said, aha, they're talking about strategic warfare or whatever. No. What they were looking at were the files, if you will, of ROTC officers in college, because they knew that the critical design review of this missile thing that I was getting involved in was 8 to 10 years away, and we needed X number of people to build it, test it, and make it work. And that's the tone of what I want the panel to do. Now, on the next slide. In simple talk, let's, by premise, say that's the engineering concept and include the alternatives that were mentioned today. Now let's look at the future. Next slide. And this is the who that have, I'm just going to sit back and listen. Bill Britton, Kent, and Dennis Wright. Next slide. Go to the next one, please. Is we have to match up the 5 or 6 forces that are going to make the space elevator and space infrastructure in general. And I played a little trick here. Is because I don't know which way the thrusts are heading, so I'm calling, as Bill Britton will call for, and Kevin Barry will call for, and Dennis Wright will call for, to reverse engineer back from the vision to figure out what we need in terms of education, a workforce, a business basis, and Dennis Wright, research and engineering, my friend. I'm going to offer the first moments to Bill Britton, and the other two interrupt when you got something to say.
I'm expecting lots of interruptions then. First, I want to thank everybody for setting us up the way that you did throughout the day. And I asked a couple questions, and they were primarily always the same, which is around why now? What makes sense now? And I think what was laid out is a really good conversation around the why. In the operations world, which is where I come from, there's an old joke and adage that the engineering team clears up what the scientists thought that they had fixed and designed and built. The engineers then get to design it and build it and put it into play, and the operation team clears up and cleans up everybody else's mistakes. So that's kind of the context for where I'm coming from today, which is this operation side or workforce. And I think that we learned something very significant throughout all these other major programs they've talked about. And the size of the workforce was a smaller entity in those days. It didn't take as many people to make things happen and go. And small strike teams were able to make these things happen, and they grew over time. I don't think we have that luxury with where we are at right now. This is going to explode, and you're going to require a workforce on the job, trained and knowledgeable from the get-go. Now why? I think the reason is because, as they pointed out, so many of these technologies are already known today. They're already understood. It's no longer the art of the possible, it's the art of the doable. And so as such, you've got to take those differing talent pools that have been using that technology for other resources, and you have to educate them first to talk to each other, to work collectively, and then to understand what it is they're now trying to do with these new ways of using the technologies. I see three primary technologies as a core element, no matter what you do in this business, that we really haven't even discussed today, but I think they're important. The first one is the knowledge of digital. Everything we talked about today has a digital component to it. Interacting, relying upon each other, really working as a collective. So the digital, everything from how do I get people from point A to point B? How do I make sure that as it goes up the elevator, there's nothing in space, debris? This is all digital data. Data correlates to the need for compute capability. The compute capability is now a major requirement to sustain this entire infrastructure operation. So how do we do that? Do we wait around? No, we have the capability today in cloud. So understanding how cloud is corollary to this new emerging infrastructure, using those cloud skills as it relates to the support for this digital community, this digital support structure. Now, embedded in both the first and the second, in digital and in cloud, is also the reference to cybersecurity. Space Force has made it a mandate that all of their programs have cybersecurity built in up front. There's a reason for that importance, and it's something that needs to be corollary. So every engineer, every person working on the space elevator concept needs to understand the digital cloud cyber arena. Now, getting that kind of workforce just doesn't happen overnight. So there's an entire requirement to really start re-looking at, re-energizing the support structure. Now, I'm not saying that universities and structures aren't capable of providing for the future, but if you really want them to be work ready for this environment, you've got to start changing that paradigm to match up. A lot of the principles that Fitzer talked about, he and I learned through the School of Hard Knocks, and as an operator, that's when he threw a wrench at me because we had dropped something accidentally on the floor. And that's going to have to happen. And what we want to do is try to reduce that as best we can in that educational experience. I saw the reference earlier to someone from the DC area with University Mars. Those are great concepts, but the question becomes, how do we make non-traditional education as well as traditional education important and computing elements for the future of the elevator? More importantly, how do we get people with tech degrees, certs, and 2-year programs involved? We can't have all PhDs and astrophysicists running the elevator. So somehow we have to find this workforce and create them ready, willing, and able to support. And this goes back to Kevin's point about the infrastructure, the economy build, all these changing elements and how they have to be focused. And I think, again, in this environment, we better start early and start often.
Yeah, and just kind of leading right off of that idea, Bill, I agree with all the things you're saying. And, you know, kind of one of the aspects that I think is necessary to really push this forward is a greater level of market liquidity that recently we've seen in the venture capital world, a rather exponential increase in the amount of capital flowing into the space sector. 2014, it was only $200 million, and now it's in the billions of dollars a year flowing in. 2020 was a banner year. But on the scale of private equity, that's peanuts. I mean, it's a very limited pool, even though we have 1/7 of all the venture capital funding in the United States is already going towards space and space startups. And that sort of making this transition in the infrastructure to the financial infrastructure, both government and private liquidity is really important. That in many ways, one of the driving factors of infrastructure throughout history, and especially, the Dark Ages were in many ways the Dark Ages specifically because the Christian Church basically outlawed any usage of interest, and that stifled investment and the ability to expand into these new rich value areas and take out a loan to build on something in the future. And that when that was reinstituted starting in Spain, it very quickly led to the Renaissance and to the development of new ventures, exploring the new world, colonization. All of that stemmed from this increase in financial liquidity. And one of the biggest obstacles that we're facing right now in terms of building up this infrastructure and getting that economy rolling, getting those students not just trained, but giving them jobs. We don't have something like Arab Spring where you overtrain and under-deliver on the jobs. You need to be able to have the economy behind it, and you need to have the financial liquidity to fund those investments. And right now, space, for better or for worse, is still kind of seen in this woo-woo science fiction. Like, it's not taken as a very serious financial investment, and that a greater growth in using tools like in international development of blended finance to help improve risk-adjusted returns, employing government capital as collateral, are all very useful tools in helping to push this forward, so that all these different small enterprises and even the much larger corporations like Lockheed and Northrop can take and better utilize the flow of money to create those jobs and to create those business opportunities and everything we've been talking about all day today. There's more than enough opportunity and value here that you can create an unending number of jobs from this with sufficient leverage.
I'd like to.
Dennis Wright, can you jump in here and talk a little bit about how research and engineering initiatives can address what Bill and Kevin have just alluded to?
Sure. If I might respond to what was mentioned before concerning education, and then I'll go into that, Fitzer.
Okay.
I think what we're going to have to see in the educational system is more hybrid degrees, let's call it that. So I noticed that David Dotson has a degree in computational physics. And I ran up against this particular problem when I was at SLAC. Is that basically you either had a degree in physics or you had a degree in computing. And the two did not meet, and the two camps did not talk to one another. And yet that was a primary demand for doing the simulations in high energy physics and nuclear physics. So it looks like that field is starting to emerge, but I think it will be critical for the space elevator. So we'll need somebody who does the physics and does the computing both. And
somebody who very recently has gone through doing undergraduate in engineering physics, getting my master's in real estate development, I can say that while that does sound nice, there is a transition process of getting those people with combined degrees into adequate jobs, because it makes for a very mixed message.
Right.
And while I certainly would more than agree with you on the utility of that generalist role, so much of the way that our workforce and stuff is hiring favors much more specialization, especially early in your career, which kind of makes that effort in greater education and better understanding to be a luxury rather than a desirable path.
Yes, and now to get to Fitzer's suggestion about the research and engineering and how that would impact things. One thing that we're coming up with now in our study is that we seem to be opening up a kind of a region between molecular modeling and modeling of materials in bulk. And the experts in our group say that we don't know much about that area. And we could conceivably be opening up an entire new area of research. But if you can understand how to do things like take molecular forces and then build those into a prediction of the coefficient of friction and things like that, I think that's would be a tremendous advance, not only in research, but in engineering, because then you don't have to test things at first. You can put it into the computer and let the computer do that. And then you can build your engineering models. And so we can do a lot of the rapid prototyping if we have a better research idea of what these basic things are. And I think the more we look into things in the space elevator, especially at this interface between the molecular, or the microscopic and the macroscopic, I think that's the future for research, engineering, and education.
Hey, Bill. Bill, you and I worked in a time frame for education with industry. Comment on that when your turn comes up.
Well, so again, Dennis, you hit the nail on the head. This is an all-encompassing, not one area, not one specific. And this is an area where volume is important. The other concern that I have, and one of the nice things that EWE that was referred to as, it took people who were operators and it gave them an opportunity to understand how the industry worked. So it really gave them dual purpose. And I think this is something in this future workforce we're going to have to look at. If you're working on the moon or somewhere else and you have one job that you are doing, I don't think that's going to be sufficient in the future. You're going to have multiple roles and multiple things that you are doing. So your ability to, do basic reverse engineering is going to be critical. And there's some real attributes that you have to have that we kind of focused. I've got the gray hair too, so I can say it. We focused more in the past on, and we need to revitalize in the way that we think about educating and moving forward. I think, Kevin, your point is dead on, that all of the funds necessary drive the volume, which gives us the choice, the larger choice of people to do things. In a response to Martin here, I referenced, right now in just cybersecurity alone, there's over 650,000 openings for cybersecurity professionals in the US, 650,000. We're not meeting the demand there. Now, are all of them need to be 4-year degree? No. So part of the problem is really understanding, what does your workforce necessity look like? What is it? Where do you need them? And what are the skills necessary? So back to Dennis's point, which is really, if I understand what I need them to do and can educate so they have a basis, and then spread that out over multiple different areas, but that takes focus, right? That takes a hybrid approach to doing things. And then you've got the concern of, do I make it too hybrid, which means I've really diluted the skill set necessary to support. So I think there's a lot of things that we're going to have to resolve here as we move forward in this particular workspace area. The other thing that's interesting in this environment, where would I go do hands-on learning right now to do these kinds of skill sets? Right. So the crickets are the right response. There isn't. So again, we're making up this environment as we go. That's an important point. So now again, back to Dennis, which was simulators, capabilities, cloud tool sets. This is where it gets to be way more critical in understanding, so we can build those preliminary training capabilities and make them available to people at large. I just think there's so many cool things ahead of us.
Yeah, and I think that the diverse focus and attention to how do we build with a more data-rich environment is absolutely right on. I mean, Space Elevator aside, adapting to having that more, automation and being able to say, how do we ask the correct questions? How do we train that workforce is going to be really critical. And I think that the guiding piece along this is figuring out how to establish proper value change and figuring out how to make it so that we don't get an over concentration of wealth in, like, much as I think SpaceX is fantastic, I think that imagining a future where the SpaceX board controls the majority of humanity's relation with space is kind of a terrifying proposition.
Yes.
I think that there is a level of democratizing that space for the purposes of having multiple entrants is one of the very best features of the Space Elevator. That by reducing that transaction cost and lowering those barriers to entry, you allow a much greater proliferation of other players in the marketplace, because there are different niches that can be served by a Space Elevator that are totally separate and completely complementary to what SpaceX is doing for getting Starlink, for sending up the rockets, and really probably establishing that first reconnaissance base on Mars. That all of those things are completely they work together. This is not a competition against. This is a how do we collaborate to go further and to do more and to reach out and utilize all of the immense value in space.
So I think there's been some really good conversation in the chat around how early do you start, and I would argue what we need to do is to ensure that in the future we have less people with gray hair on the panel. And the way to do that is to start engaging students earlier. So let me just explain to you what I mean and dive a little bit on that. So one of the things that we're doing at the university is we sponsor, our students build a competition for the state of California around cyber. But for the last 2 years, that competition has been based in cyber in space. So last year's competition, that is our students at the collegiate level build it for high school and middle school students to participate in. Last year's competition was around a scenario that a commercial satellite was hacked and brought back to Earth. Due to the magic of Hollywood, since we're in California, the payload survived and the students were able to do forensics analysis on the payload. So here you have middle schoolers and high schoolers doing forensics analysis with Wireshark, with Autopsy, with other high-end technical tools, some of which are being used by the Department of Defense to protect our systems today, to evaluate what happened to a platform and figure out how it got hacked. Then they have to go downstream in the system and figure out were the networks influenced? Was there malware or malicious code that was influenced in the system as a result? The coolest part of this is to watch those students do this in a gaming environment. This whole competition was done in a competition using an AWS-based platform, Unity. The students were competing against other students. And at the end, we had students who came up to us and they said, I never realized cyber was in space. I never realized space could be so cool because it's like a game. It's all these different things that students learn differently. We have to find a way to make that learning capability, that excitement available for the generation that's really going to be running and supporting Space Elevator Future.
Mm-hmm. Yeah, and I think that infrastructure and the buildup of just supporting those families is super critical. I mean, even going back to the construction of the Panama Canal, one of the major differences and reasons that the American effort was so successful by comparison to the French effort largely was just the amount of industrial hardware they brought to bear. But they solved a lot of really complicated non-infrastructure problems, like just the prevalence of malaria in the water around the sites. The death rate was incredibly high there, and the lack of families that were able to be supported. So the construction of the entire city of Panama City was done just to facilitate housing the workers and their families, hospitals, all of the different parts of the economy that are necessary. That when we talk about developing a space economy, I've gotten posed the question before, what is the space economy? I'm like, why are you having a qualifier? Like, the economy is moving into space. That means you have to bring all of the economy with it. And that you need to be able to have those people who run the hospital, who run healthcare, who run schools, all the whole 9 yards, that needs to become involved and engaged in it, because that's how you change it. When we had all of the momentum swing that we had from Apollo, a lot of it was because everybody was paying attention to it. The United States as a whole kind of decided, we want to win this race. We're going to send more people to school. We're going to get people more engaged. You were excited about being, a rocket engineer as like one of the best things you could do. And that fervor and that belief in space was so important to driving it forward. Finance and engineering aside, just focusing our interest on it was critical. And I think that, moving forward here, what I'm thinking, as far as engaging the economics and workforce, is to really say we need to engage the economy into focusing on space, because it's a good place to invest, because it's a place to expand, and humanity likes to expand into new places. Mm-hmm. How we prevented the French Revolution for 200 years was expanding to the New World, and as soon as that stopped, French Revolution began.
It's an interesting thing that we talk a lot about infrastructure, and especially with its economic aspects. But to me, I often think about the scientific infrastructure. And one of my dreams is to see a space elevator which is instrumented at every kilometer of its distance, and perhaps with graphene-based Hall sensors, and rotating in and out of the Earth's bow shock and into the plasma sheath and all sorts of various poorly studied areas of the Earth's magnetosphere. We can get a real-time study, or heartbeat, if you will, of the Earth's magnetosphere by the space elevator itself being instrumented as a scientific instrument. And we can think about all of the other scientific projects which become enabled by the space elevator, such as launching large research platforms that could never be launched by rockets. A lot of these things come to mind. So we consider the economic infrastructure aspects, but I think we should also continue to look at the scientific infrastructure, and that will certainly breed interest.
Oh, sure.
Yes, Dennis, you're touching on something I was trying to lead Bill into. When he and I were doing things that we don't talk about, we were actually sent into industry, not to spy on them, for heaven's sake, but to co-learn the process that industry was going through and compare it to our educational things. I think what you're suggesting, don't let me put words in your mouth, but let me try this, that you're suggesting that a fundamental part, as in responsibility of the space elevator, is to extend the boundaries of the space elevator into the scientific regimes that you're alluding to.
Yes, exactly.
Okay.
Yeah,
now, by the way, I noticed that Tim is, I know you've been here all morning, but if Tim and Adrian and Pete Swan have questions, I know not one of you is shy, but go ahead and ask, because these guys deserve the questions.
Well, I'm never shy. Anyway, let's think about this. And one of the first steps we've proposed is the Space Elevator Institute. And what we need to do is address the issues. You guys just touched on the issues from cybersecurity to tech degrees. And, you know, I believe it's true. We got to have a whole bunch of tech degrees to make it happen. We have to have a bunch of PhDs to make sure we understand the science. But, you know, how do we get that involvement of the full range of education?
I think you have three factors. You've got a conversion factor that's converting people who do other things similar to this workforce. You've got a new start, which is how do I start training this, evolving this from zero, from scratch? And then the motivation to get the younger generation interested enough to come be in that zero start element. I agree with you. The academy, the concept of some place that is a designated place to go is good. But you have to be able to be not only a place to go do, but a front for sending the message out across the multiple educational entities.
Yes, and then education is great, and people learn all this stuff, and there are a lot of people who really like space and space elevators. But when it comes to having a career in space elevators, I think there are two people who are paid to do that work in the whole world right now, and so that has to change.
Yeah, I think that's what Kevin was getting at. Basically, is the whole evolutionary element, the correlation to the different facets in time and you know, industrial revolution, all those elements. Again, I hope we line them all up this time. That's all. It's just kind of a good time. Technology is there, cloud is there, all those things are there. As someone was saying earlier, you know, the format's kind of there already. We have to find a way to just plug it in. Well, I think it's more than plug, it's motivate them in. Get them excited about being involved and excited about learning and going forward, and then really taking it off.
Bill, you make an interesting point, just picking up from Dennis, that there's only 2 people in the world actually being paid for space elevators, and we're talking about the biggest construction project of mankind. And I think you're right. You made a point earlier that this thing is going to experience an exponential rise very, very soon and very quickly. How the hell do we all hang on?
Yeah, I can go back as short as 5 years ago, and people told me at the CIO of the university, cloud is not going to take. It's just not real. It's only somebody's computer talking to another data center. Oh my God, what has happened in 5 years? Right? I dare you to name a major corporation who isn't cloud-based in some way, shape, or form. Right? Even federal governments are cloud-based. It didn't take off, it exploded. That same technological leap is what I see for space elevator. I mean, again, all the reasons not to, you all have made it very clear today, those reasons don't exist anymore. All the reasons are there now to go do. So when that go do gets done, it will do, I think, very similarly to what cloud has done, which is to accelerate right through the roof. How do you prepare for it? We have got to focus differently than we did in cloud and differently than we did in cyber explosion on developing a path for workforce development now, as we are both doing the R&D and test evaluation, and be ready.
Yeah. And I think that I'm going to draw upon somebody else's analysis entirely of looking at ARC investment, and particularly their focus on the use of rights law, and how as you get a growth in an industry, it's based on the number of units produced. So you get more units produced and the growth accelerates. And that we've seen, like in the falling cost of batteries, or even more so in genomics, this rate of cost reduction well exceeding even the rate of improvement that we've seen in computers, which is stupendous in its own right. And following, these kinds of patterns, so much analysis and focus is on these linear trends, because that is generally how humans evolutionary think. And even though we can do the math, and I'm sure everyone in this call is capable of doing an exponential, it is just not an intuitive way for humans to think. To imagine, as simple of a difference as, okay, I'm going to earn 12% interest this year versus I earn 24% interest this year. Over a 30-year time period, that's a difference of 32 times your money or 1,024 times your money. And that difference is so great that it's very difficult for us to work with. So when we're creating policy and we're creating trends, to Bill's point exactly, we have to look at what is the data here? What is this exponential pattern? What are we actually seeing? And that if we plan for our workforce and our economy according to the data that we see, rather than our straight line projections, we're going to get very different answers. And I think that just a little bit of a reframe to look at what those numbers really are, and to do that data, and to Adrian's point, to start getting the seed money to do that analytical work and really dig in, to be like, okay, if space elevators are going to take off, if we're going to start to see the scaling and the manufacture of single crystal graphene, how quickly is that going to happen? Based on our models, is it going to take 10 years? Is it going to take 15? Like, looking at what that curve looks like and the demand effect it will have on the marketplace, I think is an absolutely perfect place to start. And it's what I, sort of proposed in my panel, is that right now we're in the seed funding phase. And there's not a line at this point. I wish there was, but we got to focus on what is something we can show today, and start to get professionals and professional credibility to build these academies, to build this knowledge base up, because it is coming and we do need it.
I'll tell you one thing I'm observing as well is there's a heck of a lot of solid foundations being laid by ISEC and everybody else. The groundwork's there, and now I'm seeing, as well as the technology moving at an accelerated pace, Tim, the stuff you're doing is really important. You're accelerating the socializing around this and getting those messages out, and that's never happened before. And I think something profound will probably happen as a result of what you're doing.
Yeah, it seems to me that the demand pull is there. We were talking about all the different people who need stuff in space. but they don't know that their demands are so large. There are so many people that are dreaming and given visions, and we could do this and planning for this, but they haven't stood up and said, I need this movement. And so we need to have the demand pool stand up and start saying, I can't do space solar power without space elevators. Now we have Dr. Dodson there, David, is taking on a big challenge. He's going to present a topic inside Space Solar Power Symposium in the IAF, assuming that paper gets accepted, of course. And he's going to stand up and say, you can't do it without space elevators. And that's a big step. And that's the type of thing we need to take on. And we need to have the ability to talk to the people who have the demand pull arena. So they step up and say, oh, yeah, we need to do this. By the way, to do this, we need space elevators. I don't know how to do that. If anybody does, send me an email, call me, Skype me, whatever you want to do. But we need to start thinking about that particular issue. How do we get acceptance out there and people realizing that they really need us? We know they need us, but we need them to realize they need us.
I think the key thing to that, Pete, is focusing on the smaller scale applications of the material. And so there was this discussion in the chat and in other places about discussion with Elon Musk and build me a footbridge, then I'll talk to you. Lots of other things like that could increase the public awareness that it is possible. And
I
so we
endorse
really
that. Yes. Yes.
we really should
100%
be
agree.
Supporting civil engineering projects which use graphene or other strong materials. And much like, the Eiffel Tower and the Ferris wheel were built to demonstrate that steel was safe and reliable. We need those things.
Well, maybe we could have an intern at the University of Manchester that gets tasked to build a footbridge with at least polycrystalline graphene, and does it,
Yeah, interesting you say that, Pete. We're not quite doing that, but Bill might be interested in this. The University of Manchester organises a graphene hackathon, and we're the publishing company. We sponsor that. We have done for the last couple of years, and now we're beginning to introduce sheet graphene into their thinking already.
Great.
So we're trying to get them playing with the material, thinking about the problems. Dennis, as you said, creating the small devices and actually seeing this stuff's possible. All the way up till now, it's all been powders. Now, in the last few months, we can see that people can get hold of sheet material and start playing with it. And Bill, gamification, that's really important too, just making things fun. Yeah.
Absolutely.
Oh, absolutely. And I would say, just on this idea of the footbridge, I really like the optics of. I think that so many people just have no conception of what a space elevator even is. Like, there's lots of quotes in here of university professors being like, "Oh, actually, your data is wrong. It couldn't be at that speed, at that height." It's like, well, it's not in orbit. What do you mean it's not in orbit? And just the basic understanding that it is a cable in traction has not perforated into even the academic community. And the concept of graphene, even more so. Like, if you think about, what is a space elevator, like a tower to space, people think something more like the Eiffel Tower. They don't think of something like a freaking film of a bubble, little rainbow shimmery bifrost going into space that you're going to climb along this slippery film. And that's going to be strong enough to have a 20-ton climber just ascend on something you can hardly even see. And I think that, even if you can build this scale model of something, even at a small scale, that's going to make such a big difference and make people realize, because so much of the stumbling blocks and the hurdles we're seeing right now is just those technical demonstrations that Fitzer and Swan have both highlighted as fundamentally critical. I think that there's also a little bit of, I believe it when I see it, that engineering aside, people just don't think this is real.
Yeah. And it's also the researchers involved in graphene as well, Kevin. So that give you an idea about the problems we're facing, just getting the message out there. people are concentrating at the moment on graphene for electronics, and when you layer it up more than 10 layers, it becomes graphite, and it loses its electronic properties. So what we're talking about is making large-scale sheet graphene and layering it up and layering it up. And the pushback we're getting even from PhD researchers is, oh, well, you're just making graphite and it's going to lose all its properties. No, this is a fantastic new frontier material, and we're trying to get the scales to fall from people's eyes. So it's an uphill struggle, but we're getting the message out there and starting. But this is why the socialization aspect is so important.
I'm sorry, I'm going to jump in here for a second. Liftport was famous for our stunts. And yeah, there was science there, but I mean, you see our robots behind us. We did a lot of stunts, and that's how we got our reputation. It was a long time ago. It was more than 13, 14 years ago when we closed. But we did a lot of stunts, and they were very effective. We went out to MIT and we put a cantilevered arm out over the side of their tallest building. And on a snowy day in December, we climbed up and down with one of the robots, not one of these here. We went out into the desert and we climbed a mile into the sky. Those stunts, they teach us something. I mean, we definitely learned things along the way, but they have huge value. And it's important to note that we did all of that work before Facebook and Twitter. So if you copied those same stunts, did them again today, I guarantee you viral visibility. So just do a couple stunts, whether it's a footbridge, whether one of the things we were doing this summer when everything fell apart. There's a big bridge here. Everybody knows the Tacoma Narrows Bridge. It's that galloping Gertie that they teach in engineering class. So that's only a few, like 6 miles from here. We were going to put a barge at the bottom and have our ribbon attached to the top and down to the water. And that, because it's the galloping Gertie, every engineering student in the world is going to have an association to that. Those kind of stunts have value. So, you know, they generate science, like it wasn't wasted effort, but it also would have kind of global attention. So I'm happy to chat with anybody about those things, the things that we did and the things that we didn't do.
I'm all on board with that plan. And I think that it goes along with this sort of the seed funding and the pushing up of building this institute, gaining that momentum, really starting to build up all this stuff that Bill has been talking about of we need those people. And part of it is just getting them off the starting block, giving that dream to reach for, that, you know, convincing people in the early 90s and the late 80s of that a call like this could be happening on the internet would be a pretty hard sell. You know, it's difficult to take and tell somebody we need to start building data centers. We're going to need them. Like it's too much to try and jump all the way to the vision that we may be talking about because we're so immersed in it. You know, for the day-to-day, you have to focus on the what happens in the next year. How does this matter to me? Part of it. And that's where I think your stunts to get people rolling on the education and to dive in and to learn more of the depth and the excitement about what a space elevator can do in the future. Only then can you get that message across. But you got to start with something easy.
Well, I like Lee's. I don't know if you guys saw the chat there. Lee came up with a brilliant idea, which is instead of a footbridge in the University of Manchester for people to bounce back and forth, have a wildlife bridge. So we have a bunch of squirrels go across it, or bears go across it, or something, and you know, we would have an instant audience for that, and then we could tell people, well, it's a you know, new material that's measuring the density of the hooves of the deer. You know, I mean, we could really do something with that. So I like the thinking. What we need to do is expand this line and figure out who can do it. Now, I have a basic rule in my organization. Everybody who works with me knows there are some really, really fantastic ideas out there, but if they don't have a champion, they don't count. So I'm just putting the challenge out there. Join Isaac and jump out there and take on the challenge of trying to figure out how to do a footbridge. That would be really great. And I use the footbridge just as an example. It could be any type of, show and tell. with the new material, 2D material. But we need somebody to jump in and say, "Oh, I could probably run that. That'd be fun."
Okay, for the sake of sanity, let me relinquish control and pass it back to Lee, and I'll probably talk to everybody on the screen in the next 2 or 3 days. So back to you, Lee. You got it.
Thank you so much. As we close out the day, I'm going to turn it back over to Tim Chrisman and Lila Gislason to make the summary remarks for the day, and I will repost the QR code for getting involved with Foundation for the Future.
Thanks, Lee. I think this panel was an excellent way to wrap the day up because here the talk around what's next, what's now, and how do we prepare for success merged with what's tomorrow. And that is something that probably everyone on this call struggles with tomorrow. We look years in advance, sometimes to our detriment, when our families ask us what we're doing. But being able to bridge the gap between the rest of society, those not super early adopters, and giving them, hey, here's your training plan for a reskilling certification. You can do that for the next so many days. How this footbridge, this, demonstration projects, and that's a challenge for us within the community to tie back to tomorrow and now and here. How can we take what's needed for a space elevator and make it work now? There's been a number of conversations about this is the largest project that humanity's ever undertaken. I would argue against that. We have 50 billion devices connected to the internet right now. And 1 second after I finish this, we will have another 200 connected. We have a living organism in the form of a connected network of devices that we made. We can learn the lessons from that, and that's part of what I think Bill's message is the cyber workforce build out could have been better. But let's take the lessons from humanity's last mega project that we just kind of stumbled into, and we're like, it'll be like the telegraph, which is kind of what we did, and sort of build from there as we, go into the future, making that accessible for the rest. So thank you for being here. Tomorrow we're going to continue with wild, ambitious projects, and we look forward to seeing you. QR code to support us here at the foundation is on the screen. We'll leave it up for a little while. Some of you have already donated today. Thank you. And we'll see you tomorrow.
Do we have an agenda for tomorrow and Wednesday?
We do. It's all the best agendas. So tomorrow we will be kicking off with an update on the sort of political environment that exists right now, both in DC and out in some of the states. We'll also hear from NASA and the International Space University in how they are supporting innovation and sort of pushing the edge in the space and space elevators and other sort of groundbreaking technologies. And then Thursday, we will go into lunar elevator. So where today was Earth elevator all day, we will have a demilitarized zone between the 2 days. The combatants will then re-engage on Thursday at a time and place of their choosing. It's going to be very polite, very reminiscent of old European battlefields. I look forward to it because those were the best uniforms in history. So
choice description there.
Do we have an agenda for Thursday?
No, that was Thursday, lunar.
I know, but it's a long day. We don't have an agenda. Okay.
We have an agenda. I'm going to read it off to you. And Lila just posted it at bluemarble.week.space. We had all the things that Tim's already mentioned. Representative Matt Banky is going to come in and talk about strengthening the industrial base. Ryan Stewart's going to come in and talk about NASA innovation. International Space University is going to come in and talk about workforce development. A guest that we have quite regularly, Michael Mealing, is going to talk about market readiness levels. Again, that goes back to the infrastructure. Yeah, Lee. We've got an announcement that I'm not going to spoil, but Michelle Hanlon is going to be making an announcement that deals with the National Space Society and her university, Ole Miss, and their law program. And then I'm going to give a nearly 2.5 hour workshop on what I refer to as the Numenia process, which is a tool set that I've been using for 20 years in my effort to build out the elevator. And I wanted to share that because I think a lot of people in this call can use that tool for their own efforts. So that's a workshop in the afternoon. We've never done a workshop before, so really have no idea how that's going to go. So fingers crossed. And that's all tomorrow. And then Thursday, Lila is going to talk about some of the vision regarding Blue Marble Week, where we're going, what we're doing. I'm going to spend some time talking about lunar elevators. We have another announcement also by Michelle Hanlon. I'm also not going to spoil it, but there's some really cool stuff they're doing on the moon. And then we have a fundraising panel, not so much as ask. It's not like that, but it is, what are we doing? What is the Foundation for the Future doing? Why does this organization exist? What are the plans going forward? And then finally, we cap off the afternoon with 3 people that I'm just super excited about. Mitchell Zappa is a futurist. His actual job is to have a crystal ball and look into what the near future looks like. And I think that's pretty amazing. Dr. Nien Ong is coming in from Australia. He is a professor at Monash University, and he was an intern for me 17 years ago. So that's pretty amazing to watch him evolve. And then the chief scientist of U.S. Space Force, Dr. Joel Moser. They're going to all be talking about the future. And then we'll have a panel kind of like what we just had a moment ago with the 3 of them talking about the future. So they'll each do their own thing, and then at the end we'll have a panel. And that's Thursday. And then next month we do it all over again, 3 weeks afterwards, and we have an entire new program relating to orbital manufacturing. So we sure hope that everybody joins us for that as well, because that's the next big step. All right. Tim, any last words? Can we close this off? All right. We on the team are going to figure out, hopefully not how to have the problem that we had first thing this morning reoccur. So we're going to do some troubleshooting. Expect a link. I don't know if it's going to be this one or if it's going to be a different one, or if we're going to go back to the original one, if we can figure out how to lock it down. So just expect a link, check your messages. We'll see y'all in the morning. All right?
Okay.
Thanks everybody.
Thanks, everybody. That was great.
Really appreciate the International Space Elevator Consortium for all of their work managing today. I am very grateful. The team is very grateful. Thanks. Bye, y'all.
All right.
Thank you. Bye.